and welcome to Python for Aerospace. My name is Angelina Savoy, and I'm thrilled to be your instructor for this completely free and online course. Aerospace is an exciting and thriving industry with numerous job opportunities. The aerospace market is expected to grow from $298 billion in 2021 all the way up to $430 billion by 2027. With an increasing demand for innovation and talent, there's no better time to get involved in this industry. We will kick off this course with an introduction to Python. From there, over a series of 25 conceptual lessons, we will cover all the essential skills you'll need in order to apply your programming expertise in the aerospace sector. For the first module, you'll learn the basics of Python to create your own aircraft performance calculator. As we move on, you'll develop more advanced projects, culminating in a custom satellite trajectory analyzer for the final module. By the end of this course, you'll have completed 5 projects that you can showcase on your resume or programming portfolio. I can't wait to see all the amazing projects you create. Now let's get started. In this first lesson, we'll be covering the core terminology of Python and a concept called variables. Firstly, what is Python? Python is a popular programming language for data science and research. It is known for its simple syntax, making it easy to read because it is a high-level language. And it's also known for its large developer community, meaning that if you ever have an issue or need help with your code, there's more likely a community of people that's going to be able to help you out with it. It's also used in a wide field of studies such as data analysis, artificial intelligence, automation, space, and more. The first concept we will be covering is something called variables. And you can think of variables as boxes of data stored within the memory of a computer, also known as RAM, which stands for Random Access Memory. And depicted below, I have 3 instances of variables. They're all depicted as boxes. And here, if you see, I have a variable, and a variable has 3 core characteristics: a name, a data type, and a value. So in this case, I have a variable name. It's called my var, and I have a variable value. It's assigned to 3.14. And a data type you can think of as classifications of variables. So in this case, I have a 3.14 variable value, and that's something called a float. A float is a number with decimal points at the end of it, so 3.14, that classifies as a float. So in this case, I have a variable name, my var, with a data type of float, assigned to a value of 3.14. And you can think of it as being added inside of this box here. Moving on, we have another variable variable instance, and it has a name of hello, a data type of str, which is short for string, and string you can think of as text. In this case, I have a variable value of Alice. You can see here it's not a number, it's text, so it has a data type of string. In this last example, I have a variable name of favenumber, and it's assigned to a value of 36, and because of that, it has a data type of int, which is short for integer, and an integer is a number with no decimal points at the end of it. So in this case, it's 36, no decimal points, so it has a data type of int. Moving further into data types, you can think of data types in this analogy as colors of boxes, and data types in general are classifications of a value of a variable can hold. So here I have examples of 6 different variables, all depicted as boxes, and you can see the data type of the variable is dependent on the value. So each of these 6 variables have different types of values. Here I have 3.14, and that is a float because it is a number with decimal points. In this variable, it's Alice, which is text, so it has a data type of string. In this variable, I have 36, which is a number with no decimal points, so it has a data type of int, standing for integer. And you can also have true-false statements in computer science, and those things are called booleans. And in Python, it's denoted as bool, so it can hold anything that is true or false. And whenever you want to store multiple values of the same data type in a variable, you're going to be using something called a list. So in this case, I want to store the values of 1, 2, and 3 inside of a single variable, so I use a list. And you can also store nothing inside of a variable. And whenever you store nothing inside of a variable, the data type is none. So this leads us into the first exercise and lesson of our course. So if you head over to the Jupyter Notebook localhost server, you can go under Chapter 1 and Lesson 1 Python syntax. And when you open it up, you should have a graphical display like this on Jupyter Notebook. And we covered what Python is already. You can learn more about what Python and its capabilities at their website here. And like we mentioned before, we're going to be starting off with variables, and a variable acts as a container within a program, which is capable of storing information of different types, such as numbers, text, and more. And I show an example of a variable being assigned with using this code below. And you can see that first you need to give a variable a name. So in this case, I want to name my variable favorite number, and I'm going to assign it to a value. In order to do this, I'm going to use an equal sign. If you've ever done algebra before, this is like a common denotation of assigning a value to a variable. So I use equal sign, and I'm going to set it to the value of 10. So you can do so with the following, and you can see here that we have the name and the value. Python is implicit about its data types, meaning that it does not show the data type when you declare a variable statement. So in this case, this is an int. This is a comment, by the way. This isn't interpreted by the code. This is just to make notes on your code. So I put a hashtag and then a note saying this is an int data type. And if you recall, an integer is a number with no decimal points, which is what this variable is assigned to. So in this case, I have set this to the number 30, and it has an int data type. In order to run this code cell, you can do it in two ways. You can go up here, go to run, and run selected cell, and you can see it isn't highlighted anymore, and it'll go to the next code segment. And you can see it prints out nothing. It doesn't really give us any visual feedback, but under the hood, it's storing this information under this variable name. And I'll show you guys this later. You can also run code within code cells by using a shortcut by typing shift and then clicking return. So if I go here, shift return, that will run it for me. And that's really handy if you have like a bunch of code cells sequentially and just want to run them really quickly. So let's say we do want to have a visual display as an output. We can use something called a print statement. And you can use print statements to pretty much print any kind of text onto your screens, including numbers, characters, and more. So in this example, you'll need a print keyword. So in this case, I'm using print, and then you have parentheses. And inside these parentheses, you put in whatever you want to print out. So let's say I want to have something that says hello world. This is text, and whenever you want to print out text, you need to enclose it within these quotation marks. And you can see here, if I press shift return, it prints out the text enclosed within these quotation marks onto the display here. You can also print things of different data types. So let's say I want to print a number. A number doesn't require quotation marks around it. So let's say I just want to print 34. I press shift return again, and it prints out 34. I can print out floats as well, and so forth. So let's say I want to print the value of favorite number onto the display. You can do so by putting in the name of the variable within the parentheses of the print statement. So here, I have the print statement and enclosed the name of favorite number. And when I print it out, I have 30. This is because up here, I assigned the value of 30 to the name favorite number, and that gets stored within the memory of the computer. And when I print it out here, it pretty much gets that information and then prints it out. So let's say I wanted to change this to be a different number, not 30. Let's say I want it to be 10. I would just go up here, change this to 10, shift return to make sure that it updates the memory, and then run it again, and you can see that it will print out 10. This leads us into the first exercise of this course. And in order to do an exercise, I list out all the objectives here, and you just pretty much have to follow the instructions I list out. I'll be walking through each of the exercises in order to make sure that you understand what they do, but I highly recommend that you try them out yourself before you refer back to this video. If you want to see clear-cut solutions to each of the different exercises, you can go to the Jupyter notebook here, and under each chapter, so in this case we're in chapter 1, there will be a solutions folder. And inside the solutions folder will be another notebook with the solutions inside of them. So let's say I open up the solutions for lesson 1. You can see that I have the solutions outlined here. So give it a shot yourself and come back to this video when you're done. Okay, so to tackle this exercise, let's create a cell below. In order to do so, you can press B, or you can click this little icon here. So I'm going to click that. And firstly, it asks us to assign a variable called random number to a number of your choice and print random number onto the screen using the print command. So let's first create a variable. It's going to be called random number, and I'm going to assign it to 33. And then I'm going to use the print statement, and in order to print the value of a variable, you need to enclose the name of the variable within the parentheses. So I'm going to paste this in there, and now if I run it, I get the output of 33. Moving on to data types. Data types are analogous to categories that tell a computer how to understand and interpret different kinds of information. And as I mentioned, Python has a lot of support capability for an array of different data types. And here are some. There's integers, which are full numbers without any decimal points. So examples would be 33, 102, 22, so forth. A float can be a number with decimal points. So it can be 3.14, 22.0. It can also be whole numbers. So floats encapsulate more numbers than integers because they are inclusive of numbers with or without decimal points. So another example of a float would be -19 for so forth. Strings, you can pretty much think of text or characters. So I have cat, dog. Characters are single text, so it would be like A, B, C, D, so forth. Booleans are true or false. It can only have 2 different types of values, and it has to be capitalized, so true and capitalized false. Lists are ordered collections of items, so I can have a list of integers, so in this case 1, 2, 3. I have a list of strings, apple, orange, kiwi, and then tuples are lists but immutable. Immutable means that its value cannot be changed. So whenever you assign a variable to a tuple, it's set in stone. You cannot change it. So here I have a tuple with 10 and 20, another tuple with strings, Alice and Bob. You can also have mixed tuples, where you can have values of different data types. So in this case, I have a mixed tuple of 9. This is data type string, apple, and a data type of float, 3.14. Dictionaries are collections of key value pairs. When I say key and value, means that it has a key here, and then a colon, and then a value. So in this case, I have a dictionary representing fruit prices, and the key is the name of the fruit. So the keys for this dictionary are apple, banana, and kiwi. And the values are the prices, which are floats. So for apple, I have 1.99. For banana, I have 0.99. And kiwi, I have 1.49. And lastly, we have sets. A set is an unordered collection of unique items. So you can see that we can have a completely organized set where everything has the same data type, like here. We can also have very unordered collections. So here I have one, which is a data type of int, apple, a data type of string, and a data type of bool of true. So it gives you a little bit more leeway in regards to the types of values you can store. Awesome, so this is me showing an example of assigning variables of different data types. Here I have an even variable set to 4, which is data type of int, pi, the data type of float, name, data type of string, data type of bool, data type of list, data type of tuple, and a data type of dict as dictionary. You can feel free to play around with assigning variables again and try playing around with different data types. And this leads us into exercise 2. And in this exercise, you are an astronaut tasked with creating a mission report for a spacecraft going to Mars. And you are given a task to initialize variables for various aspects of the mission. So give it a shot yourself and come back to this video when you're done. Okay, assuming you gave it a shot, I'm going to create another cell under this. And let's start off by assigning each of the variables. So the first one it tells us that it wants us to create is astronaut name, and it wants us to set it to a value of data type string with your name. So I'm going to astronaut name, and I'm going to assign it to Bob. And the second one is telling us to create a variable called astronaut age. I'll just copy paste it. And I'm going to assign it to an integer value with your age. So this astronaut is 33. Next, we need to assign a variable called fuel and set it to a float value within 30.0 and 53.0. So let me just pick a number in between, 43.2. And it has to be a float, so make sure you have a decimal with some kind of number after it. Next up, we need to create one called isEngineRunning and set it to a Boolean value. So Booleans are true or false values. It would be sad if our engine wasn't running, so I'm going to set it to true. And then assign a variable called astronauts and set it to a list value containing string of values of each of the names of the astronauts. So let's first begin by creating our assignment. And a list value is an ordered collection of items. So we have these brackets here. And inside these brackets, we have independent values with a specific data type. In this case, it wants it to be a string data type, so that will be text. And let's give astronauts a name. So Bob, Alice, and let's say Charlie. And lastly, assign a variable called astronaut ages and set it to be a dict value, with the key being the name of the astronauts and the value being the age of the astronauts. So a dict, you can see an example of a dict here. We denote it using curly braces. So I set it equal to curly braces, and we want the key to be the name of the astronaut. So let's make one for Bob, and he is 33. So in this case, the key is the name and the value is the age. And let's do it for each of the rest of the astronauts. So Alice is set to 25. And then we have Charlie, who is 22. And now I'm going to run shift return. So this is saved, and I'm going to create another code cell below this. It wants us to print out all the variables, and We can make print statements for each of these things like the following. I can do print astronaut name, I could do print in parentheses astronaut age, and I could have 6 lines of code, right? I can make a print statements for each of these 6 variables, and it will work. But we can do this in a more simplified fashion that doesn't take up 6 lines of code, because as you become to think more like a programmer, you want to minimize the amount of space of redundant information your code takes up. And a way you can simplify this into just 1 line instead of 6 lines is by separating each of the variable names using commas within the print statement itself. What I mean by that is I can put in the variable name astronaut name, put in a comma, and an astronaut age. If I print it out, it will give us the name and the age separated by a space. So now, instead of 6 lines of code, we can just condense everything into 1 line of code just by separating all the variable names using commas. So let's put everything in here. And now if I run shift return, it should print the values of each of the different variables we assigned up here. Moving on to basic operations, Python allows you to conduct basic mathematical operations. You've probably done these before. We have addition, that's done using the plus sign, so 3 plus 4. Subtraction, which is the minus sign, 5 minus 2. Multiplication has this weird funky symbol called the asterisk, which kind of looks like a star or a snowflake. And here I have 3 times 8, 3 multiplied by 8. And then division has the slash sign, so 24 divided by 4. And then one additional operation is called the modulus. A modulus gives you the remainder output. So for this case, and it's denoted by the percentage sign. So I have 5 percentage sign 2, so 5 modulus 2. The remainder of 5 divided by 2 is 1, because 2 fits into 5 2 times and has 1 left over. So this will give us 1. So here I have examples of setting variable names equal to the output of these operations. So here I have a variable name of add set to the output of 3 plus 4, subtract set to the output of 5 minus 2, and so forth. And here I'm printing out the values of these variables. And you can see when I print it out, I didn't run, make sure you run the code cells. When I print it out, I get this output here. Addition, we have 7, which makes sense because 3 plus 4 is 7. Subtraction, 3, 5 minus 2 is 3. Multiplication, 3 times 8 is 24, which is 24. Division, 24 divided by 4 is 6, so I get 6. And 5 modulus 2 is 1, so I get 1. And here I'm just using the comma notation again. In this case, I'm just putting in text that describes the operation and the value output of the operation itself. So it gives us all this information in a nice, clean way. You can also perform operations on data types that are not numbers. So for example, you can do this with text, with strings. So for example, let's say I have 2 variables, first name and last name, set to the first name and the last name of a person, and I wanted it to be condensed into just 1 piece of text. I can have an operation that uses addition and adds a white space in between. So for example, I have this variable name called full name, and I set it equal to the first name plus a blank space plus the last name. And now if I print out full name, it gives me this, John Doe. And the reason why I add the white space in the middle is because let's say I just did first name plus last name. It'll just give me the first name directly attached to the last name, and we don't want that. So in order to remediate that, I just put another piece of text in there using quotation marks, and within those quotation marks, I use a blank space And now when I run it, it gives me John Doe with a space in between. This leads us into the last exercise for this lesson, which is a space resource calculator. In this exercise, you are a mission planner for an upcoming spacecraft launched and are tasked with computing the following values outlined below. So give it a shot, and if you need some help, I added a hint here describing all the equations you will need to tackle this problem. Distance is equal to speed times time, fuel consumption is equal to distance divided by fuel efficiency, and time to destination is equal to distance divided by speed. And I have these variables hard-coded for you. So when you're tackling these problems, just make sure to use the variables that are provided for you, and make sure you run it beforehand so you can use it. Okay, so in order to do this problem, let's start by creating a new code cell below. And firstly, it wants us to calculate and print the total distance traveled. So firstly, I'm going to be creating a variable, and setting it equal to the value of the total distance. So let's call it total distance. And I'm putting an underscore in between just to make it easier to read. And I'm going to assign it to speed times time because that's the equation I have for distance. And we can see here that we already have speed for us pre-assigned, and we want it to be multiplied by time, and multiplication has this star-shaped asterisk symbol, and then we use time, and we have travel time here. So I'm going to copy and paste that. But the second thing it wants us to calculate and print is total fuel. So I'm going to put total underscore fuel, and I'm going to set it equal to distance divided by fuel efficiency. So we calculated distance here. We'll put total distance, and then to divide, you just put a slash. So I'm going to put slash fuel efficiency, which is predefined here. And then lastly, I'm going to calculate the total time to destination. So let's call it total underscore time, and we're going to set it equal to the distance divided by the speed. So we have total distance here, and then we have the speed up there. So I'm going to put slash speed. And then lastly, it wants us to create a variable called full name and print out the full name of the astronaut. So here, let's say full underscore name and equals first name. And then we're going to put a plus, and we want a space in between the first name and last name. So I'm going to put quotation marks with a space in between, plus last name. And then now we want to print out all the values. So I'm going to run this code, and I'm going to create a code cell below it, and let's do print. And I'm going to print total distance, comma, the total distance. This is just to denote which one of the numbers is affiliated with the variables, because if I were to just do this, it'll give me a number, and if I were just a random user looking at this application, I would have no interpretation as to what this number is. So in order to make this clear to whoever the mission planner is, we don't want them to have any problems, especially for something as intense as mission planning. So we put in total distance, comma, the name of the variable, and you can see here, it makes it nice and clear. Let's do this for the rest of the variables. So we have total fuel, and I'm going to put in total fuel, print total time, total time, and then print the full name. I'll just do this full name, and then comma full name. So now if I run this, we have total distance of 50,000. Makes sense because 5,000 times 10 is 50,000. Fuel, which is 5,000, which is the total distance divided by the fuel efficiency, which makes sense. And then total time, which is total distance divided by speed, that gives us 10, and then the full name of the astronaut, Sally Ride. Welcome to the second lesson. In this lesson, we'll be covering handling data, and the first concept we will begin with is something called typecasting. And typecasting is when you convert a value from one data type to another data type within the same variable. So in this case, I have fave number, and here I change the data type of fave number from a float to an int. And you can see here the value of fave number is 3.14, and I convert it to a data type of 3 because an int does not have decimal points included in it, so it goes from a float to an int. And this process of converting a variable from a data type to another data type is called typecasting. And one thing to note about typecasting is data loss and order. So some data types in Python have more capacity of data it can support than other data types. So for example, an int has the lowest capacity because it can only store numbers with no decimal points included, and it has less capacity than a float per se that has support for both integers and numbers with decimals appended to the end of it. And this order goes like the following. Double has the most support, while int has the least support. And when you are typecasting from, let's say, a double to an int, you're moving to the right direction in this case, you will experience data loss. While if you go to the left, let's say you're typecasting from an int data type to a double data type, you will experience no data loss. There's two primary storage mechanisms in Python. There are arrays and lists. Lists are built in. They can support multiple data types and are dynamic in size, while arrays have to be imported with libraries, can only support one data type, and are fixed in size. So here's an example of a list, and a list is denoted using brackets. So for every list, you'll have these surrounding brackets, and inside we have each of the different items known as elements, and they are all separated using commas. And each element within a list has something called an index, and an index is a way to keep track of where an element is within the list. So for example, A here has an index of 0. All indices start with 0. That's a common, standard in computer science. And it moves up from 0. So A has an index of 0, B has an index of 1, C, 2, D, 3, and so forth. And this comes in handy when you want to refer to a specific item, specific element within a list. So here's some common operations you can run on lists. So let's say I assign this list to a variable called alphabet, and I can get the length of that list by using the len keyword, len, and inside parentheses enclosing the name of the array, so alphabet. In this case, it will give me 5 because we have 5 items within that list. Let's say I want to get a specific item from that list. This is where indices come in. So let's say I want to get A. We know that A has an index of 0, so I can mention the name of the list. So I say alphabet, and then I put brackets right next to it. Inside those brackets, I put in the index of the desired item I want outputted. So in this case, I want A, so I put in 0. In the second one, I get the value output of C because C has an index of 2. And you could do this special technique if you want to get the last item of any list. You can do the name of the list, and then within brackets, you get the length of the list and subtract it by 1. So what this effectively does is this gets the last element because we know that the output of this will be 5, and E has an index of 4 because we all start off with 0 for indices in computer science. So we add the extra, we we subtract the extra 1 within the operation in order to account for that, and that will always give you the last item of a list. You can also get multiple items as your output using something called slicing. In slicing, you kind of have the same kind of structure with the brackets, but inside the brackets, you put in the index where you want to start, separate it using a colon, and then the index of where you want to end, but it is not included. What I mean by that is, let's say I want to get an output of A and B. A has an index of 0, B has an index of 1, and C has an index of 2. You can see here that A and B are included within the first statement, where I start at 0 and end at 2. A will be included. This is an inclusive index, so we have A, but this is exclusive, meaning that it will limit up to this index, so it will not include C. It will only include up to that point. So include A and B. Let's say I wanted to do this in shorthand notation. You can just get any slice starting from the beginning of an array, or list, by putting the comma, putting nothing before the comma, putting the comma, and then putting the end index, which is exclusive. So this effectively does the same thing as above, it's just a little bit shorter, removing extra redundancy. And let's say I wanted to get a slice from the list starting from the end. I can do so by getting the number from the end. So let's say I just want to get the last two numbers. So I just put -2 and then put a comma at the end of it. And that will give me the last two numbers from a list. You can also delete specific items from a list. You can do this by using the del keyword and within parentheses enclosing the value of the item you want to delete. So let's say I want to delete C. I will put alphabet bracket 2 because that will give me the C value, and that will effectively delete it from the list. You can also add things to the end of a list by using the append keyword. So you need to denote the name of the list and put a period, and then put a word called append, and within parentheses, put in the value of the item you want to add. So in this case, I append F to the end of the alphabet list. You can also reverse the direction of a list by using this little notation here. And within the brackets, I put 2 commas and this -1 sign. And whenever you use this combination, it will always reverse the direction of the list. So moving on to the Jupyter Notebook of this lesson, we'll first be covering typecasting. And remember, this is the process of converting a value from one data type to another. And an example of when you will be needing to use typecasting within a program is like the following. So let's say I try to perform an operation like addition on two different values with different data types. So here I have a variable num assigned 10 with a data type of integer, and I have an operation here where I'm trying to add a string data type with an int data type. And this mismatch between a string data type and an int data type will cause something called a type error, because it doesn't make sense to perform this operation on two different data types. The compiler of this computer is going to be freaking out. And it will give you an error that looks like the following. It'll say type error can only concatenate str, not int, to str, which makes sense. So let's say we want to make this code work. I still wanted to print out the number is, 10. So in order to work around this issue, we use typecasting. So we can do this by converting the integer num to a string. So I have num set to 10, and in this case, we wrap the num in the string keyword. And what this does in the back end of the computer is it makes it so that this number will be processed as text. So I'll think of it like this. The number is plus 10. It will effectively process the number as a text value, which will make this operation legal. So I run it again, and now you can see we get the output we want, which is the number is, comma, 10. Typecasting is also useful for numerical applications. Let's say you have an integer variable, and you want it to be interpreted as a float variable instead. Typecasting will let us do that. So let's say I have a variable here called num_2, and I have it set to 20. I can convert it to a float by wrapping the float keyword around the name of the variable using parentheses. So I say float, parentheses, num2, and this will effectively convert it into a float. So you can see that the outputs of this code block will give me 20, which is an integer output, and 20.0, which is a float output, because you can see here that I convert it to a float. How about the other way around? We can interpret a float to be an int. So in this case, I have a variable called numFloat, and I set it equal to 3.14. And I have this variable named numInt, and I have it set to the int typecast of float. So this will effectively typecast this value into an integer value. And now if I print it out, I get the number 3. So remember the fact that we do experience data loss when we are typecasting from a data type that has more support to a data type that has less support. So floats intrinsically within Python have more numerical support. It supports more types of numbers than an integer. And since integers can't have these little numbers at the end after the decimal point, we're sacrificing this data. We're sacrificing the 0.14 in order to convert it to an int. So just be mindful of that whenever you are typecasting within numerical application, because here I get 3 and we have some kind of data loss. But if you are trying to have an application that rounds down or tries to get rid of this data, then this could come in handy. Python also allows us to easily know a data type of a specific variable by using the type command. This is really helpful because, like I mentioned before, Python has implicit data types, meaning that it will not, when you write the code, you will not state what data type you want the variable to be. So sometimes you might get confused which data type a variable might have. So in order to get rid of this confusion, you can print out the type of data type of a specific variable by wrapping the variable name around the type keyword using parentheses, and here we get float and int. This leads us into the first exercise of this lesson, where you will be converting these two variables into the respective desired output variables. So this one you will need to convert to an int, and this one you will need to convert into a float. Give it a shot. Okay, so in order to do this, I'm going to create a new code cell, and let's start off with view remaining. So I'm going to typecast it, and I'm going to set it equal to the int version of itself. So we're going to use the int keyword, which is the desired data type, and within parentheses, I'm going to put in the variable name. So I'm going to reassign it. This is reassigning it to the int version of your remaining. And for oxygen levels, I'm going to reassign it as well. I'm going to set it equal to a float. And inside of parentheses, we're going to put in oxygen levels. So this will effectively typecast everything to our desired output data types. And then now it wants us to print out the output so it looks like the following. So we can easily do this by using the print command. And let's do fuel remaining. And I'm going to put this comma here in a space, comma, fuel underscore remaining, and then print oxygen levels, comma, space, and then oxygen levels. Now, if I run all of this code, shift return, shift return, shift return, you can see that we have fuel remaining of 33 and 21.0. It wants us to have this like a little unit at the end of it, and I forgot that putting the comma puts a space in between, so we can just get rid of the space here. And let's add the units. So this is in liters, and this is in, I think, kilopascals, just a standard pressure. So now we have our desired input of fuel remaining 33 liters and oxygen levels of 21.0 kilopascals. Moving on to ways we can store data in Python. Like I mentioned, there's two ways, arrays and lists. And they have a lot of similarities. Lists are built in, they can store elements of different data types, and they can dynamically grow and shrink in size. While arrays are not built in, they are homogeneous, meaning they can only store elements of the same data type, and they have a fixed size once they are initialized. So here's an example of a list being assigned. And here is an example of an array where I import it using a library. We will get further into this later on. Don't worry if you are confused by this, but I just wanted to include a code snippet about how you would initialize an array in Python. So one core concept you need to understand when you're using a list in Python or an array is indexing. Whenever you are using an array or a list, you're most likely using multiple items, and each item will have its own index, which denotes its position within a list. Let's say you want to get access to the number 2 in the numbers list here. You'll just say numbers, and inside these enclosed brackets, put in the index of the desired element output. So I want to get 2, so I put in 0, and that gives me 2. You can also index out characters from a string via indexing. So I have a variable name called name assigned to John, and let's say I want to get the character H out of this. You can think of this as an array of characters. So J, O, H, N. J would have an index of 0, O would have an index of 1, H would have an index of 2, and N would have an index of 3. So we want H, and that has an index of 2, so just put in name, brackets, and the index of the desired character output, which is 2, and that will give us H. And this is all the code from the examples I listed above. And if I print it out, you can see we get 2 and H. Let's say I wanted to get a range of outputs. This is where slicing comes in. Here I have a list of numbers initialized, and let's say I want to get a specific slice of 4 and 6 as an output. So here we initialize a variable name called slice numbers, and we set it equal to the output of the slice operation. And here we're slicing numbers, and we denote where to begin in the slice by the start index. So I want to start at 4, and this is inclusive, so this will include 4, and then a comma, and then where I want to end, and this is exclusive. So let's say I want it to end here. I'll have to end it at 8, and 8 has an index of 3. And now if I print out slice numbers, this will give me the output of the slice, which is 4, 6. You can also use shorthand notations in order to avoid redundancy. So let's say I want to get an output of 2 and 4, just beginning from the start of the array to up to 4. I can do so by putting 0, which denotes the start of the array, up to 2. But you can also make this shorter by using a comma instead and omitting the 0 whenever you want anything from the start of the array, and effectively these two will return the same output, 2, 4, 2, 4. You can also do this the other way around. So let's say I just want everything from the index of 1 to the end of the array. I just put 1 and then comma, and that will give me anything up to the end of the array. So give me 4, 6, 8, 10. You can also do this in the backward direction. So you can slice in the backward direction, where -1 represents the last element, and -2 represents the second to last element, and so forth. So let's say I wanted to get 6 and 8, which are here. I would denote it by using -3 and -1, because -3 is a third to last element. So 6 starts here, and it's the third to last element. And we want it to end at 8, which is the second to last element, but this is exclusive, so it will exclude 10, and that will return 6, 8. You can also have things known as two-dimensional arrays. Two-dimensional arrays are arrays or lists inside of lists. So for example, I have a variable name here, 2D array, and you can see this is the outermost list, and then inside of it I have elements that are lists themselves, so that effectively creates a two-dimensional array. And this is really useful when you're dealing with like two-dimensional things such as pixels, and you just want to denote a specific location. The way you can specify it is by putting in the row and the column index. So let's say I want to get the value 2. Well, we know from here that this has a row of 0, because it goes 0, 1, 2. 0 being the topmost row. This is the second one, so it has an index of 1. Last one, 3. So it has a row of index 0 and a column of index 1, because it goes 0, 1, 2. So I would put in the row index and then the column index, and I'll store it within the value 1 variable. And then let's say I want to get the number 9. We know that this has a row of 0, 1, 2, has a row of 2, and then a column of, this is 0, this is 1, 2. So this has row index 2, column index 2. So I just specify that, and then I print out each of these values, and that gives us what we want. Let's say you want to change arrays and lists. In order to modify a value within an array and assign it to another item, you need to specify the index and reassign it. So let's say I have a list here of numbers 1, 2, 3, 4, and 5, and I want to change the value of 2 to be something different. So I would do this by specifying the name of the list or the array, so numbers, and within the brackets I specify the index of the element I want to change. We know that 2 has an index of 0, this is 1, so if it has an index of 1, so I put 1 in there, and then I assign it to the value I want it to have. So I reassign it to 7, and you can see if I print it out, it will have the newly assigned value of 7. You can also delete items from an array, like the following, by using the del keyword. So here I reassign the numbers to have an array value of 1, 2, 3, 4, and 5. And let's say I want to delete the third element, number 3, and we know that 3 has an index of 2. So I'll put the del keyword here, and inside parentheses I put in numbers and the index of the position I want, of the element I want to delete. So I want to delete 3, so I put in index 2. And now if I reprint it, it reprints numbers with 3 deleted. You can also add items to the end of an array, which is called appending items, like the following. So I have a list of numbers here, 1, 2, 3, 4, and 5. And let's say I want to add 6 to the end of it. I would specify the name of numbers here, put a period, dot, and put the keyword append, and then close within parentheses the value you want to add. So I want to add the value 6, and I reprint it. You can see that it has 6 added to the end of it. You can keep going on with this. So let's say I want to add 7. I'll just use the same line, put in 7, reprint it, and you can see 1, 2, 3, 4, 5, 6, 7. Let's say you want to reflect or reverse the order of the elements within a list. So instead of 1, 2, 3, 4, and 5, I want to show 5, 4, 3, 2, 1. You can do this by using this. Here I have an example of a piece of code that reverses the direction of an array. So for example, I have a numbers array here set to 1, 2, 3, 4, 5. And the reflected variable here is assigned to the reversed direction. And the way you reverse it is within the numbers by specifying numbers. And inside these brackets, you put the special combination of 2 colons and a negative sign, and that will reverse the direction. So this will give us an output of 5, 4, 3, 2, 1 when we print it out. This leads us into the second exercise. Here you are given a hard-coded values list, and your task is to run the following steps in sequential order. And the output should look like this. So give it a shot. To do this, I'm going to create a new cell here and make sure I run this cell. And the first thing we need to do is delete the last item. To do this, we're going to use the del keyword, and within parentheses, I'm going to specify the values list, and I'm going to use a negative index in order to get the last item. And we know to get the last item, we specify -1. So that's the first step. The second step is to set the second element to the number 8, so values, and the index of the second element is 1, because we start at 0, and the second element would be 1, so we set it equal to the number 8. Then we need to reverse the direction of the list. So I'm going to go values, values, and we put the special combination of 2 colons and a -1, and that will flip it and reassign it to the values array. And then now we need to append the numbers 5 and 9, so we do values.append 5, values.append 9. And that pretty much does it. So we're going to print it out, and we should get the output specified above of 438159. Perfect. So the last thing we're going to do in this lesson is to get the user input. To do this, we're going to be using the input command, and what the input command effectively allows you to do is to interactively receive data from a user. So let's say you have a program and you want to get specific numbers from the user themselves so they can use your application. The user input would be a great application or use case within this application. So here's a bit of code I wrote, and what this does is it asks the user for their favorite color and saves it into the fav color variable, and then it prints it out. So if I run this code, it'll say, what is your favorite color? I will answer blue, and you can see it will print out favorite color blue. We can keep running this code, and let's say I say yellow this time. It will give me an output of favorite color, yellow. So the way you do this is you just specify the input keyword, and within parentheses, just prompt the user what they want using text, and save it into a variable, and then use that variable wherever you want in your code. In the last exercise, you will be creating your own rocket engine performance calculator. You are an aerospace engineer, and you're tasked to create a computer program to calculate the engine performance of a rocket engine. and the calculator has to meet the objective specifications listed below. These are the equations you'll be needing for this problem. The specific impulse is equal to the thrust divided by the mass flow rate times 9.81, which is the acceleration of gravity, and then the exhaust velocity is equal to the specific impulse times 9.81. So give it a shot. All right, so let me specify another code cell, and firstly I'm going to begin by asking the user for the thrust and mass flow rate of the propellant. And the way we're going to be doing this is, let's create a thrust variable, and I'm going to set it equal to the input, and I'm going to ask for the thrust of the engine, so thrust of the engine. And one problem we are going to encounter is, again, with typecasting. When we input the user, when we ask them this, the output of an input, so if I run this again, whatever I put in here, let's say I put in a number, which is, in this case, we want a number, this will be interpreted as a string. It will be interpreted as text, always. And in this case, we don't want thrust to have a string value. This is also listed within the objective. We want to typecast it as a float. We don't want it to be text. So what we will have to do is we need to wrap this around the float keyword. And now it will take whatever input is placed in here and it will typecast it as a float. Moving on, we will get the mass flow rate. And let's do the same thing where we wrap it into a float because we want it to be interpreted as a float. And then let's ask for the mass flow rate. Enter mass flow rate. And save it into the mass flow rate variable name. Next is to calculate the specific velocity, the specific impulse of the rocket. So we can do specific underscore impulse, and that is equal to thrust. We have thrust here divided by, in parentheses, because we want to follow order of operations. So whatever operation we put in here will be run first, and then we run the division. So parentheses, mass flow rate, which is in this variable name, times 9.81. And then exhaust velocity. So exhaust underscore velocity, and set it equal to specific impulse times 9. And now what we want to do is print everything out. So I'm going to save this. And here I'm going to print out the values as strings. So I'm going to do specific impulse plus specific impulse, and then again for the exhaust velocity. And when I run this, I'm going to get an error. Let me terminate that really quickly. So when I run this, let's say I put in an arbitrary thrust like 30, a mass flow rate of 10. I'm going to get a typecast error again. The reason is because here we have a float data type and here we have a string data type. So we need to typecast this one more time into a string. So I'm going to put the str keyword, and same situation here. Wrap it in the str keyword. And when we run it again, we should get a specific impulse calculation alongside an exhaust velocity calculation. In this third lesson, we'll be talking about a concept called control structures. And you can think of control structures as the flow of execution within your program. So depicted below, I have a picture of a control structure, which is comprised of control statements, conditionals, and iteration. So you can see each of the steps here go to next step, and within this control structure, we have something called conditionals, and whenever you have a conditional, it will split off into two different states, depending on whether the value is true or false. So in this case, if it is true, it will go to step 4 and then repeat the entire program. If it is false, it will just go to step 4 and then terminate the program because there's no step afterwards. So this process of going to step 4 and then repeating back to the beginning is called iteration. This allows you to run the program multiple times, depending on a specific feature or function. In the process of repeating a program, repeating steps within the program is referred to as iteration. And you can think of each of these different steps as their own control statements. So within our Jupyter Notebook for this lesson, I just give a little background on what control structures are specifically within Python. And within programming, they allow you to control the flow of execution in your code. And they determine which states are executed under certain conditions or how many times a statement is executed. And there are three main types of control structures. There are loops, conditionals, and control statements. Loops are used to execute a block of code repeatedly. Conditionals are used to execute different blocks of code based on whether a condition is true or false. And control statements are used to control the flow of execution within loops and conditional statements. So let's begin with loops. Loops in Python are used to execute a block of code repeatedly, and there are two main types of loops, for loops and while loops. For loops are used to iterate over a sequence. This could be lists, arrays, strings, or any kind of iterable object. And they will execute a piece of code one time for each item within that iterable object. So for example, here I have a list of different planet names, Earth, Mars, Venus, and Mercury. And here I'm using a for loop. In order to do so, you use the for keyword. You specify the name of the item you want to loop and the list or the iterable object you're iterating over. So in this case, I want to print out each of the names of the planets inside of this list. So I say for planet in planets, I print the name of the planet. So if I run this code, it will still print out each of the different planets in this planets list. Another way of looping is while loops, and they will execute a block of code as long as a specific condition is true. So while loops inherently use conditionals in order to operate. So let's say I have a variable name called I, which is set to 1, and I want to run this piece of code that prints out the value of I whenever I is less than or equal to 10. And each time it prints out the value of I, it will add 1 to it. So what this does, if I return the result, is it will go all the way from 1 and it will count up to 10. And as soon as I is equal to 11, it will not be less than or equal to 10, meaning this will evaluate to false, and it will terminate the while loop. So whenever this conditional statement here is true, it will run the blocks of code in between, which is specified using an indent. So whenever you're using a while or a for loop, you need to make sure all of the lines of code are indented by highlighting it and pressing tab. And this will make sure that this is within the loop itself. And whenever this evaluates to false, the code in between will stop running. This leads us into the topic of conditionals. Conditionals allow you to execute different blocks of code based on whether a condition is true or false. There are three main types of conditional statements: if statements, elif statements, and else statements. If statements are used to execute a block of code only if a specific condition is true. So for example, this code will only print out text if the number is greater than 10. So I have a variable called number, which is set to 20. And this conditional here, this if statement, uses the if keyword. And after the if keyword, you put a space. And here, you specify the condition that you want to be true. And if it is true, it will run the code underneath it. So here it's checking if the number is greater than 10. And then if it is greater than 10, it will print out the number is larger than 10. So here I have a number set to 20. So it is greater than 10, which will print out the number is larger than 10. But let's say I set this something to equal to 5. It will not print anything out because here 5 will be less than 10. This will be false, so it will not run the code underneath the if conditional. Elif statements are a different type of conditional that are used to check additional conditions after a if statement is added. So let's say I have a number variable here called set to 0, and this conditional, this if statement checks for if the number is greater than 10. And let's say I wanted to do another check. I wanted to add another conditional that checks if the number is 2. If I want it to be the same, if you want to add another condition to the same variable, then you would use an elif statement. So it will first check if the number is greater than 10, and then if this is not true, it will go to this one, and it'll check if the number is equal to 2. So right now, let's say I set this to 11, it will print out the number is larger than 10. Let's say I set it equal to 2, this will be false because 2 is less than 10, it's not greater than 10. So it will revert to this conditional, and it will check if the number is 2. It is 2, so it will print out the number is 2. You have something else like 3, this won't run anything. Since this matches the second conditional, it will print something out. Finally, we have else statements. Else statements are used to execute a block of code if none of the if or elif statements before it evaluate to true. So let's say I have the same two conditionals I specified up here, but let's say I have a number that doesn't match both of the criteria I specified. So this number 6 is not greater than 10, and it does not equal 2. But what if I want it to be like, I don't want to create another elif statement that checks if the number is 3, 4, 5, 6, anything less than 10 and not equal to 2. So I create a default case in this using this elif statement that will evaluate to any number that is not greater than 10 and not equal to 2. So for example, I have 6, which is less than 10 and not equal to 2. And you can see here that it will print out what's under the else statement, which is numbers smaller than 10 and is not 2. And this would work for any other number that fits that case. So like 5, which is less than 10 and not equal to 2, it will also print out the same thing. This leads us into the first exercise of this lesson. And you are an astronomer recruited to analyze the luminosity of celestial objects in the sky, and you have to follow the specific objectives outlined below. And one hint for this exercise is you can iterate over an object, and in this case celestial objects, which is specified here as a dictionary, by using the following code. And what this code does is that it loops for over each object inside of this dictionary, like each little celestial object in this case, and then it will print out the key. So print out the name here, separated by a colon, and the value using the 1 index. So it will print out the value. This has an index of 0, and this has an index of 1. Give it a shot and come back to this video when you are done. Okay, so firstly, we are tasked with printing out the names of the celestial bodies using a for loop. This is pretty straightforward because we're pretty much given the code here. So let's follow that same reasoning and print out the names of each of the celestial objects. So I'm going to create another code cell below. I'm going to say for obj, this refers to each object inside the celestial object dictionary. In celestial objects, which is specified here, dot items. This will extract each of the items from this dictionary one by one. And I'm going to put a colon here, and I'm going to press tab because we want this code to be inside of the for loop. And then I'm going to print the name. The name is here within the string, and it has an index of 0. So I'm going to print obj 0. And if I run this code, I need to run this code before it and then run it again. It will print out the names of each of the different objects. Moving on. It asks to initialize an array variable to contain only the luminosities of the solar objects. So let's call this luminosities. And I'm going to set it to an empty array, empty list in the beginning. And now it wants us to contain the luminosities, and the luminosities are these values here. So let's do the same kind of situation where we loop over each of these objects. So I can pretty much copy this code here. And in this case, we're not printing out the name. We want to add the luminosity to this list here. So we can do luminosities. And in order to add something to the end of a list, we use the .append method. And within these parentheses, we specify what we want to add, which is the luminosity value. So we'll just do obj, and we get the luminosity by specifying the index, which is 1. So I'm going to put 1 in there. And then lastly, it wants us to iterate over the luminosities array using a while loop and use a conditional to print out all the celestial bodies within a luminosity of less than 200 solar units. So you can do this by specifying a while loop with an index. So I'm going to create an index variable and set it equal to 0 because we know that all the indices within a list start with 0. And I'm going to create a while condition, and the condition will be index is less than the length of luminosities. So this will effectively loop over every single item within luminosities, and it will check if the luminosity at that specific point. So we can reference the luminosity at that point by using the index variable. And it wants us to check if it is less than 200 solar units. So I'm going to do less than 200. And then inside this conditional, it wants us to, print it out. So print the luminosity value. So this will give me the value of the luminosity at that index. And then lastly, we want to get out of this conditional because we're not in the conditional anymore. We only want to run this if the luminosity is less than 200, but as a general case, we want to make sure that index has 1 added to it, or else this will keep on running forever. So let's run this code first. So we have all the luminosities in this array. And then now if I run it again, this will loop over each of the luminosities. If I create a code cell here and say luminosities, this has all the luminosity values within it. And now here we're just looping over each of the different items within this luminosities list, and we are printing it out if it is less than 200. So this is not less than 200, it won't print. This is less than 200, sorry. So it will print it out. This is greater than 200, it won't print it out. This is less. This is 6 times 10 to the negative 10 to negative 5. So this will be way less than 200. And then we have 100, which is less than 200. And this is greater than 200, obviously. Moving on to control flow statements. These statements change the normal flow of code execution. They include commands like break, continue, and pass, and allow you to exit a loop early, skip certain iterations, or do nothing when a case is met. So let's begin with break statements. Break statements allow you to exit a loop early when a specific condition is met. So for example, I have a for loop here that goes over each planet within this list of planets, and it checks if the planet is equal to Mars, and if it is equal to Mars, it will exit the loop. And if it is not equal to Mars, it will continue and it will print the name of the planet. So what this does is it goes for each item. So it'll first go for Mercury. It'll check if it's equal to Mars. It's not equal to Mars. So print it out and it'll move to the next item. It'll move to Venus, not equal to Mars. So print it out. Move to the next item. Earth, not equal to Mars. So print it out. Move to the next item. Finally, it's Mars. It will break out of the loop, meaning the loop is terminated. And then since this print statement comes after the conditional, this will not run, and it will not get to Jupiter because the loop is terminated. So if I run this code, all it will print out is Mercury, Venus, and Earth. Moving on to continue statements. Continue statements allow you to skip an item and not just terminate a condition. So let's say I wanted to include Jupiter. I just didn't want to include Mars. So in this case, I would use a continue statement because then it'll print out Mercury, Venus, Earth. It sees that this is Mars, so it'll continue, and it will just skip over this code because this code anything that comes after the continue will be skipped. So Mars won't be printed out, but Jupiter will. And then finally, we have pass statements. A pass statement is a null operation, so it means it does nothing when executed. And this is typically used as a placeholder in places where Python syntax requires a statement, but no action is desired. So let's say I have Mercury, and I just wanted to do nothing when it hits Mercury. It'll pass through this condition here, so it'll just do nothing, but it won't skip the rest of the code. So it'll still print the name of Mercury out, it just does nothing. So let's say you want a conditional for it, and you just want it to do nothing, you'll use pass in this case. So if I run this, it will say Mercury, Venus, it'll go to Earth, it'll say our home, print it out, and then print out Mars and print out Jupiter. This leads us into the final exercise of this lesson, and you're tasked to create a simple Python program that will simulate a space mission control operation, and the program should incorporate various control structures to manage different aspects of the mission. And here below you have some hard-coded variables, so make sure to utilize that during this exercise. Give it a shot and come back to this video when you are done. Okay, so in order to do this, let's read over what it wants us to do one by one. So it first states to initialize a while loop that runs when the mission time is less than or equal to the mission duration. So this would be pretty simple to do. In this exercise, you are tasked with creating a simple Python program to simulate space mission control operations. program should incorporate various control flow structures to manage different aspects of the mission. And I have hard-coded variables here, so make sure you use that when you tackle this problem. So the first thing I would do is follow this first step, which says initialize a while loop that runs when the mission time is less than or equal to the mission duration. So this is a pretty straightforward while loop because the condition is made really explicit to us. It's saying check if mission time, which is here, is less than or equal to the mission duration. Mission duration is listed up here. And let's put a colon. And within the while loop, decrease the distance to the destination by the distance traveled per hour. So distance to destination minus equal distance traveled per hour, and then within the while loop, decrease the fuel level by the fuel consumption rate. So fuel level minus equals fuel consumption rate. So this will set fuel level equal to itself minus the fuel consumption rate, and distance to destination equal to itself minus the distance traveled per hour. And then it asks us to print out the fuel level, mission time, and the distance to destination. So print. And in here we say mission time, and let's specify the mission time. Let's do the same thing for remaining fuel. So this will be fuel level. And then distance to destination. And we should also probably specify units here. So I'm going to say this is in hours. Fuel level is in gallons. So I'm going to go here and specify gallons. And distance to destination, I think, is in kilometers. Yeah, kilometers. And now it wants us to break out the while loop if fuel level or distance to destination is less than or equal to 0. So let's do a conditional for that. If fuel level, start with fuel level, is less than or equal to 0, the following, or distance to destination is less than or equal to 0. Here. Then we want it to break it out, meaning it will just terminate everything. And then lastly, it wants us to increment the mission duration by 1. That makes sense. I'm gonna do mission. I think mission time by 1. And then I think we should add something to the end saying we've completed the mission. So I'll add a print statement saying mission complete. And now if I run this, I'll print everything out. And it will have mission complete at the end of it. I want to make like each mission time distinct from each of the other mission times. So I'm going to use a special key combination with a \n. And what this does is that it creates a new line after kilometers. So if I run this again, Oops, let me reinitialize these variables. You'll see that we have an empty line at the end of this line here because we added this little \n to the end of kilometers, making it a little bit more readable. And it says mission complete. Great job. In this lesson, we will be talking about functions and modules and how they're used within Python. So functions, abstractly, you might have heard this if you've taken algebra before, is blocks of reusable code for a specific task. And abstractly, a function is anything that takes in inputs, runs any kind of operation or any kind of task on them, and then gives you one output. So functions can have multiple inputs. It can have one output, it can have 3 inputs, it can have 5 inputs, and it will perform an operation on those inputs in order to give you one output. So for example, I have a function called add here, which takes in the inputs of 3 and 6, performs an operation of addition on them, and then gives you one output of 9. Modules are files containing code that can be reused by other files. And the reason I explain this in tandem with functions are because modules have defined functions inside of them, and each file is referred to as their own module. So in this case, module 1, module 2, module 3 will have independent files, but they can all be used. Functions within those modules can be used within one program. So here I have functions from module 1, a function from module 2, and a function called module 3, all consolidated into a single program. And the reason why modules are used within code is to organize tasks. Let's say you're working for a large organization like NASA that has hundreds of thousands of lines of code. It can get really disorganized if you try to shove it all into one file. So typically these organizations will organize their code base into separate modules, each assigned to a specific task, and consolidate it all into one program by using functions defined in each of the modules. So in Python, the way you define a function is by using a def keyword, short for define, and then you can name your function whatever you want. So in this case, I have a function called greet, and within the parentheses, you specify the inputs of the functions. These inputs are called parameters of a function, and this is what the user will feed into the function in order to get the output. And then using a tab will denote the code that goes inside the function. And in this case, I have a piece of code that prints out hello, comma, the name of the person inside greet. So here I have greet on Bob and then greet with Alice embedded inside of it. And now if I run it, it'll say hello Bob and hello Alice. This is called invoking a function, where you use the function and feed in the input in order to get the output. Functions can also take in multiple inputs. However, functions can only return one output always. There will never be a time you can return multiple outputs. It's only one output. And in order to return an output, you will use the return keyword. And in this case, I'm returning the addition of the input A plus the input B. And here I invoke the function by calling add, and I put in the 2 inputs I want it to be added together. I put in 5, comma, 3, and then I save it to the result variable. And then I print it out to the console with addition here, and then I typecast the result to a string and then print it all out. So in this case, when I run the code, it will say addition 8. And we can modify this. So let's say I want to do 3 plus 7, then it will do 10. This leads us to the first exercise. You're tasked with creating a calculated program with the following specifications, and you need to utilize the variables of A and B for testing. Give it a shot. Okay, so in this task, we are given the objective of first creating a function called add that takes in 2 numbers and returns the sum. So this is pretty straightforward because we're pretty much doing the same thing here. So let's call it, let's use the keyword def add. We're going to take in two inputs. I'm going to call them A and B. You can call it anything you want. You can call it like C and D, but for simplicity, I'll just call it AB, colon, and then return A plus B. And then let's do the same thing, but for subtract. So def, name of the function, subtract, inputs. I'm going to call the inputs A and B, colon, and then return. In this case, we're subtracting, so we're going to do A minus B. And then divide, so def divide A comma B. And we're dividing, so we're going to return A slash, which is shorthand for division, B. And then def multiply A comma B. And then we're going to return A, this asterisk sign, which is multiplication, and B. And now we have all the functions we need for our code. So now let me create another code block. And now it wants us to create test values for all the functions and then print them out. And then utilize variables A and B for testing. So let's print out the outputs of every single operation. So let's print out add. And we're going to feed in these variables here. So AB, AB, and let's do the same thing for everything else. We're going to print out the output of subtract, B, print, divide, and then print multiply. So now if I run this all, I need to hard code these variables, make sure these are defined, then run it again. You can see the outputs here. We have 4 plus 5, which is 9. We have 4 minus 5, which is -1. 4 divided by 5 is 0.8. And 4 times 5 is 20. Moving on to modules. Modules, again, are files that contain Python code. And this is used mainly for organization, so we can reuse chunks of code and makes the program a lot easier to manage. So one example of a very popular module in Python is the math module, and it gives us mathematical operation support without having to write all the code from scratch. So without this math module, we'd probably have to rewrite a lot of mathematical functions, especially for technical applications that require a lot of math-intensive tasks. So in order to import a module, you just use the import keyword followed by the name of the module. So in this case, I use import, and then I specify the name of the module, which is math. And you can access functions within a module by using dot notation. Dot notation is when you specify the name of the module, and then you put a dot, and then the name of the function itself, sqrt, and then you feed in the input. So in this case, sqrt stands for square root, so we're getting the square root of 25. And all this code for the square root function is embedded within the math module. So there's an entire file dedicated to this stuff with a bunch of mathematical operation support. So now if I import this and run this, I should get 5. You can also import functions within a module using the import keyword. So here we specify from the name of the module, math, and then we type an import, and then we specify the function name we want. So I want the pow function. This stands for power. And now we can use this method or function without dot notation. So in this case, I just print out the output of pow of 5 and 2. So this gets 5 to the power of 2. The 5 to the power of 2 is 5 times 5, which is 25. Run this, and it should give me 20. Let's say you want to import the map module, but you don't want it to have the name. You want it to have a different name. So you can use the as keyword. So in this case, I say import math, and then I put the as keyword, and then the name you want it to have. So I put in the letter M, and then now we can just use the letter M as the name of the module, So in this case, I print out the output of m.square root 25 and m.pal, which gives me 5 and 25 respectively. In this exercise, you are tasked with creating a calculator using the math module that contains the features outlined below. You can use the variables a and b for each function. Okay, so in this exercise, we are first tasked with writing a function called pal, and we know that that's within the math module. So first we need to import the math module. So we can do that by typing in import math. And now we can define each of the different functions. Let's start off with pal. So I'm going to say def pal as my function name. I'm going to take in the inputs of a and b. And then I'm going to return the output of pal from the math module. So I'm going to say math dot, we're going to use dot notation, pal, and then we're going to feed in a and b. So a to the power of b. And let's do ceiling. It takes input a and returns math.ceil. So a, and then it says return math.ceil of a. It only takes in one input. And what this does is that it takes whenever you have, I'm going to use a comment here, a slash, this hashtag refers to a comment, and this allows us to write like things like hello world without it being processed. It's not interpreted as code, it's just notes we can add. So what math.ceil does is it takes in, let's say, a number with decimal points, like 5.6, and it will round up. So usually in mathematics, if you have something like 5.5, it will round up, or anything below will round down. This is just a clear rule, just to round up. So let's say I have an example like 5.2, it will always round up. So this will become 6. 5.1 will also become 6. Same for like 5.7, 5.8, 0.9, it will always round up. Floor is the opposite. So I'm going to define floor. You can input a and return using dot notation math.floor of a. And this returns the opposite, where you have something like 5.8, it will always round down to like 5. And then write a function called factorial, which takes an input a and returns math.factorial of a. And what factorial does is, you might have seen this before, it's usually written like this in math. And what it does is that it goes from this number here all the way down to 1 and multiplies each of the descending numbers. So what this will do is it will do 3 times 2 times 1, and it will output, let's say, 6. Let's use another example. Something like 4 would output 4 times 3 times 2 times 1, which would be 24. All right, so now we have all of our functions written. I'm going to make sure that it is run, and let's create another code cell. And now let's print out the output of each of the different functions. So pal, let's feed in the A, B inputs for testing. So I'll put in A, B, and then let's do ceiling. This only takes in one input, so I'm going to put in A. Floor, I'm going to put in A as well, and then print factorial. Okay. So now if I run this, I get 1024 for the first output. Let's use something smaller, like 3, to make this a little bit simpler. So I have 243, which is 3 to the 5th power. I have ceiling. This makes sense because this will round up, and 3 is 3. Floor. and factorial. 6 makes sense because it's 3 times 2 times 1. Let me change this to a decimal point to make the ceiling and the floor a little bit more apparent. So let me do this, convert the A to 3.1. Now if I run this again, oh, we can comment out this code for now. If I run this again, you can see ceiling returns 4 because it is rounding up, and floor will return 3 because it is rounding down. Great job. In this lesson, we will be covering files and data input-output systems. At some point within your journey of programming in Python, you'll need to leverage files in order to get data for your program. Examples of scenarios where file handling and data from files becomes handy is instances like reading sensor data from spacecraft instruments, parsing telemetry logs, and accessing configuration files for simulation parameters. So firstly, we'll begin with opening and modifying files. Python has built-in support for accessing and altering files. You can open a file using the open command. So here I have a file variable and I have it set equal to the sample.txt file, and the W here stands for write, and it allows us to write to a file. So what this does is it opens a file called sample.txt, which is a standard text file, and it allows us to write to it. You can also use other things like R, which stands for read only, and A, which stands for appending only, meaning that you can't like rewrite anything, you can only add to it. But we want write permission, so I'm going to put W and write and execute it. And now we can apply this to actually writing text. So now let's say I want to write the words blast off to the sample.txt. I will first access the file and give me write permissions by specifying W. And then you can use the dot notation with the write method and put in the input of the text you want to write. So first I'm going to write blast, and second I'm going to write off. And then after you're done writing, you need to close the file. So I specify file and then use the close method here. So now if I execute this and go back to my Jupyter Notebook display, you can see that there was a txt file that was created. And if I open it up, you can see the words blast off have been written. When you are dealing with long-form datasets and you want to iterate over data, you can write data using loops. So an example here are 3 hard-coded arrays of planet names, surface gravity for each of the planets, and surface temperatures in Kelvin for each of the planets. So Mercury has a surface gravity of 0.38 Gs and a surface temperature of 440 Kelvin, and so forth. So let's say I want to write these different data values into a file called planets.txt. So first I access the file and save it to the file variable by using the open method. And inside the open method, I specify the name. I want it to be saved into planets.txt with write permissions granted. Now I iterate over each of the different values using a for loop. So I say for I in range the length of the planet names. So this will iterate over each of the planets. And for each of the planets, it will write to the file the name of the planet, its associated surface gravity, by accessing the index of the surface gravity, because I will be a number, because range will give you each of the numbers up to the length of planet name. So it goes 0, 1, 2, 3, 4, 5. So this will access the surface gravity and then surface temperature by using the surface temperature array here. Once it's done writing each of the planet data, it will close the file. So if I run this and open up here and open up the planets.txt file that was just generated, you can see that it will list out all the details for each of the planets. So first it goes Mercury, surface gravity, and then the surface temperature for Mercury, all the way up to Neptune. For this first exercise, you are a planetary scientist tasked with saving orbital details about planets into a file for later use. You need to initialize a text file named orbital details and iterate all the planets here alongside their details such as orbital periods and axial tilts, and save it into the file. Okay, so for this example, I'm going to first initialize the file. So file, and then we use the open keyword, and we specify the name of the file we want to save to, and it says orbital details .txt since we want to save it into a text file. And I'm going to put comma and specify it with write permissions granted. And now we can iterate over each of the planets. So I say for I in range, and then we put the length of the planet, the planet names. So this will loop over each of the planets. And then inside there, we want to write the file. So we say file.write. And first, let's write the name of the planet. So we'll do planet names, and then the index here. And then let's write orbital periods. So I'll say period space, and we're going to typecast this into a string since currently is a float, and then specify the index. And let's do the same thing for the axial tilt. And then wrap it around a string, specify the name, and then put an I. And then finally, we want to end things off with file.close. Close the file. So now if I write this and go here, we should see that orbital details.txt was generated. And if I expand it, you can see that we have all of this saved into a text file. Let's format it a little bit so it looks a little bit more clean. So here, I can add little spaces, so I can add a space at the end of this, or let's say we can add a comma, and then we can add a colon here, a comma there, and then an escape here to create a new line. Now if I run this and refresh this, you can see that it gives us each of the planet names with their own line, and it's all properly formatted. You can also work with txt files by using the load_txt command. So let's suppose we have a text file called spacecraft.txt containing the 3 columns mass, fuel, and force. So I can open up spacecraft.txt and to show you. Okay, so we have spacecraft. So each of the rows define as spacecraft, and we have 3 columns. And the columns are mass, fuel, and force. You can work with these kinds of values by using the code below. So in order to use the load_txt command, we need to import a module called Numpy, and I'm going to import it with the name np. And now we can load in the data from load.txt of spacecraft.txt. So if I just print out this without all this extraneous code, print data, it'll print out all of these, and it will represent each row with an array. You can cross-reference here and see each of these will be an array. And then it is all stored within an array. So we have a two-dimensional array, an array of arrays. And we will transpose this data. We're using another method within the Numpy module called transpose. And what this does is that it switches the columns and the rows. So let's print that out to see what it looks like. And you can see here that it pretty much flipped the columns and the rows. So you can see here 3.2 was where it was here. So you can think of it as rotating the entire thing, or like flipping the entire thing, where everything moves. Flipping it clockwise, like 90 degrees, I think. That'll switch everything. So it will switch the rows and the columns. So the data will now look like this, where we have, let's say, like, the mass was 5, 12.1, and 7.3 respectively, and fuel would have been 3.2, 4.7. We just have them all within rows. So this will be the mass row, this will be the fuel row, this will be the force row. It just makes things easier to work with because now we can use indices to reference each of the values. So now if I just wanted to say I wanted to get the masses of all the spacecraft, I don't have to do any finessing with the data. I can just straight up reference the index and get the masses, reference the index, get the fuel, reference the index, get the force. As before, it would have been a lot more trickier because you would have had to get like specific coordinate, like the column row value, and have done like something really funky where you use two things specifying the row and the column, but now it's all within their own consolidated rows. So let's say I print out mass, it will print out the masses of spacecraft 1, spacecraft 2, and spacecraft 3 respectively. There's just a cool thing to know when you are working with large data sets. And it will be a cool leeway into the Numpy module, which we'll be diving into soon. You can also work with very specific file formats. So within Aerospace, you're going to be dealing with very specialized file formats. And one example of such is the FITS file format. And the FITS file format is used to store astronomical images. And let's say an image like this would be stored within a FITS file. It stands for Flexible Image Transport System. And it is a standard format for astronomical data. And under the hood, the data, the binary that's used to store information about this image is structured like the following. It is segmented into things like called HDUs. HDU stands for Header Data Units. And there's a primary header data unit, followed by extension header data units, like the following. And the primary header data unit includes primary header information alongside associated binary data. So header information will be things like metadata, things that describe the image. So like the image resolution, the device that was used to create the image, things like that will be considered within the primary HDU. Extension HDUs are just subsequent data describing the image itself, and they have their own binary data associated with it too. So in order to work with the FITS file, we need to use the astropy.io module and import the FITS method. So if I run this, this will open the FITS file, fits.open, example.fits. It will access the header HDU, or the primary HDU, by referencing index of 0, because we know this goes at the very beginning, therefore it has an index of 0. And this will get the data array alongside the header information, and if I print it out, you can see that it will print out all the data and the header information. And if you look just at the header, You can see this stores metadata, information about the data, such as the telescope used to get the information, the array data type, the instrument, and the object being studied. One thing to note is if you get an issue when you're running these commands with the import statements, you have to write pip install bits. Pip install the name of the module. So if you get an error running any of this code, just make sure you do a pip install and then run this code cell. And that's it for this lesson. For this project, we'll be creating an aircraft performance calculator. The objectives of this project is to create a Python program to calculate the performance metrics based on user input, incorporate formulas for range, endurance, fuel consumption, and climb, allow users to specify aircraft characteristics like weight, wing area, and engine thrust, and provide graphical outputs and analysis of performance trade-offs. So we need to cover some conceptual knowledge first before we build our own aircraft performance calculator. And this includes the following: basic aerodynamics, performance parameters, propulsion systems, atmospheric conditions, and performance calculations. So let's begin by covering basic aerodynamics. Aerodynamics is the study of how things fly through the air. And the core of this is to understand how airflow works over surfaces and how that affects engineering characteristics like speed, lift, drag resistance, and stability. So let's go over the 4 fundamental forces of flight. Whenever you are dealing with an aircraft or spacecraft, you're going to be dealing with the 4 forces of lift, weight, thrust, and drag. And the interplay of these forces determine the motion of an object as it flies. So here we have weight, which is dragging down the aircraft. We have lift that counteracts weight. We have thrust, and then we have drag that counteracts thrust. And a little bit more in depth for these 4 forces, weight is created by gravity and the mass of the object. Lift opposes gravity. Thrust is produced by the engines or the propulsion system, and it propels the aircraft through the air. Drag counteracts this and creates aerodynamic resistance, and it opposes thrust. So in the context of airplanes, how do they create lift? Airplanes have these things called airfoils on their, which is like a teardrop shaped that their wings are formed into. And how this creates lift is when you have airflow over the top, the air over this wing will move faster, and it will create a pressure difference between the top and the bottom. Since the air over the wing moves faster than the air below the wing, this is called Bernoulli's principle, it will create lower pressure here and higher pressure here. And the difference between the pressure from the top and the bottom of the airfoil creates lift and allows the aircraft to fly. One more thing to understand is principal axes. Aircraft have intrinsic characteristics that's determined on their orientation called attitude. And attitude describes the orientation along the 3 dimensions centered at the center of gravity. So let's say the center of gravity. So let's say if I were to put like a piece of like a stick there, and I were to try to balance this aircraft, it would perfectly stay still on that stick at that point if I were to place it at that point. But if I were to put it, say, like up here, it would probably veer that way. And if I were to place it like here, it would probably plop forward. But here is like the perfect spot where it can balance on something. And from this originating point of the center of gravity, we have 3-dimensional axes. We have the yaw axis going down the z-axis, the roll axis, and the pitch axis. And rotation about this axis is called pitch. Rotation about this axis is called roll. Rotation about this axis is called yaw. Yaw is like a basic side-to-side motion. And it will it's probably when you want to change direction, like if you want to go left or if you want to go right, the aircraft will change its yaw. Pitch is an up and down motion. So if you want to go down and descend, you'll change the pitch. Go up, change the pitch to go upward. And then roll is an up and down motion of the wings, and it is perpendicular to the two other axes. This comes in handy for calculating aircraft performance, which are various measurements and characteristics that describe how an aircraft performs in flight. So parameters include and are not limited to the speed, which is how fast the aircraft is moving, altitude, which is the distance above a reference point, and it's usually sea level or ground level. We have range, which is the maximum distance an aircraft can travel without refueling. Endurance, the amount of time an aircraft can remain in flight with a given fuel level. Rate of climb is how quickly an aircraft can ascend vertically. Ceiling is the maximum altitude which the aircraft can maintain a specified rate of climb. The payload is the total weight of the passengers, cargo, and any equipment that an aircraft is carrying. And then we have takeoff and landing performance, which is the takeoff distance, landing distance, and minimum runway length required for safe operations. Moving into propulsion systems, propulsion refers to the process of pushing an object forward by producing thrust. And on an aircraft, thrust is generated by accelerating a liquid. And the liquid is air. And air is, yes, indeed, considered a fluid in order to create a force. This operates on Newton's third law, which states that propulsion on an aircraft is equal to the propulsion of equal to the force produced in the opposite direction. And this is true because when air is accelerated by the engine on an aircraft, the reaction to this acceleration produces a force on the engine itself. And this allows us to generate thrust. Same concept also applies for propeller aircraft. Let's say you have a propeller aircraft, and whenever the propeller spins, it has angled blades on its propellers, which create a pressure difference between the front and the back surfaces as they move through the air. And this pressure difference results in the air being accelerated backward. And since the propeller accelerates air backward, there must be an equal and opposite direction due to Newton's third law, and that will push the propeller forward. Engines work a little bit differently. In an aircraft, the engine produces the force by expelling a gas called the exhaust backward, and because this is Newton's third law, the action of expelling a gas backward creates an equal and opposite reaction force, which in turn pushes the aircraft forward. This works the same for a rocket. Instead, you have some kind of fuel, and fuel out of the nozzle of the rocket generates a backward force, while the rocket moves forward due to the equal and opposite reaction force. Atmospheric conditions is also helpful when we are calculating a performance of an aircraft. And these include parameters such as air density, temperature, pressure, humidity that all affect how the engine works and how the aircraft can produce thrust. This is because when an aircraft tries to produce thrust, it relies on air molecules. And let's say something changes the composition of the air molecules. This will change the performance of the aircraft. So air temperature is a huge factor because it affects air density, with warmer air being less dense and colder air being more dense. And in colder temperatures, air molecules are closely together, and this leads to higher air density. On the other hand, in warm temperatures, air molecules are farther apart, resulting in lower air density. with pressure, pressure decreases with altitude, and as altitude goes higher, there will be lower pressure, meaning that there are going to be fewer air molecules available for propulsion systems to work with, which results in less thrust. Humidity is the amount of water vapor in the air, and this may affect engine performance because moist air is less dense than dry air, which can slightly decrease engine efficiency. Wind speed and direction can also impact aircraft performance during takeoff, landing, and flight. Headwinds can increase airspeed, improving engine performance and reducing takeoff and landing distances. Tailwinds, on the other hand, tailwinds can increase airspeed and then reduce takeoff and landing distances. And then we have tailwind, which can increase airspeed, but may require longer runway lengths for takeoff and landing. For turbulence, this can be caused by factors such as wind shear and convective currents, which can affect the stability and efficiency of propulsion systems. So now moving on to our calculations. Some things you will need to calculate include the weight and balance, the total weight, which is calculated by summing up the operating empty weight, the payload weight, and the fuel weight, the center of gravity, which is a pretty robust calculation, taking into account the distances of specific objects and their masses from a datum point. And the product of this is called the moment. So we take the total moment and we divide it by the total weight. We have the moment, which is calculated by taking the weight and the distance of the weight from a datum point. So let's say here we have a data point at this yellow dot, which is the center of gravity. We take in the distance of the object, so in this case it would be the reference line. And let's say we had something here, we would take the weight of it and then multiply the weight times the distance in order to get the moment. Other equations of motions include lift, drag, weight, acceleration, velocity, and distance. And you can look through each of these calculations yourself in order to figure out the equations. And then we have endurance and range, which are important for computing the distance and capacity of an aircraft. So now let's move on to writing the code for this performance calculator. I highly suggest you try this out for yourself and use the calculations and the functions I referenced here before the objectives in order to help assist with this project. Okay, so it looks like we have predefined variable values here to use for this project alongside a helper function, and this helper function is going to print all the performance data. So given these inputs, it's going to print out everything we need for our performance calculator. So we don't have to worry about creating all the print statements from scratch. This handles it for us. And it looks like this is broken up into 3 steps. And the first step is to write all the performance calculation code. So here we first need to calculate the range. And if we reference the code above, it looks like range is calculated by taking the fuel capacity divided by the fuel consumption rate, and then taking the range in hours and multiplying it by the true airspeed. So let's write that code. So let's do range in hours and set it equal to the fuel capacity. divided by the fuel consumption rate. And then now we can get the range in miles. This will give us the fuel totalage, and then we get the range in miles. And then we multiply it by the true airspeed. Here, and I can get rid of this code here. Here, it says to calculate endurance, and if we scroll up, we are given the endurance is fuel capacity divided by fuel consumption rate. So endurance in hours, we can return that. Endurance in hours is equal to the fuel capacity divided by the fuel consumption rate. And let's make sure to return everything. So let's return this here and return the endurance in hours. Calculate total weight. Total weight is going to be the payload weight plus the fuel weight. So let's return that. Return payload plus fuel weight. Calculate the center of gravity position. So it looks like we reference this. It wants us to get the sum of all the moments using the sum method, and then divide it by the total weight. So let's do that. Let's get the total moment first. I'm going to use the sum method. This gets the sum of all the moments inside of here. And then return the, let's actually save it to a variable. I'm going to call it center of gravity position. And we're going to get the total moment, and we're going to divide it by the total weight. And then let's return it here. Moment, you might recall, is the weight times the distance of the arm. So that's pretty straightforward. You can do return weight times arm. Lift, all these four motions of flight, lift, drag, were defined here. So it looks like lift is 0.5 times CL times rho times velocity squared times S. So I'm going to reference this here and paste it in there. And then let's return drag. Drag, we can do something very similar. It's going to be equal and opposite to lift because of Newton's third law, so it's essentially the same line of code. They still want us to insert it. I'll just copy this into here. Calculate weight. Weight is pretty simple. It's mass times gravity. So I'm going to return mass times g. And then acceleration. Acceleration, if we look here, is thrust minus drag minus weight divided by the total mass. Velocity is velocity plus acceleration times time. And then distance is pretty simple. It's going to be velocity times time. So now we have all of our functions written. Let's move on to the next step, is to pretty print all the values. So in order to pretty print everything, we are going to get all the hard-coded values, and then we're gonna feed it into the pretty print method here, this helper function. So let's save this for later. And first let's get all the values. Oops. First let's get all the values we need for this. So let's begin with range. So range is equal to calculate range. And let's feed in everything. So our range needs fuel capacity, fuel consumption rate, and true airspeed. Fuel capacity and true airspeed. So I can just pretty much, the variable names are the same as the input names. You can see fuel capacity, fuel consumption rate, true airspeed. So I'm going to paste these in here. That will give us our range. For endurance, this is our fuel capacity and fuel consumption rate. Total weight is the payload and the fuel weight. Let's see. Yeah, you can see the payload and the fuel weight share the same parameter names, so we can paste it. So we can say total weight. Let's move on to the center of gravity position. And that's moment list and total weight, which have the same variable names. Lift is this. We have drag. Weight. Acceleration. Velocity. And distance. And now we have all these hard-coded values in place. We can feed it into the pretty print function. So let's do pretty print. And let's feed in each of these values one by one. So first thing it takes in is range, endurance, total weight, CG position. So we can pretty much feed this all in order. So let's do range first, comma, endurance, and so on. And distance. Now if I run this code, whoops, we need to make sure everything is hard-coded. So I'm gonna go here, I'm going to run this, and this, run this, and then now we can run this. Now we can see all of our performance calculations from the calculator. So let's say I want to save all the performance values into a text file. The way I would do this is first we need to use a file command and write to a file using a specific command. So if I look at the inputs here, I see that the name of the file is being passed in. So first, or I think the reference of the file is being passed in. So we can first begin by writing to the file, file.write, and writing the performance calculations. And we want this output to be formatted like the following. very similar to the output here. So let's kind of follow that standard. So I'm going to do file.write and put this to create a new line. And then let's write range file.write. And the way we can do range is by using something called formatting. So effectively we can do something like this. Dot format. And inside this format parentheses, you can put in the variable name. So I can put in range. And what this does is it removes the need to concatenate things. So instead of doing file.write, something like like something like this, which, this isn't the worst thing in the world, but for the sake of simplicity and removing redundancy, this doesn't look the most visually appealing. And if it was another amateur programmer getting into this project, this doesn't look so good, especially if we're repeating it over and over again for each line, kind of like what we're doing in this case. So in order to make things more clear, you can use the format, and wherever we place curly braces inside of this text string block, it will plop in the range variable value. So it'll say range, the value of range in this case is like 3000, so it'll say range 3000 miles. So it'll look exactly like it does here. Let's do the same thing for the rest of the values. So next up we have endurance. We can put in endurance. And then we have total weight. And then we can do center of gravity, CG position. Now let's change the units of these. So endurance is hours, total weight is pounds, and then we have center of gravity, which is feet. And let's make sure we have like a new line at the end of these. So I'm going to put in these little characters, make sure we have new line. And then after center of gravity position, we have lift, drag, weight, acceleration. So I'm going to do lift, drag, weight, acceleration, velocity and distance, velocity, distance. And let's put in the proper units and variables for each of these and make sure these have a new line for each of them. And lift has newtons because it's a measurement of force. Drag, weight are the same. Acceleration is meters per second squared. Velocity is meters per second. And then distance is meters. Great, and then now let's put in the respective variable values. So we have lift, we have drag as a parameter name for drag, weight, acceleration, velocity, and distance. Now we have everything written to a file. Let's make sure we can write all the code to, we need to close it too. Let's make sure we write the code to execute this function. So in order to do so, we're going to be doing things a little bit differently. So first you'll need to type with open. And in here we can specify the name of where we want to save our file, or the file name. So aircraft performance analysis.txt. And then we're going to save it as f, so we can refer to the file as f. And then let's invoke the function. So I'm going to pretty much use this name. And let's put in file, put in f. You can also do file equal f as another way of inputting a parameter to a function. And now let's make sure all these names are correct. So range matches range here. Endurance is endurance. Total weight is total weight. Hopefully, yep. Easy position, lift, drag, weight, acceleration, velocity, distance. And the file, which we specified as f. So let's give it a shot and run it. Looks like it ran without errors. So now if I go back here, it should have generated a text file. And now you can see we have all the performance calculations saved into a text file. Great job. This brings us into the first exercise of this lesson, where your task is to develop a flight trajectory planning software for a space mission to Mars. Software requires efficient handling of numerical data for trajectory calculations and simulations. So give it a shot by trying to fulfill all the objectives below. It's okay if you get stuck on this, it's a little bit challenging, but try to figure out whatever you can. Okay, so let's begin by creating a new cell here. And the first thing we need to do is we're going to be using the Numpy package. So we need to make sure we have Numpy installed. So I'm going to do import Numpy as np. Then now we can get started. So first it wants us to create a Numpy array representing time. So let's set time equal to, and it wants us to do seconds from 0 to 100 with a step size of 1. So in order to do this, we're going to need the np.arange method. And if you recall, this will give us a numerical array with from a starting point up to an exclusive ending point with a specific step size. So we'll take the starting point, which is inclusive, the ending point, which we have to be careful about. You can't just put 100 because it's exclusive, so we will need to add 1. And then it wants us to have a step size of 1 second, so I'll do that. The second one is a little bit more challenging. So it says generate a Numpy array representing altitude in meters during the launch phase. The altitude should start at 0 meters and increase linearly with a time at a constant rate of 100 meters per second. So let's break this down. Firstly, let's create an altitude array. And it wants us to start at 0 meters and increase linearly with time. So what stands out to me is increase linearly with time. So it should be the same length, same size as time. So let's begin with a zeros array. And let's have it the same shape, the same length as time. So I'm going to put time.shape, which will return, you can see here, print time.shape 101, because that is 101 in length. And this will give us the same value. So both of these will be same in length. And if we look at what it looks like right now, it's just an array of 101 zeros. So it will be increasing linearly with time, and it should be at a constant rate. So in order to do this, we can do a scalar operation on each of these values. So for each 0, we're going to be adding a specific value, and linear with time at a constant rate of 100 meters per second. So 100 should definitely be in there. And linearly means you need to multiply each of the values in time. So if we look at what time looks like currently, I'm going to comment out this code. It goes 0, 1, 2, 3. So each of these values should just be multiplied by 100. So we're going to do altitude plus equals 100 times time. So we'll take each of these time values and then assign it to the altitude with 100 multiplied. So let's take a peek at what that looks like. You can see here, it's just the same thing, but 100 multiplied to it. So 1 times 100 is 100, 2 times 100 is 200, and so forth. I'm going to get rid of these print statements now. And now it's asking us to calculate the velocity array using the altitude array. So let's specify velocity and assume a constant acceleration due to gravity, 9.81, and during the launch phase. Okay, so we know that gravity, we know that altitude, we know that velocity is the gravitational acceleration times time. And we already have the acceleration of gravity defined here. So I'm going to set it to that. And we're going to do a scalar operation of multiplication and multiply it by time. And this is because we know from here that the gravitational acceleration is meters per second squared, and velocity has units of meters per second, and gravity has 8 units of meters per second squared, and time has units of seconds. So the s squared in the denominator and the s here are going to cancel out, which will give me meters per second. It's okay if you didn't get that. It's a quick mathematical trick you need to do. But the point of this is to know that we're doing a scalar operation on each time value. So for each time value here, we're going to be multiplying 9.81, and that will all be stored within the velocity variable. So if we do this, oh, I forgot to on this, do that, you can see that 1 times 9.81, 2 times 9.81, and so forth. So now let's create an acceleration array using a constant acceleration value of 9.81. So in order to do this, let's just use the np.full method. So I'm going to call it acceleration, and np.full will allow us to specify the name, the length of the array we want. So let's make it all the same shape. So we time dot shape, and we want it to fill it with specific numbers, and that will be the gravity acceleration. So what this will do is it will make an array full of 9.81 values that is 101 in length, because we know that time.shape is 101. So let's see if that is true, and you can see that is true in the output. Now we need to print the shape and data type of each generated NumPy array. So this is pretty straightforward. So let's do this for time, altitude, velocity, and acceleration. So I'm going to first start off with time, shape of time array, and specify time.shape. And then let's do one more, and it will be data type of time array, and this will be .dtype. And let's do this for the rest of the values. So instead of time, this will be altitude, 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 do.shape, altitude.dtime, velocity. We have velocity here, so velocity, velocity, velocity.shape, velocity.dtype, and then finally acceleration. And now we can run it. And we know it's correct because everything has a shape of 101. And the time array is a constant integer value because it's like 0, 1, 2, 3, 4, 5, and so on. So they're all whole numbers. So that'll be int 64, while the rest has decimal points, so they'll be floating point representations. You can also use Numpy for generating random numbers and random arrays. This includes using the random module and then specifying the rand function within that module. So here I have randarray1d, which creates a one-dimensional array of random numbers from 0 and 1. So here when I run this, we get a 5 length array because I specified 5, full of random numbers. We can also do the same thing, but for two-dimensional arrays. So here I have an array of 2 rows and 3 columns, full of random numbers. The NumPy randn function generates random numbers from a standard normal distribution, with the mean being 0 and the standard deviation being 1. So here I have a random one-dimensional array forming a standard normal distribution. And then the same thing here, but for a two-dimensional array with 2 rows and 3 columns. Let's say you want to specify a range where the random integers can fall between. You can use the rand int and specify the starting point and the ending point, which is exclusive, and the size here. So this will generate a one-dimensional array of random integers between 0 and 9, which is 5 in length. And then this one will generate a two-dimensional array of random integers from 0 to 99. So it starts at 0, goes up to 99, and has 2 rows and 3 columns. You can see here every time I run this, it will give me completely random values. You can also compare arrays and perform Boolean operations. So the mp.where function returns the indices of elements in an array that satisfy a given condition. So here we have np.where, and we specify the array we want to do, and then a conditional. So this will return an array of items that follow this conditional statement. So this will return all elements that are greater than 2. So if I run this, it'll give me an array output of 2, 3, and 4. You can also use any in order to get any element in an array that values to true and otherwise false. So here we have an array full of booleans. It goes false, true, and then we run the any method, and what that returns is any element is true. So let's say if any element in here is true, this will be a true output. But if all things here were false, this will return false because nothing in there is true. And all only returns true if everything is true. So currently it's false, but if I were to convert everything to true, this will go to true. You can also perform logical operations on items within a NumPy array. So I have 2 NumPy arrays here full of conditional statements, and this will run an AND on both of them. So go through each item one by one and perform an AND and return that as an output array. So true and true is going to be true, so we get true. False, true and false is false, so we get false. False and true is false, so we get false. And false is false, so we get false. We can also run OR statements, so true and true, true or true is true, true or false is true, true, false or true is true, and false or false is false. We can also write logical NOT conditions, so this will return the not the opposite of the conditional value, and it can only take in one array, so I feed in array 1 here, and it'll give me the not output. So it'll give me false, false, true, true, like the following. You can also manipulate arrays. The first thing we'll be doing is indexing. So in order to index it, it's very similar to indexing values in a list. You just use the bracket notation here and specify the index you want the output of. So first I initialize an NumPy array, and then let's say I want to get 1. I just use bracket notation and specify 0. Let's say I want to get 4. 0, 1, 2, 3. 3 is the index of 4. That gives me the output of 4. And then let's say I want to start from the very last element. Output. And then I just put in R bracket notation -1, and then I get the output of 5. Slicing is also very similar, if not exactly the same as slicing with a list, but in this case, you're just using an array. So let's say I want to get all the values starting from beginning up to the 3rd index. This will return the first 3 elements, 1, 2, and 3. Let's say I want elements from index 3 to 6. Just remember the ending value is exclusive, so we do 3, 7, and that will give us 0, 1, 2, 3, 4, all the way up to the index of 7, so give us 4, 5, 6, 7. If it wants us to get, if you just want to get even indexed elements, we'll specify 2 commas and 2. Oops, sorry, odd index elements. So this will begin from the beginning and then move up in intervals of 2. So it'll go 1, and then 3, 5. You can also reverse the direction of this array. So go descending 10, 9, 8, 7, 6, 5, 4, 3, 2. You can also append and concatenate arrays in NumPy. So here I have 2 NumPy arrays specified, and let's say we want to add the ending of this to here. I would just use the append method, and I specify the first one and then the second one, and this will just add this to the end of this array and create an appended array. So that will output in 1, 2, 3, 4, 5, 6. And then we can also concatenate arrays. Concatenation requires an axis. So in this case, we have an axis of 0 because we're just adding, concatenating one-dimensional arrays. So here I specify parentheses, and within parentheses I add R1 and R2. You can also perform something called flattening. So let's say you have like a 2-dimensional array, and full of 2 rows, but you just want to collapse it down into a single row, you can perform the flatten operation, and that will just condense everything into one row. For this second exercise, you are tasked with creating an emission profiling program that performs the following objectives. Give it a shot and come back to this video when you are done. Okay, so for this one, we are first tasked with creating a random number generation function to generate simulated altitude, velocity, and acceleration data. So first, let's begin by importing Numpy as NP. And then let's do altitude first. And we're going to set it to np.random.uniform. And let's start with 0, go all the way up to 10,000. And have a size of 1,000, which is specified here. Assume that the flight data consists of 1,000 data points. And then for velocity, it's going to be the same function. Let's create a random value. I'll start from 0. Typically for missions, you can use an arbitrary value, but I will use something realistic, 400 meters per second. And then acceleration, 0 doesn't really make sense because you can have negative acceleration, not object can decelerate. So 20 meters per second squared and 20 meters per second squared. And then these are all going to have the same size as 1,000, which is what's specified here. And now let's identify critical points. So critical altitude, critical velocity, critical acceleration. So altitude must be above 5,000 to be critical, velocity has to be greater than 300, and acceleration has to be less than negative 9.8 per second squared, indicating deceleration. All right, so let's start off with altitude. And we're going to need something called conditional values in Numpy, like we demonstrated before. And this is done by specifying the Numpy array. And inside these brackets, we're going to put in the conditional statement. So altitude, in this case, has to be above 5,000 meters. And let's do this for velocity. Critical velocity is velocity. Velocity must be greater than 300 meters per second. And then critical acceleration has to be acceleration. And inside these brackets, acceleration is less than negative 9.8. So now we need to concatenate arrays representing critical points to an array and then print it out. So this will be like a flight profile, and we can set it to NP, and we can use the concatenate method. And we're going to concatenate 3 values together. So I'm going to specify parentheses, and inside those parentheses will be all the critical values: critical altitude, critical velocity, and critical acceleration. And now, since we have the flight profile, we can print everything out. So I'm going to say flight profile, and then I'm going to print out the entire profile. So you can see the negative values here are critical points for deceleration. These values here, I'm guessing, is for velocity, because it's 10 times into the second power And then these huge values here in the beginning will be critical altitude, because it starts at critical altitude, goes to critical velocity, and then goes to critical acceleration. Hello, and welcome to the second lesson of the second module. In this lesson, we'll be covering the foundations of Pandas, which is a Python library used for data manipulation and analysis. It allows us to work with data structures and functions to manipulate and change these data structures by simplifying the workflow of structured data, which can be found in sources from tables or spreadsheets. So in order to use this, we're going to first import the Pandas library under the alias of PD. And once we do that, the first concept we will cover is series. And you can think of series as a one-dimensional label array capable of holding pretty much any data type from integers, floats, strings, and so forth. And you can think of this similarly to as a column within a spreadsheet or a single list in Python. So to demonstrate this, we're going to first create a NumPy-based array by importing NumPy, and we're going to create a data variable that holds a NumPy array of integers. So in this case, we have an array of integers consisting of 10, 20, 30, 40, and 50. And we can translate this array into a Pandas series by using pd.series. And by inputting the NumPy array here, we effectively have a series data affiliated with this variable. So if I print out series, we can see that we have a Pandas series outlined here, and each item has its own index, 0, 1, 2, 3, 4, and we have the data type of the Pandas series as an int64. We can describe this Pandas series in a wide range of ways by using attributes and methods that are affiliated with it. So here I outline two attributes that are affiliated with the Pandas series. So I use index and values. Index provides us with indexing information, so it gives me the start and stop index alongside the step of this Pandas series. I also print out values, which prints out the individual values that are contained within this Pandas series. So I have 10, 20, 30, 40, 50, and so forth. And we can also access methods that are intrinsic to this Pandas series. So I do sum, which returns the sum of all these values, which is 150. Max, which gives out the maximum number held in the series, which is 50. And min, which gives us the minimum number, which is 10. So we have 10, 50, 150. Values prints this out, and index prints out the range information. Moving on to data frames. Data frames is used for data that has two-dimensional labeled data structures. So in this case, using the spreadsheet analogy, this would be a spreadsheet containing of both rows and columns. In order to demonstrate this, we'll be using a hard-coded data dictionary, and this dictionary holds information about people, and the properties are going to be name, age, and city. And the people are going to be John, who's 30 and lives in New York, Emma, who's 25 and lives in London, and Peter, who's 35 and lives in Paris. So currently this is within a Python's dictionary, but we can convert it into a data frame by using pd.dataframe and enveloping it inside of this data variable. So by feeding it in, this translates it into a data frame, and we store it inside of a variable called df. So by printing this out, we can see that we have 3 rows here, each affiliated with its own person, and the columns describe the characteristics of the person. So we have John, who's 30, lives in New York, and so forth. We can access rows, columns, and individual elements using indexing, slicing, or label-based methods. So here I demonstrate us accessing a single column. So let's say I just only wanted the names of each of the people affiliated with this data frame. You can do print name, which just prints out the names. You can also print out multiple columns. So let's say I wanted to get the name and the age of the people. So I do name, age, and you can see we get the name and the age. We can access a single row. So let's say we wanted to get the first person. We only wanted information about John. we can see that John has a row index of 0, and let's say we wanted to get information about Emma, who has a row index of 1. We can do df.lock, and by doing lock and specifying the index of the row we want, we can print out information about that person. So here we have name Emma, age 25, and city is in London because we use the lock in order to access that row. We can use ilock in order to access a single row by the index. So in this case, I do ilock of 0, and that gives us information about John. We can access elements within the data frame itself. So let's say I wanted to get a single element by label. So I would specify the row and the attribute I want to get. So at 0 and age. So this will print out 30. This prints out 30 because we're specifying the row of 0. So we're going to get this row, and we want this property here, which is age, and that is 30. You can use IAT if we want to access a single element by its index instead of its property name. So let's say I wanted information at row 1 with an index of 2, so 0, 1, 2. This will print out London, as you can see, because we're accessing the second index of the first row. You can perform various manipulation methods on data frames themselves, like adding or removing columns, filtering, or applying functions. So here, let's say we wanted to add a new column that specifies the gender of each of these 3 people. So I create a data frame manipulation, and I specify the new column I want to add, and then I specify the genders of each of the respective people. So John is male, Emma is female, and the last person is male. And you can see here, after I manipulate it, we add another column to our data frame. We can also filter for rows based on a condition. So let's say I wanted to get everyone above a specific age. I wanted everyone above the age of 25. So you can do df, which will return the data that fits all these conditions, and then here I specify the condition. And the condition is that df age, this property, has to be greater than 25. So we can see here, this should return John and Peter, because those are the only 2 people above the age of 25, and you can see that our filtered data frame does so. Lastly, you can also apply a function to each column. So like for each row that has this column in it, it will apply a lambda function, and a lambda function is just a function embedded in one line. And you can see here, it's saying for each age value, just add by 1. And what this will do to our data is it will up the age of each person by 1. So you can see this outputs everyone's age as 1 year older. So you can see John, who was 30, is now 31. Emma, who was 25, is 26. Peter's 35 is now 36. Happy birthday, everyone. So this leads us to our second exercise, which is about planetary analysis with pandas. And the objectives are outlined below. You're supposed to create a panda series representing planet distances from the sun in millions of kilometers. You need to create a pandas data frame representing characteristics of moons of the outer planets. And then need to analyze the data to find key information about planetary distances and moon characteristics. Give it a shot and come back to this video. Okay, so let's create a cell here. And let's begin by importing pandas. So we're going to do import pandas, and we're going to import it under the alias of PD. And once we do that, let's first begin by making a series that represents the distances of planets from the sun. So let's call this planet distances. And let's set this equal to a series. So we're going to do PD series. And inside of these parentheses, we're going to have it represent planet distances. It also wants us to create a Pandas data frame representing the characteristics of the moon, described by moon data. So let's call this moon characteristics. And we're going to set this to a data frame. Which represents the moon data dictionary. Oh, let's make sure this has the pre-established data. And now you can see we have our planet distances Pandas series and moon characteristics Pandas data frame. So now that we have this, let's perform some analysis on the data. So let's first get the average distance of the planets from the sun. So I'm going to and in order to print this out, we're going to be performing a sum method on the Pandas planet distances series. So we're going to do this dot mean, and dot mean will give us the average. And let's also print out the number of moons for each outer planet. So I'm going to specify a new line. I'm going to use our \n to create a new line. And I'm going to say number of moons for each outer planet. And let's specify our outer planets. So the outer planets are going to be Jupiter, Saturn, Uranus, and Neptune. And for each outer planet, we're going to loop over them and print out the moon that is associated with it. So in order to do this, we're going to do for planet of outer planets. Let's get the number of moons. The way we do this is let's create a new variable. Let's call this num moons, and let's set it equal to moon characteristics, which is our data frame here, consisting of all the planet data associated with moons. And inside this, we're going to specify a conditional. And we want the affiliated planet, since this specifies our planets, and we want to make sure it matches the specific planet we're looking for. So in this case, this is going to run the case for each of these planets and check if it's the planet we're searching over. If that is the case, we're going to get the shape index of 0, which will return the number of moons affiliated with it. So let's print out this information. I'm going to return a formatted string, and inside here we're going to specify the planet. and then the number of moons affiliated with it. So you can see here, the first one is pretty straightforward. It returns the average distance of the planets from the sun using the mean, which gets us the average of all these values here. And then the second one loops through each of the specified outer planets, and for each of the planets, it checks if it matches the moon data. And if it does match the moon data, it will get the number of planets associated with it by using shaped 0. Shaped 0 returns the number of outputs this is, like the length of this output. So you can see in this array we have Jupiter happen twice, Saturn happen twice, and Uranus one. So it counts each moon instance of Jupiter. So in this case that'll be 2 because we have 2 moons associated with Jupiter. For Saturn we also have 2 because Saturn pops up 2 times, and Uranus we have 1, and Neptune we have 1 because Uranus and Neptune pop up only once respectively. And you can see all that data is outlined. The last thing we're going to do is we're going to get the largest moon of each outer planet. So this is going to be a similar thing where we loop through each of the outer planets. And once we do that, we're going to get the largest moon. And this is going to be, we need to check for a match again. So let's make sure it matches the planet we are searching for. And once we match this planet we're searching for, we're going to run the sort values method. And this is going to sort by a specific property. So in this case, we want it to sort by the largest. So it's going to be diameter. I'm going to get the entire full name of this column, and I'm going to put it in here. And let's make the ascending property false. It's naturally going to be ascending, meaning it's going to be going up. However, we want this to be descending because we want to get the largest first. So I'm going to set ascending to false, and then I'm going to use the ilock method in order to get the specific column number, which is 0. And then once we get that value, we're going to print it out. So I'm going to do print, and in here, let's use a formatted string. And I'm going to specify the planet, and it's going to contain the value of the largest moon. And let's get the name of the moon by specifying that within the column. And you can see here, let me create a new line that prints some empty space. This will give us the planet and the moon we're searching for. So here we have Jupiter and Ganymede. Ganymede is the largest moon associated with Jupiter because you can see here Jupiter has 2 moons. It has, within this data set, it has Io, which is 3,642 kilometers in diameter, and then it has Ganymede, which is 5,262 kilometers in diameter. So it has Ganymede, and it does this because it performs this conditional here that specifies all the planets for Jupiter, and for all the planets for Jupiter or whatever planet it's searching for, it sorts the values by its diameter, makes sure it's descending, and it gets the first item in the row, and the first item will be the largest in diameter. And currently what it's doing is it's printing the planet and its largest moon. Let's say we also wanted to print the diameter affiliated with the largest moon, so I'm going to put this in parentheses in the string, and inside these curly braces to specify the value, I'm going to do this largest moon, and instead of the moon name, we're going to specify the diameter, which is this string here. So now you can see if we run it, we get the name of the moon and its value, and let's also specify the unit inside the parentheses. So you can see the planet, its largest moon, and how big it is. Pandas also allows us to work with a wide range of file formats from external sources and data sources, such as data sources that are published on the internet. To demonstrate this, I have an external CSV file here. This is the link to the CSV file that contains information about SpaceX missions. And let's say I wanted to load this into a Pandas data frame. In order to do so, we're using the pd.readCSV method. ReadCSV will read in the CSV file format from this external resource. So here, this creates a data frame that loads in all the data from the CSV format. And let's say we want to gauge more information about this data set. So in order to do this, we can do a few methods in order to get some initial information about it. So let's say we want to print out the first 5 rows of the data frame. We can do df.head and print that out. So this will give us the first 5 rows within the data frame itself. So you can see it gives us the flight number, F1-1, the launch date, the launch time, where it was launched, the launch vehicle type, the payload name. So the first payload was Falcon Sat 2, the payload mass, how much, the customer name, the reason it failed. Let's say we also wanted to get basic information about the data frame. You can use the info method. And the info method, you can see, prints out general information. So here it prints out the number of columns. So it has 16 columns which contain information like customer country, mission outcome. We get the data type of each column. We get the index affiliated with each column, which is really handy, especially if we're working with large data frames, and the column name specifying the characteristics of the data. Let's say you want to get summary statistics of the numerical columns. So you can see here we have numerical columns like payload mass, and let's say I just wanted to get numerical statistics related to it. You can use df.describe in order to do so, and you can see what that does is for numerical columns like the payload mass, it'll give us general statistics information. So it'll give us the count, so there's 33 values, the mean, the average payload mass is about 3,000 kilograms, pretty heavy. The standard deviation, the minimum payload mass is really tiny, it's 8 kilograms. The maximum payload mass is super heavy, it's almost 10,000 kilograms, the 50%. So general statistical information to get a gauge of numerical columns. This leads us into core methods with Pandas. There's a wide range of mathematical and statistical methods you can run on Panda data frames. So for example, you can apply basic statistical and mathematical functions like mean, median, sun, standard deviation, variance, and more. So here's just me playing around with each of these respective functions and then printing out the values. So let's say I wanted to get the average payload mass. You do mean. Let's say we wanted to get the middle, like if we listed out all the launches, which will be the number with the mass that's exactly in the middle of the data set. The sums up all the values related to mass, sums up all the mass, the standard deviation, and then the variance. So you can see here, each of them are printed out. There's also a few more explorative methods I want to cover. let's say we wanted to print out all the unique launch sites. So here in the SpaceX datasets, there's a specific number of launch sites. There's Cape Canaveral, Marshall Islands, Vandenberg space bases, and so forth. But let's say we only wanted unique launch sites. We can use pd.unique, and this will specify a data attribute for all the launch sites. And then let's say we wanted to describe statistical values of all the numerical columns. This will be another way of doing so, where we use the scribe method and we only include a numpy.number. So this will produce an outcome with payload mass that outlines its statistics. We can also print out the one above it. So here you can see this will give us an array listing out all the unique launch sites. So we have Marshall Islands, Cape Canaveral, Vandenberg, Kennedy Space Center. You can also use specific methods for data selection and data filtering. So here, let's say I want to get specific columns of the data set. So let's say this data frame contains a lot of information, like I mentioned before. However, let's say I only wanted the name of the payload and the orbit of the payload. So running this will return the payload name and the orbit it is in. So let's RadSat is in low Earth orbit. We have SpaceX CRS-2, which is low Earth orbit. We have Cassiope, which is in polar orbit, and so forth. And let's say we also wanted to filter rows based on a numerical condition. So let's say I wanted to get all payloads that exceed 3,000 kilograms in mass. So I would do df payload mass, which specifies the column I'm shooting for, and runs a conditional on it, checking if it's greater than 3,000. And this will return all the payloads that are greater than 3,000. So you can see here we have payloads outlined, like the Sky Perfect JSAT, TICOM, for different customers. You can also perform methods to group data by using the group by method. So let's say I wanted to group the data by their launch sites. So here we have our 4 respective launch sites. I just create specific groupings based on the launch site, and then here I obtain the average value for the payload mass. So this will return the average payload mass out of each launch site. You can see launches out of Cape Canaveral tend to have the highest mass, followed by the Kennedy Space Center, Marshall Islands, and Vandenberg. This leads us into the second exercise, where we're going to be conducting more research analysis on the SpaceX launch dataset. Give a look over the objectives outlined here, and then we'll walk through it together. Alright, so I'm going to create a new cell, and first let's begin by importing Pandas. So we're going to import Pandas as PD, and then let's outline our CSV again. So I'm going to re-import the CSV. We can reuse code that was specified above. So let's reuse this code again. So this specifies the URL of the CSV data, which is our SpaceX mission data. And then this reads it into a Pandas data frame. Once we have that, let's refer to the dataset not as df, but launches dataset as specified. Dataset. Perfect. And then let's get some values associated with the dataset. So we're going to do launches dataset.head to get the first few rows. So you can see we have the flight number, launch site, vehicle type for each satellite. And then let's move on to the next the prompt where we need to print out the customer country column. So in order to do this, we can refer to launches dataset. In order to get access to a specific column, all you have to do is use the arrays method, where you're kind of like indexing out for the column itself. So I use brackets, and inside those brackets I specify the name of the column I'm looking for. In this case, it's the customer country. And you can see if I run this, it will print out all the countries of the customer who purchased the payload being deployed. So you have US, Malaysia, Canada, Luxembourg. And after that, we're going to move on to the next prompt, which is print out all the unique customer countries. We're going to be doing this by using the pd.unique method, which gives us all the unique values associated with a specific column. And in this case, the column we want to do is the customer country. And you can see this gives us all the unique countries that are launching payloads. So we have the US, we have Malaysia, Canada, France, Turkmenistan, Israel, Japan. And next we want to make a variable named launches by country and make it grouped by the customer country column. So I'm going to specify launches by country. And here we're going to be utilizing the group by method. So I'm going to specify launches dataset and then specify group by. And we want to group by the customer country column. So this will contain all the launch information affiliated with a specific country. So let's get information about this by doing head, which prints out the first 5 values. And you can see here this returns an output having groupings of launches affiliated by each customer country. So in this case, you have it grouped. And then we need to print out all the launches with a payload mass of less than 4,000. We can do this by specifying a conditional directly within the Pandas dataset. So let me go down here. And then we're going to specify a conditional. So let's specify launches dataset. And here we can have our conditional. So we're going to specify the column we are trying to selectively filter out. So launches dataset. And the column name is payload mass in kilograms. And it has to be less than 4,000. And this will print out all payloads with a mass of less than 4,000 kilograms. Moving on, we need to print the medium payload mass for the United States. In order to do so, we're going to run another numerical conditional. So let's do launches dataset again, and in this case we're dealing with all the countries affiliated with the US. So our column that we're dealing with is going to be customer country, and we're going to check if it is equal to the United States. So this in and of itself is going to return all the launches affiliated with the US. And now we want to get the payload mass of all of those values. Payload mass in kilograms. And then we want to get the median, the middle value. And this prints out 1925. So the median payload mass launched by the United States is 1,925 kilograms. In this lesson, we'll be covering the foundations of Matplotlib. Matplotlib is a library for creating visuals in Python. These include line charts, graphs, various plot types, and more. You can learn more about Matplotlib on their website here. And in order to import Matplotlib, you need to use the import keyword followed by matplotlib.pyplot, and then we can name it under the alias of plt. And we can begin by creating a simple line plot using Matplotlib. In order to do so, you need to specify the values of x and y. So in this case, I have x set to a list from 1 to 5, and then the y values associated with each x value here. And in order to plot them, you need to use plt, and then use the plot method, and specify the x and the y values. And then you can show it by using the plt.show method. So here, this will plot the x and y values on a line chart. You can also add visuals to your plot by adding more parameters to the plot method. Ways to customize the appearance include the color, the line style, the marker, and the marker size. So in this case, I'm changing the color of the plot to be green, the line style to be dashed by including the line style parameter here and including 2 dashes, the marker style be this dot, and then the marker size. And then we can reshow the plot by typing in plt.show again, and this will show the updated plot with the customized appearance. You can also add titles alongside text for each of the axes by adding the plt.x label and specify the name of the x label, the y label with the y-axis title alongside the title for the entire plot, specified here, and then by typing in plt.show again, and this will show the updated plot with the new y-axis title, x-axis title, and the general plot title. This leads us into the first exercise of this lesson, where you'll be plotting supernova brightness. A supernova is a powerful and energetic event that occurs during the final stages of a star's life cycle, and it is characterized by a sudden and dramatic increase in brightness, followed by gradual fading over time. In this example, you are observing a Type 2 supernova and trying to visualize the observational data on the brightness of the supernova at various time points following its initial explosion. Give this a shot yourself and then come back to this video. So we have the sample dataset predefined here with the time points and the brightness. And if we create a code cell below, first we'll need to import Matplotlib. You can do so by doing import matplotlib.pyplot under the alias of plt. And then now we can plot the values. So first we'll specify the x-axis, which will be the time, and then the y-axis, which will be brightness. And then we can specify the styling. So we want the color to be purple, the line style to be dashed. So we'll do these 2 dashes to indicate that, and then the marker to be an O, followed by the marker size, set to 5. And let's set the X and Y labels. So the X label will be called X, and then the Y label will be called Y. And then we can specify the title of the graph, which will be brightness of supernova. And then finally, we can show the plot by doing plt.show. And you can see this will plot the brightness of the supernova over time, and you can see the initial explosion here with a drastic increase in brightness, followed by a gradual fading over time. You can use Matplotlib to create more complex visuals using other libraries such as math and Numpy libraries. So here I import math and the Numpy library, and this will give us more capabilities to plot more mathematical functions. An example of a mathematical function you can plot using these two libraries in tandem with Matplotlib is the sine function. And in this case, we will be plotting evenly spaced values, so we'll also need the np.linspace method. And what this does is, for the x values, this will give us evenly spaced values from 0 to 2 pi, because we know that the sine function ranges between 0 to 2 pi on the x-axis. So this does that. And then on the y-axis, we want to show the output of the sine function with x in it. So do np.sine with x. And then we plot the values by doing plt.plot with the x and y values inside. We give the x and y axes corresponding labels. So I gave the x-axis the x label and the y-axis the sine of x label. And I title the graph plot of sine of x. This plt.grid method will give this chart a gridded background. And then we do the show method in order to show the plot. So here you can see that we have a plot of sine of x over time, which is this wave-looking graph with x and y axes labeled and a title. You can also plot multiple mathematical functions on the same axis. So in this case, let's say I want to plot sine of x and cosine of x. We do the same x ranges, 0 to 2 pi, with 100 evenly spaced values. And I create two values for y in this case. y1 is sine of x, and y2 is our second function, cosine of x. And then now we just need to do plt.plot twice, one time for sine of x, which is y1, and then the second time for cosine of x, which is y2. And now if I run this code, you can see that we have two functions plotted on the same graph. You can also create three-dimensional surfaces using the MPL2 Toolkits module. So here I import the axes 3D from the MPL Toolkits 3D module. And here I create a figure and I set it equal to the figure function. And this just tells it to create a 3D projection on the axes. So this means we will take three axes, the x, the y, and the z axis, to represent each axis within the three-dimensional plane. And the x and y will be values from -5 to 5, and it's going to be 100 evenly spaced values. And we will create a mesh grid of these x and y values. And the z-axis will define the function we want to plot. So this is a three-dimensional mathematical function, which is a sine of the square root of x squared plus y squared. And you can see it looks like the following if we plot it. And we just plot the surface by doing the axis.plot surface and feeding in each of the coordinates, so x, y, and z. And this specifies the styling of it, so the way it's colored and shaded in is called verdis. And then here we label each of the x, y, and z labels, and we set the title of the plot, and then we finally show it. This leads us into exercise 2, where you can apply your understanding of math and Numpy alongside Matplotlib to plot the tan and cosine functions. Try this yourself and come back to this video when you're done. So let's begin by importing each of the three modules we'll be working with. So first, let's import math, and then import Numpy as np, and then finally import Matplotlib as plt. And then the first asks us to create a plot of the tan function with names for plot title, x-axis, and y-axis of our choice. So let's begin by specifying the x-axis, and these will be evenly spaced values. And we know from the tan function it goes from 0 to 2 pi, and we can use math.pi in order to get the pi value. And we want 100 evenly spaced values. And then on the y-axis we want np.tan, because we're plotting tan over the range of x. And then let's plot this x and y. And let's give it a title of plot of tan x. And let's give it an x and a y label. So the x will be called the x-axis, and then the y label will be called tan of x. So now if we run this, we should also finalize this with plot.show. We will get x and tan x as the x-axis and y-axis labels, with a plot of tan of x with the title plot of tan of x. And let's make sure we put a grid on this, so we can do plt.grid and true inside, and this will give us a grid background. Now we are tasked with creating a plot with tan and cosine of x, with custom titles, x-axis, and y-axis. And we need to make sure that the x-axis has equal spacing from 0 to 2 pi using 50 samples, and make sure we have grid enabled. So the x value should be the same, but rather than 100, we'll do 50 evenly spaced values. And this time we're going to be plotting two functions. So we do np tan of x for the first one, and then we'll do cosine of x for the second one. And now we can do plt.plot x, and let's plot y1 first. And then let's plot y2. And then let's give this a title, plot of cos x and tan x. Let's give it an x label of x and a y label of y. And then we can do plt.grid true in order to enable grid background. And then we can finally show everything by doing plt.show. So this will give us a plot of cosine x, which is this orange line here, and tan of x, which is this blue line here. Welcome to the fourth lesson of the second module, where we will be covering orbital mechanics and the foundations of classes in Python. So firstly, let's cover orbital mechanics. Orbital mechanics is a broad field of study that relates the motions of artificial satellites under the influence of gravity and other factors that might influence its orbit, such as thrust and naturally induced forces within the space environment. So underpinning all of orbital mechanics is math, and the math specifically behind conic sections. So in math, a conic section refers to a curve that's created when we have some kind of plane that passes through a right circular cone. So here we have a right circular cone, and the orientation of which a plane, which is pretty much like a flat sheet of paper you can think of compared to this cone, how it passes through it will define the properties of the conic section. And the orientation of which the plane is passed through the cone can be categorized as a circle, ellipse, a parabola, or a hyperbola. So here we have a circle, this is perfect circle. We have an ellipse, which is slightly elongated. A parabola doesn't have ends, and then we have a hyperbola, which is more exaggerated than a parabola. You can see here, if the plane passes through the right circular cone at a complete angle, it forms a circle. If it's slightly more tilted, it creates an ellipse. More tilted, parabola, and then most tilted, where it's completely orthogonal or 90 degrees, or like parallel to this line here, we have a hyperbola. And all conic sections are defined by their eccentricity. This is like the stretchiness, so how stretched out the ellipse of the orbit is, and we can divide it further. So underpinning the characteristics of an ellipse that is formed within a conic section, we'll be focusing on ellipses because all orbits are essentially an ellipse of some kind, with a perfect circular orbit being a special case. And here, with an ellipse, they have foci, or focus, for one point, which are two fixed points within the ellipse itself. And these points are such that the sum of the distance from any point on the ellipse to the two foci remain this constant at all times. And we also have the major axis, which is the longest diameter of the ellipse. So here we have two diameters, this one denoted by the red line, which is the major axis because it's the longer one. And then we have the minor axis, which is the shortest diameter of the ellipse that connects two co-vertices. And you can see that the minor axis and major axis are always perpendicular to one another in an ellipse. Going further with more details about an orbit, orbits have 2 points. They have the apoapsis, which is the furthest point of a satellite from its orbiting body. So here we have the orbiting body, which is the sun, and we have the artificial satellite. The periapsis and the apoapsis. The apoapsis is the longest point from the satellite to the orbiting body, and then the closest point is called the periapsis. In an orbit, we also have two terms called the ascending node and the descending node. So you can see here, if we have a perfectly flat disk, and then we have our orbit here, which is slightly inclined, you'll have two distinct points of where this orbital plane crosses this reference plane here, and the direction of which the satellite is heading when it passes either of the 2 points describes whether it's ascending or descending. So let's say I'm tracing out the path of this orbiting body here on this orbit. You can see that the satellite orbiting body is going upwards when it crosses this point. So this is called the ascending node, and then it comes back down, 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 and it's going down as it's passing this point here. So this one's denoted as the descending node. To further characterize orbits, we have things called orbital elements, also known as Keplerian elements. These are foundational and incredibly important to describe the characteristics of an orbit. And they include the semi-major axis, which is half of the major axis. So you can see here, it's denoted by A, and denotes how far away the satellite is. In this case, we have an exoplanet from the central body here. We have the eccentricity, which is how much the orbit deviates from a perfect circle, like a stretchiness. So you can see this is somewhat of an eccentric ellipse. We have the inclination, which is the angle between the reference plane. So here we have the reference plane, which is shaded in gray, and our orbital plane, which is shaded in this tinted yellow. And the angle between the reference directional plane and the orbital plane is called inclination. That's given in degrees. We have the argument of periapsis, which is the orientation of the orbit. It is the angle between the ascending node and the periapsis. So here, the periapsis is the closest point. So here, this is the closest point from the orbiting body of the orbit. And the angle between the ascending node, which is here, because the orbiting body goes upwards at this point, and the semi-major, the perigee of the orbit is denoted in omega W, and that's the argument of periapsis. Next up, we have the longitude of the ascending node, which is denoted by this horseshoe sign, and it also gives us the angle measured from the reference direction of the ascending node. So here we have the ascending node, and then we pick a reference direction, which is a specific angular direction of the plane, defined of the orbit, and the angle between this reference direction and the ascending node is the longitude of the ascending node. And then finally we have mean anomaly. This is a positional value, and the only positional value in regards to time of an orbit. And this measures where the satellite is in regards to the orbit, like where it's positioned at its point in time. And this is given in degrees. This is pretty complicated, especially if you're getting into it in the beginning. But as you become more acclimated to how orientations of satellites work, this will become second nature. So diving a little bit more into how semi-major axis relates to eccentricity, we know that the semi-major axis is the length from the center to the furthest point of an orbit, or the apogee of an orbit. And it shows how stretched out the orbit is. You can see as we have larger values of eccentricity, the more stretched out the ellipse looks, and this is directly related to the length of the semi-major axis. You can see as the length of the semi-major axis gets smaller, this eccentricity gets larger. So they're inversely proportional. And you can, as a reminder, we can use the eccentricity value to classify the shape of the orbital path. When E is 0, it's circular. When it's between 0 and 1, it's elliptical. When it's 1 exactly, it's parabolic. And then when it's greater than 1, it's hyperbolic. Inclination. This is the angle between the orbital plane and the equilateral plane. And when it's 0 or 180, we have a completely equatorial orbit, meaning it orbits the equator. When it's between 0 or 90, this is prograde. This is when the orbit of the planet's equator matches the direction of its rotation. So we have prograde. And then when it's 90, we have a special case called the polar. And then when it's between 90 and 180, we have the opposite of a prograde, where the orbiting object moves in the opposite direction relative to the rotation of Earth. We also have special cases with orbits as well that you might be hearing as these terms are thrown around generally within the aerospace community. We have geostationary orbits. This is a circular orbit where the satellite maintains a specific point around the central body at all times. This is when you want a satellite to, for example, plot out imagery over a same location. You would use something called geostationary, where the satellite matches the rotational velocity of Earth in order to get its specific data above a very specific point. We also have sun-synchronous orbit, where the satellite orbits the sun in a manner that it maintains its fixed angle in respect to the direction of the sun. So for example, a lot of satellites that are providing daytime data are within sun-synchronous orbit because they constantly want the sun to be behind them. We have Monea orbits, which is an eccentric orbit where it's highly elliptical and has a very high inclination value. And it allows for the orbit to maintain a high altitude at all times. It's a very exaggerated orbital configuration. We have a Hohmann transfer. This is for interplanetary trajectories. So let's say we want to maximize propellant usage, but we want a satellite to move from one altitude to another. The Hohmann transfer orbit will let us do that. We have low Earth orbit, which is any orbit between 160 and 2,000 kilometers above the surface of the Earth. A lot of internet satellites are within LEO. We have medium Earth orbit, which is 2,000 and between 35,786 kilometers above the surface of the Earth. And then we have high Earth orbit, which is any orbit above that. As with orbital motion, we are going to be deriving all orbital motion from Kepler's laws of planetary motion, which state that all planets move along elliptical paths, which is the law of ellipsis, the law of equal areas, where if you were to draw some kind of hypothetical line segment joining a planet to the sun, it will sweep out equal areas in equal intervals of time, meaning that the area formed by this little angular shape is the same as the area formed by this amount of shape, and the amount of time you can see is the same, and the areas are the same. So that's equal areas in equal time. And then lastly, we have the law of harmonies, where if we would take the square of the orbital period, it is proportional to the cube of the semi-major axis of its orbit. So let's say we take the semi-major axis, which is this line here. This value squared is proportional to the cube of the semi-major axis of its orbit. Moving on to classes in Python. Classes in Python are essentially a blueprint for creating things called objects. And within a class, you define the specific attributes and functionality of an object you want to have. The best analogy of this would be to use an example of a dog. So let's say I want to make a blueprint for how dogs should be specified. So here I have something called an init method, and this is known as a constructor. A constructor is what runs every time I want to create a new instance of this class. So every time I want to make a new dog, this will be run. And here I use the self attribute. This is whenever you want to assign a specific attribute to the specific object related to this class. So I set self.name is equal to name. So whenever I invoke an instance of this dog class, I will name it. And then inside this class, I define two methods which define specific functions of what our dog can do. So let's say we want our dog to bark and we want to change the name of the dog anytime. So in this bark method, first I reference itself. Every time you want a specific class to run something, it's good practice to mention itself. And here I print out self.name under a formatted string. So this gets the name of the dog and puts says woof at the end of it. You can also change attributes related to a specific class. So here, let's say I wanted to change the name depending on what the user inputs. So here I say it prints out the previous name, and then I reset the name to the name the user wants, specified within this function as a parameter of name. So I do self.name is equal to name, and then I print out the new name. So you can see here is an example of me making an instance of it. So this will turn this blueprint and use this blueprint dog class in order to make a specific object. So let's say I wanted to make a dog called Dexter. So I would dog, and you can see that the input constructor takes in a name. So we want this name to be Dexter. And then I invoke a method on it. So here, remember we specified bark. So this will print Dexter says woof because it takes the name Dexter, puts it in this formatted string, puts says woof at it to the end of it, and then prints it out. And then I invoke the change name method on it and specify a new name. So let's say I want to rename Dexter to Duke. So I do my dog.change name, and then I specify Duke, and then I run bark again. So here it shows the previous name as it's re-specified here. It resets the name and then puts out the new name, which is Duke. And then finally I run bark one more time, which gets the name of the dog and then puts says woof at the end of it. This leads us to our exercise for this lesson. Your objective is to make a class for a spaceship, and then create a constructor for it, which takes a name, crew capacity, and speed, and create a few instance variables and methods of increase speed, set crew capacity, and state name. Give it a shot and come back to this video when you are done. So let's begin by creating a new cell, and in here I'm going to make a class, and we're going to call it spaceship. And first, we're going to specify a constructor. So remember, we can do that by specifying init. And here we take in the self as a parameter. And then we want to take in name, crew capacity, and speed. So I'm going to do name, crew capacity, and speed. And inside of this constructor, we want to set the instance variables. So we're going to do self.name is equal to name, self.crew capacity is equal to crew capacity, and then we're going to do self.speed is equal to speed. And now that I have this constructor created, let's first create a method named increase speed. And this is going to take in self and speed as the parameter, and this will uptick the speed by 10. So we're going to do self.speed plus equal 10, and this will take the current speed value and increase that by 10, and then we wanted to print out the new speed is the new speed. So print, and let's return a formatted string here. And I'm going to, inside curly braces, specify the new speed. So do self.speed and say is the new speed, exclamation mark. I'm going to create one more method. It's called set crew capacity. So we're going to do set crew capacity. And this will take in a new capacity value. So let's do new capacity as the parameter name. And this will set the previous capacity to the new capacity. So first let's print out the previous capacity, just so you know what the crew capacity is before we set it to the new one. So we're going to do previous capacity. And then here I'm going to do self.capacity. And then let's set the crew capacity to be the new capacity. And then let's do one more formatted print value that prints out the new capacity. So new capacity, and then we print out self.capacity. And then lastly, we're going to create a method called state name, which prints out the name of the spaceship. So we're going to do def state name self, and here we want to print out the spacecraft name. So let's do a formatted string, and I'm going to specify spacecraft name and do self.name. So this will create our class for us. And now let's create an instance of the spaceship class. So I'm going to name this spaceship, and I'm going to invoke the spaceship class. And let's specify the characteristics that we want for a spaceship. So we need the name. So let's say this is going to be for Starship. We want the crew capacity. So we can do 100. And you can also specify parameter variables in here. So let's be specific and just say crew capacity equals 100. And then we can say speed is equal to 500. So now let's say we want to use some methods for the spaceship. So let's say I want to get the name of this. So I'll do spaceship. Well, firstly, let's invoke this to make sure that we have our spaceship object. And then let's run a few methods on it. So let's first run state name, and this should return spacecraft name because of this formatted string, and then the name of the spacecraft. We have Starship because we set the name up here within the constructor to be equal to the name instance variable. Let's say I want the crew capacity to be set to 120 instead of 100. So we do spaceship dot set crew capacity, and inside here we do 120, and you can see self dot crew capacity, because we set the instance variable name to be crew capacity. That's a good catch. So you can see here, this will print out the previous capacity of 100 kilograms. And then after we update it for this method set crew capacity here, we have the new capacity. So it prints out the previous one, sets it, and then prints out the new capacity. Lastly, let's increase speed. So we're going to do spaceship dot increase speed. And we want to specify the value. Oh, whoops, we don't need a new parameter here. We just need self. And you can see here, when we run increase speed, it gets the current speed, increases it by 10. So initially its value is 500. It adds 10 to that, so it's 510. And then it prints it out. So it says 510 is the new speed within a formatted string. In this lesson, we'll be covering orbital visualizations and TLEs. TLE is a standardized format used to describe an orbit of an object around Earth, and it's formatted like the following. Here you have either 2 or 3 lines. If it does contain a third line, the first line is reserved for the name of the satellite, and the subsequent 2 lines include orbital details and other characteristic information about the satellite itself. So an example of a TLE breakdown would be the following. Here is a TLE of the International Space Station, and the first name is the name of the satellite, and on the second line, you first have the denotation of the line itself, so 1 is for line 1 and 2 is for line 2. And then the second value here, 25544U, is the satellite catalog number. So it's 25544 in the catalog, followed by the classification, which is U, standing for unclassified. After that comes the launch year. So this satellite was launched in 1998, so it shows 98. And then after that is the launch number of the year. So this was the 67th launch of the year, followed by A, which stands for the piece of launch. Next we have the epoch year, the epoch. And this is general timing information for which this TLE was recorded. So an epoch is a specific period of time, and then we have this time stamp within the time of the Julian day. And then these 2 values, which would be these 2 values here, are the first and second derivatives of mean ballistic motion, which describes the general velocity and motional information about the satellite. And then here we have the drag term and the ephemeris type. So the drag term will be the radiation pressure coefficient. And then the ephemeris type is always 0 because it's undistributed TLE data. And then we have a checksum in order to check for data, check for errors in the data appended to the end. The second line, the final line is also reserved for the satellite catalog number alongside each of the orbital elements. So we have inclination, right ascension of the ascending node, eccentricity, argument of perigee, mean anomaly, and mean motion, ended by the revolution number at the epoch, so a timestamp designator alongside a checksum for error checking. You can parse for TLEs, meaning that given a TLE that looks like the following, you can create a program that takes in the TLE structure and derives information from it, so it'll be able to designate which one of these numbers is which, so it can parse for the first line and designate it with the satellite name, and then match each of the following line characteristics with the values themselves. And the way we can do this is, suppose we have a text file. In here, and the way we parse for TLEs is, suppose we have a text file called tle.txt. And if we go here, we can see that inside this text file, we have the contents of an example TLE with the ISS. And the way we can extract information from it is by, again, using the open method, specifying the TLE file name, and then we can put it under read-only mode. And this method of read lines will read the 3 different lines of the TLE. And you can see if it printed out, we have each line printed out within a list. So each item within this output list is a line in the TLE. And once we get each of the lines of the TLE, we can clean the data. So if you've noticed here, we have these new line break characters at the end of each item here, and we don't want that in our output TLE. So in order to get rid of that, we can create a new list, and we can map over each line in the TLE output here using these lines of code. And the strip method gets rid of the extra break characters, special characters at the end of each item. So now if we print out this TLE data clean variable, you can see that we don't have the special characters of \n attached to the end of each item. The last step is to interpret the TLE and assign it the right values with the proper variable names. So firstly, I get the name of the satellite from the TLE, which is just the first line. Pretty straightforward. Then the second line and then the third line are lists containing different orbital characteristics. Well, strings, like large strings containing orbital characteristics. And how I extract the individual values is, suppose we have line 2, I just slice the characters out of the string themselves. So for example, satellite number is 5 in length, and it goes from, this is index 0, and this is index 1, so it goes from 2, 3, 4, 5, 6, and the end is exclusive, so we'll do 2, 7, and this will allow us to typecast it from a string into an integer, and then we save it into the satellite number variable. And for example, classification is just the little u at the end of this, and it has an index of 7, so I just do line 7, and it can be saved as a string to a variable. And I do this for each of the different characteristics in line 2, and then for each of the different characteristics in line 3, such as the satellite catalog number and the 6 different Keplerian elements, I follow the same logic, but in this case using the line 2 variable and extracting specific sections from that variable and typecasting it to numerical float values. And after you're done with that, you can print the TLE data. And this is just a huge print method, which takes in a satellite and it will extract different properties from it and print it out. So this is all the information that can be extracted from the TLE. So we can save this. And then I create a data dictionary here with a key and all the extracted variable values we assigned here from the TLE data. So now we can feed this dictionary into the print TLE method that we initiated here. And this will print out all the TLE information we extracted from this text file. We can now take this a step further and create orbital visualizations using Matplotlib. And before we create orbital visualizations, we need to make sure we calculate everything from the TLE. So a lot of the characteristics within that describe the orbit can be extracted directly from the TLE, but we do need to calculate some values ourselves. And one value is the semi-major axis. And there's formulas for that online. The value of the semi-major axis is as follows. And if you want to calculate this in Python, you can import the math library, and I wrote this sample method here that given the mean motion from a TLE, this will calculate the semi-major axis according to the formula above. And here is an example of me implementing that. And let's say we print the semi-major axis. This will, given the mean motion from a TLE, print out the semi-major axis. We will also need to calculate the orbital period according to this formula here. And this can also be done using the math module. And once you calculate the semi-major axis, it can be inputted into this function in order to derive the orbital period, like the following. And you can see the orbital period for this is going to be 5,495. The PyAstronomy library is a comprehensive Python library for astronomical related calculations and data analysis. And this can be used for the mathematics to derive the values for orbital visualization, so we don't have to do all the tedious math work like the following ourselves. We can just have PyAstronomy do it all for us. So here you can see that I import Numpy and PyAstronomy alongside Matplotlib. And I print out all the values we calculated before that define the orbital characteristics of the orbit at hand. So here we have the semi-major axis, the period, the eccentricity, and all the 6 Keplerian elements. And now we can feed this into the Kepler ellipse method of PyAstronomy, setting the semi-major axis, the period, the eccentricity, and all of these rest of these values for the orbital characteristics. And this creates the range, so it goes evenly spaced values from 0 to the period of the orbit, so how long the orbit lasts, and we create 200 evenly spaced values. And this will create all the positioning information given the range. And now if we use Matplotlib and create a plot, we can visualize the orbital trajectory. I think I named it wrong. We can visualize the orbital trajectory of the International Space Station just from the TLE itself. So what this program does is it takes all this information from the TLE and computes the mathematical values, and then finally visualizes the orbit. This leads us into the exercise of this lesson. You are tasked with creating your own orbit visualization program that parses and visualizes TLEs. Make sure it follows the objectives outlined below. So in order to do this, let's first import all the libraries. So first we'll do Numpy, and then math, and then we can import astronomy, and then we can import the Matplotlib modules, import Matplotlib, and once we have everything imported, we can first follow the step here, which is to create a class entitled Orbital Visualizer, which takes in the name of the TLE file within the constructor. So class Orbital Visualizer, and then we can define a constructor which takes in the TLE file name. So first we need to reference self and then file name. Then we can set self.file name be equal to the file name. And once we have that set, it says assign name line 1 and line 2 to empty strings. So here we can do self.name, self.line 1, and self.line 2 to be empty strings. And then we want to create a variable called satellite and assign it to none. So we'll do self.satellite is equal to none. Now that we have the constructor established, we need to create a method within the class titled extract TLE contents that extracts each line from the TLE file, cleans them, and stores them within name, line 1, and line 2 respectively. So let's begin by creating a method, and we're going to call it extract TLE contents, and let's refer to self. And here, let's open up the file. So we're going to use open, and we're going to open up the TLE file name. So it'll be self.filename, and let's read this. So we're going to do it in read mode, and let's refer to it as F. Actually, let's call it file. And in here, we're going to extract the lines from the file. So I'm going to do lines file.read lines. And this will create a list full of each line in the TLE. And let's make sure that each line in the TLE is clean and we can store it within the TLE contents. So that, remember, the first line is going to be the name. So self.name is equal to lines 0. And in order to make sure that it is clean, it doesn't have any special characters in it, we use the dot strip method. And then we can do the same thing for line 1 and line 2. In this case, it's going to be index of 1, because it's the second element, and then the third element. Once you have that, we are tasked with creating another method titled parseTLE that parses the TLE contents from each variable and stores them inside an object that is assigned to satellite. So let's begin by creating a method called parseTLE that references itself. And in here, we can set the satellite number. And let's just start by assigning each variable to its respective value in the TLE. So let's begin with line 1. So here we have line 1, and I can just pretty much use the extractor I created here. So we can do, because these values are going to be the same because all TLE structures are the same. So we can go down here. And we can indent it in order to make sure that this is all within the same method. And instead of line 1, it's going to be self.line1 for each of these values. And then instead of line 2, it's going to be self.line2. Now we're done with that, we can assign it to the self.satellite object. So here we can do self.satellite and set it to a dictionary. And each of these values will be different characteristics. So for name, we can do self.name. And we can have each of the values. So we can do satellite number, satellite number, and so forth. And we can pretty much just follow the outline I specified here for this dictionary object. And luckily enough, our variable names matches with the code here. So we should not have any problems. I'm going to indent inside. And then once we're done parsing this information, we assign it to self.satellite. So this is the parsing itself, where we're extracting the individual values from each of the lines, and then we assign it to this dictionary. We need to also create 2 additional fields within satellite called orbital, period, and semi-major axis, and set them both equal to 0. So let's do that. So in here, we can do semi-major axis for the 0, and then orbital period set to 0. And then it asks us to create a method called calc semi-major, which sets the semi-major axis within the satellite object using self.satellite mean motion. So here we can create a new method, and let's call it calc orbital period refers to itself. And we can take the calculations from before and in this case, we don't have the mean motion as an input parameter, so we'll need to derive it from the satellite object. So in order to do this, we'll do 2 times pi So in order to do this, we can modify this little code here. So let's set self dot satellite, and we want this to be the new orbital period. And this is going to be equal to 2 times math.pi times the square root of the semi-major axis cubed divided by gravity times mass of the Earth. So that will calculate the orbital period of the satellite. The next method we want to create is the semi-major axis calculation. Semi-major, and this will reference itself. And in this case, let's go up here to this code again. We will be using this line, and we'll be replacing it with the values we will be using so here. In this case, it's going to be n is equal to the mean motion, so self dot satellite, and in here we're going to specify mean motion times the rest of this code. And then we can set the semi-major axis and set it equal to this value here. So that we have the converted mean motion, and then we're just feeding it into this equation, which gives us our semi-major axis, which is assigned here. The final method we are tasked with creating is the plot orbit method in order to visualize the orbit of the TLE using PyAstronomy and Matplotlib. So let's create a method, and let's set it to plot orbit, and it's going to refer to itself again. And then in here, let's do a check in order to see if the satellite is defined. If satellite is none, meaning that the TLE contents were not extracted and not set, then we're going to print out a alert message to whoever is using the program and saying error TLE is not parsed. And we can alert them and say, please call the parse TLE method. And we can return out of this function early if this is the case, because we don't want it to run afterwards. If there is TLE contents that are parsed, we can now visualize the orbit. So we can pretty much use the code outlined here in order to do so, but using our own custom values. So I'm going to place in the orbit code here, and we're going to put self.satellite, the semi-major axis. Here's the orbital period. And then instead of data, it's going to be self.satellite for the rest of these things. And we can also put the period here as the satellite's orbital period with 200 evenly spaced items, and then plot the positioning of the orbit. Now we can visualize everything using Matplotlib, using the code specified here. And now we are using a dark background with these plot configurations. And instead of data, it's going to be self.satellite name. And now we can print everything out. Let's make sure these imports are correct. Okay, now that we have no errors, let's make sure that our code works by creating an instance of this class and testing it for ourselves. So I'm going to create a new code cell, and let's call this Visualizer. And this is going to be an instance of the Orbit Visualizer class. And we need to feed in the name of the TLE. So it's going to be TLE.txt, which is the text file here. So we're going to be parsing through this TLE as an example. And once we have the visualizer, we're going to first call extract TLE contents. And then one more time, we're going to invoke parse TLE once we extract the TLE contents. And then once we do that, we can calculate the semi-major axis. And then we can calculate the orbital period once we have the semi-major axis. And then finally, we can visualize everything using the visualizer plot orbit method. So now if we run this, you can see that we get a plot of the International Space Station. And first we extract the contents. So we strip away each line here and store it within their own respective variable names by parsing it. And once we parse it, we first calculate the semi-major axis, which is required to calculate the orbital period. And once we have the semi-major axis and the orbital period, we have the 6 orbital characteristics necessary for plotting an orbit. So we then plot it out using Matplotlib. In this project, we will be creating a solar system visualizer from scratch using Matplotlib, Numpy, and the MPL toolkits libraries in order to create 2D and 3D visualizations of the solar system. So before diving into this project, let's cover some foundational concepts. And we can see that an outline of the solar system is comprised of the following. We have the sun, which is a G-type star that is the central body of the solar system. And we have 8 planets that orbit around the sun, which can be categorized as terrestrial and gas giants. So we have 4 terrestrial planets. They're Mercury, Venus, Earth, and Mars. And the gas giants are Jupiter, Saturn, Uranus, and Neptune. And we have 1 dwarf planet called Pluto. And other things we have in orbit that are also known as natural satellites are the moon. And notable moons include Titans, Europa, and Ganymede. We also have asteroids, comets, and objects within the Kuiper belt. And you can see here is an outline of the solar system alongside any orbital bodies within the solar system to scale. And outlined below, I have a table representing each of the orbital details for each planet. So here I have the 8 planets outlined, and the orbital period in Earth years, the eccentricity, and the inclination of each of these planets. And here is the the data within a list format. So here we import libraries in order to start our visualization. And this is going to be a 2D visualization. And here I have planet names in a list alongside their respective semi-major axes and orbital periods. So Mercury has a semi-major axis of 0.39 astronomical units and an orbital period of 0.24 in years relative to Earth. And since the eccentricity and inclination of these values, you can see the inclination and the eccentricity of these planets are pretty low, very close to 0. We're going to be treating each orbital path as a circle for simplicity when we are plotting this on a 2D axis. And we're going to be using Matplotlib and Numpy to create a 2D visualization. So here we use plt.style.use and we set the background to be a dark background. And here we create a figure and an axis, and the figure size is 8 by 8. And this line up here places a yellow dot in the center. It creates a scatter point, which is just a dot of size 100 with a label of sun. So this will be our central body. So you can see here, this yellow dot is the central body positioned at 0, 0 at the very center. And then here we loop over each of the planets defined up here. And for each of the 8 planets, we get the orbital radius, which is the semi-major axis. And we get the range, which is 0 to 2 pi, because these are circles. And then for the x values, I just multiply the orbital radius by the cosine of theta. And then for the y values, we multiply the orbital radius by sine. And this lets us plot circles representing each of the orbits on the xy axes. And we do ax.plot, the x, the y, and the planet. So for each planet, we're just drawing circles that represent their orbital characteristics using their semi-major axis. And then we plot it out. And then this sets the aspect ratio to be equal. And then we set the x and y axis labels alongside the title and a legend, which is this side box here that shows the lines denoting each planet. And then we set a gridded background to be true, and then finally show the plot, which looks like the following. For the interactive portion of this exercise, you're tasked with plotting orbits in 3D now. And feel free to reference back to the previous lessons in order to help you. And don't feel hesitated if you can't get everything. You can follow along with this tutorial once you try it out yourself. Okay, so firstly, we need to create a figure of size 8, 8 and assign it to a variable called fig. So here we kind of do the same thing, but in this case we're just creating a figure variable. So let's call it fig, and let's set it equal to plt.figure. And the figure size will be 8, 8. And then it's asking us to plot the sun at the center. So remember, we can do this by doing ax.scatter. It's a scatter point, and we want it to be centered at the center. And we want its color to be yellow, size to be 100, and have the label of sun. And then now we're enumerating for each of the planets. And then first we need to create a variable called orbital radius and assign it to the semi-major axis value for each planet. So orbital radius is equal to, I think we hard-coded the arrays here, so semi-major axis and index I. And then let's do orbit theta, as we're assigned here, and assign it to a set of 100 equally spaced values from 0 to 2 pi. So we're going to be using the np.linspace method, .linspace, starting at 0 to 2 times math.pi with 100 equally spaced values. And that will be our range. And then let's create the x-axis list, which will be the orbit radius times the cosine of orbit theta, which represents the x values of a circle. And then the y values of a circle will be the sine of orbit theta. And this satisfies these 3 lines of code here. And then this plots the z direction. And then this will plot everything onto the figure. So now we are tasked with setting the x, y, and z labels. So let's do x.set x label. Remember, this is going to be in 3 dimensions, so we need to set the x, y, and the z, which is the 3rd dimension. So let's do x and AU, astronomical units, and 2 more for the y and the z axes. And then let's set the title. And let's call this Solar System Visualization. And then let's create a legend for this as well. So we're going to do ax.legend. And then finally, we can show everything on the plot by doing plt.plot. And it says math is not defined. Let's make sure we have it imported. Import math. And you can see here we have everything plotted in a 3-dimensional axis. And let's rename these y labels here. And you can see that now we have a 3D display of the different planets in our solar system visualizer. And let's make sure that this is, instead of plt.plot, plt.show. And now that gets rid of our error we had, and it shows the 3-dimensional visualization. In this lesson, we'll be covering FITS files and Astropy. So firstly, let's begin with understanding FITS files. FITS, like we mentioned before, stands for Flexible Image Transport System, and this is a very standardized format commonly used within the aerospace industry for storing various types of data within images, tables, metadata, and so forth. And FITS files are primarily used for the following purposes. They're firstly used for astronomical images captured by telescopes and other instruments. They're also used to store spectral data, which represents the intensity of electromagnetic. In this lesson, we'll be covering FITS files and Astropy. Firstly, let's begin with FITS files. FITS stands for Flexible Image Transport System, and these are files that is very standardized within the aerospace and astronomy industries, and they're commonly used for storing different types of data. And they're primarily used for storing astronomical images captured by telescopes and other instruments, spectral data, which represents the intensity of electromagnetic radiation, usually it's light, as a function of wavelength or frequency, alongside tabular data for specific measurement observations. So a FITS file is segmented into HDUs, standing for header data units. And the first HDU is called the primary HDU, And this contains a data array, typically representing a 1D spectrum, a 2D image, or a 3D data cube. And any additional HDUs after the primary HDU are referred to as extensions, and they contain auxiliary information like image extensions, ASCII table extensions, and binary table extensions. You can learn more about the technical details of FITS files at this link if you really want to get into the nitty-gritty of each of the different data types. So, in terms of obtaining FITS data, there's a wide range of online data sources that publish FITS files for public use, and they can be downloaded readily. One website I would recommend checking out is the SSDS SkyServer website. And this includes a wide range of tools in order to extract FITS files. So this is an outline that's going to help you retrieve SDSS images from the website here, which you can check out if you want to try obtaining some FITS files yourself. And they're typically taken using these types of cameras. So let's do an overview of a spiral galaxy called NGC 1087. And SkyServer has something called an object explorer that allows you to analyze specific astronomical data characteristic for various celestial bodies. So here is an example of one on a spiral galaxy. And you can see here it contains information like the type of object being considered, galactic coordinates. It also has positioning information alongside imagery and object spectra, showing you the electromagnetic output of these things alongside an infrared spectra. Other details include general information about the camera, imaging details, magnitude of different parts of the spectra. So this will be ultraviolet, green, red, near infrared, and longer wavelengths are depicted within the image. There's also uncertainty values alongside miscellaneous observational calculations. Here's an entire informational data set of each of the fields contained within SkyServer if you are interested in learning more. SkyServer also allows you to visually see information about a specific image using the image analyzer. So in this case, we're going to see an image of NGC 1087. You can see here it says the coordinates, and it'll also print out auxiliary information such as the declination, the type, and the different ultraviolet, green, red imagery values depicted here. You can use Astropy, which is an open source Python library, in order to coordinate transformations, do unit conversions, and other astronomical calculations. And in this case, we're going to be using the FITS file handling features of Astropy. So in order to access that, you import astropy.io, and you can import the FITS function from that library. And in order to read a FITS file, here I have an example of a FITS file. So I have multiple FITS files. And let's say we want to read the FITS file for M13, which is a galaxy. We can use the fits.open method and specify the name of the file we want to study. So I have the M13 FITS file here. And I'm going to put it under the alias of HDUL because it will be a list of HDU objects inside of a FITS file. And you can see here when I do hdul.info, it will print information about the FITS file itself alongside the header information. So you can see here we can get the type, the dimensions of the image, the formatting, alongside information about the camera and other miscellaneous information about the FITS file. You can combine Matplotlib and Astropy in order to plot the image of M13. So here we import the libraries. We first import Matplotlib as PLT. We also use the Astropy visualization features and their utility methods. And here I specify the plot style I want to use for Matplotlib, and I imported a specific styling from Astropy to use. Here I extract the imagery data from the FITS M13 FITS file, and I store it under an image file variable. And then here extracts the imagery data from the FITS file itself by feeding in the packaged data file variable. And you can also retrieve information once you get the data from the FITS file. And in this case, this will print out the dimensions of the image. So it's 1040 pixels wide and 1392 pixels in height. And then now we can display the image using Matplotlib. So I do plt.figure, and then I use the imshow method and feed in the image data in order to display the image. And I use this color bar feature in order to create a color bar with the image data. And you can see here, this is a plot of the Messier 13 galaxy using a color plot visualization. This leads us into the first exercise of this lesson, where you'll be visualizing a FITS file. It is going to be this FITS file here, the M6707HH FITS file. And your task is to print out the header information for the primary HDU, print out the dimensions for the image itself, and visualize it. So in order to do this, we're going to first import Astropy. So let's do it from astropy.io, import FITS, because we're going to be downloading data from the FITS file. And then let's import the visualization libraries we'll be needing. So we can pretty much import everything we import here, down here, after we import Astropy. And then let's set the styling to be the same. So we can copy this code in order to have the same styling output. And then let's open the FITS file. So we can do with fits.open. And the name of the file we want to open is this. So we can specify that in there. And let's put it under the alias of HDUL. So now we have the contents of the FITS file accessible to us. Let's print out the information. So hdul.info. And then let's also print out header information. So we can do HDUL. The primary HDU is going to be stored at the beginning. So we're going to do index of 0 and then print out the header like we are asked to. And now if I run this, we get the header information alongside the general information about the FITS file we are dealing with. And then now we can plot the imagery. So first we're going to unpackage the image file. And we can do this by using the get pkg data file name. And in here, we're going to specify the FITS file. And this extracts the imagery data. And then let's get the data itself from the file. So we can do fits.getData and then input the image file. And let's set the external parameter to be 0. And now if I print image data, you can see that we get different values here describing the image. And let's get the dimensions of it. So I'm going to do image underscore data, dot shape, and that will print out the dimensions of the image. So we know it's 1059 by 1059 pixels. And now we can show it in a figure. So we can do plt.figure to initialize a Matplotlib figure. And then let's do plt.imshow and feed in the image data. And then use the color bar method in order to display a visual output of the galaxy. And you can see here, we have a really pretty color bar display. In this lesson, we'll be covering the SPICE and SpiceyPy libraries. So firstly, what is SPICE? SPICE stands for Spacecraft, Planet, Instrument, C-Matrix, and Event files, and these are standardized formats used within space science to represent geometric and positional information about celestial bodies, spacecraft, instruments on board spacecraft, and events in a mission or observation. We typically see this used for NASA missions. And the categories of data included within the SPICE file format are as follows. We have the ephemeris data, which describe positions and velocities of celestial bodies like satellites. We have coordinate systems. Different measurements have different coordinate systems depending on the mission itself, whether it's planetocentric, spacecraft relative, and so forth. Instrument geometry. These describe geometric characteristics of various spacecraft instruments, such as the field of view, focal length. And then finally, we have event times, which are timestamps related to significant mission events. SpiceyPy is a Python library wrapper for SPICE, which provides Python bindings to the SPICE toolkit, which was originally written in 4chan. But this allows us to use Python to access the powers of SPICE. So we can import this by doing this import statement here, and then we can import it under the SPICE alias. And now we can print out the toolkit version by using this method, tkvrsn, and then passing in the toolkit. And this will print out the toolkit version we are dealing with. And now we'll be doing an interactive step-by-step visualization of the Cassini trajectory. Cassini is a spacecraft that was built by NASA, which orbits around Saturn, and it carries a suite of scientific instruments designed to study the atmosphere of Saturn, its magnetic fields, rings, and moons. In order to do this, we're going to first have to load up a kernel, and a kernel is a file containing various types of data used within the SPICE toolkit in order to perform calculations and simulations related to space missions. Kernels can come in different formats, such as a text-based binary, a meta-kernel, or just a binary itself. And in order to set up the kernel environment for a project, we're going to be using the following kernels. So make sure, if you want to follow along with this, you have the following downloaded. And all the kernel specifications needed for a project can be specified within a text file. In this case, it's within the castmetak.txt file. Here I have all the kernels downloaded in this folder. So in order to read SPICE files, we'll need to use the furnish function, which allows us to load a meta kernel. So in this case, I want to include the meta kernel called castmetak, which is inside of a text file. So I use the spice.furnish function to do that. And here's a code snippet example that converts datetime strings into ephemeris time. So there's different time references, and one is datetime and one is ephemeris time. So this allows us to convert between the two. So I have str to et. So this takes in the first UTC datetime, which is a datetime string, and converts it into ephemeris time. And this one just goes to the second one and converts it to ephemeris time. So now we use this print statement to print out both of the ephemeris times relative to the date string here. This code below generates time values, so each ephemeris time value in the list corresponds to a specific time point within a time interval, and this calculates the ranges between the times. In order to compute the position of the Cassini spacecraft at multiple time points specified by the times variable, so these are the time points we're going to be dealing with as the Cassini moves over time. So what this does is it takes in the name of the spacecraft, so in this case Cassini, the times, the reference frame we are dealing with. Reference frames are specific ways to keep track of positioning, and we're going to be using a J2000 reference frame, and then different flag values alongside the observer location, and this will give you an output of positions and light times for the Cassini spacecraft, given these characteristics. So here we get the positioning and the light time. Once you're done doing any calculations with the SPICE toolkit, you need to make sure you clear up the memory in the kernel and reset the kernel state, and you can do so by using the kclear method, which will clean everything up. And now that we have everything calculated and saved within variables, so in this case I have positions and light times, we can finally plot it out using Numpy and Matplotlib. So here I convert the list of positions into an array in order to make things easier for indexing, and then I create a figure of 9x9 size with a 3D projection using Matplotlib, and then I print each of the positional axes. So I print out the X, the Y, and the Z, and then I put a title on the graph and show it. So here, let's make sure we have everything imported. So do import numpy as np, import matplotlib.pyplot as plt. And now you can see here we have a 3D positioning visualization of each of these values. And you can see here over time, these are the different positions the Cassini spacecraft has orbited. In this lesson, we'll be covering Skyfield and JPL horizons. Firstly, Skyfield is a Python library for astronomical calculations. It provides high-precision ephemerides, which are predictions of celestial positioning and motion for various celestial bodies such as planets, moons, and stars. And you can see with Skyfield, you can create very intricate astronomical visualizations like the following, which visualizes various constellations on a polar coordinate graph. And JPL Horizons is an online service provided by NASA JPL that allows users to access ephemeris data for solar system bodies. So this will provide positioning information for various bodies within our solar system. And it's usually within a tabular format, including relevant timestamps. You can learn and obtain the latest ephemeris data by visiting this Horizon Systems webpage, and usually they have it stored within their small body population searches. You can also access it via its different interfaces here. In order to import the JPL Horizons dataset using Python, we can use AstroQuery. So here I import from AstroQuery JPL Horizons, the Horizons method, and in here you can obtain specific ephemerides data for a celestial body with the following specifications. So in horizons, you can specify the ID, which is the target celestial object. So I just picked 3552. The location, which is the observer's location, so 568, as a hard-coded value, and then epochs. And epochs stand for like timestamps, and this specifies the time range and time step you want to retrieve the positioning information. So I step is 1 year, I start at 2020 February 10th and stop at 2022 December 31st. And the ephemerides method extracts the data, and we can print it out here. And you can see this will give me the target name, the date string, alongside other information such as the degrees. This brings us into the first exercise, where you're tasked with using the horizons function with an astro query in order to obtain the ephemerides for a comet named Eros relative to the sun from 2020 to 2022. In order to do this, let's begin by first importing astro query, so we can pretty much copy the same line here in order to import the horizons dataset. And then now we can follow the same line of logic for this object, but instead of this ID, we're going to use the ID for the comet Eros, which is 433. And then it needs to be relative to the sun. So the ID for that is specified here as 500 at 10. And it starts at this date, which matches, and stops at 2022, December 31st, with a 1-year step. This will extract the ephemerides, save it into a variable named f, and now if we print it out, we get the information for the Eros comet. You can create your own sky map using the Skyfield library. So here you'll need the following features from the Skyfield library, alongside the following from Matplotlib in order to create a visual. First thing we need to do is load the data from Skyfield. In the following, we use the load function to import the ephemeris data for DE421, which is one of the most accurate ephemeris models available. And here I just specified a relative timescale using UTC time alongside my lat-long geocoordinates. And by using the load method, we can load in the ephemeris data for DE421, which is saved in the .bsp file here. So if I go here, you can see that I have a BSP file that's containing that location information. And within the data, I want to specify a specific planet I want to focus on. So I choose Jupiter by indexing out the Jupiter barycenter. The barycenter is the center of mass for a specific celestial object. So we begin at Jupiter, and then we also store it in Earth by specifying the Earth barycenter. And then here we obtain the ephemeris data specifically for Jupiter at the timescale specified here. And now we can obtain the data by specifying this URL and then loading in the data frame in order to obtain the data. Let's first import this. Another important concept to know is observer and positioning. So you can define an observer variable using our geocoordinates within the world geodetic system, and that's a reference frame system. And then we can specify a very specific point in the sky relative to an observer using the elevation angle, which is the vertical angle, so it would be like this vertical angle here, and the azimuth, which is the horizontal angle, which would be this angle here. So here we set the observer, we use the world geodetic system and specify the observer coordinates with latitude and longitude at the time point. And then from there, we can extract the position in the sky the observer will look at. So here we use observer from alt as, and we specify the elevation degrees and the azimuth degrees in order to specify the angles of the following two values. And there, we can specify the center of observation, and we center it at a star, specifying the right-eye sensation and the inclination of the target we are looking for. And once we have that, we can find the position of Jupiter relative to Earth and develop a 180-degree projection. So we get the position of Earth at the time frame, and then we observe the object, in this case Jupiter. And then from there, we develop a projection with a field of view of 180 degrees. And once we do that, we calculate the position of the star over at the specific time stamp. So here we do Earth at T, we observe different stars. So this will allow us to map out projections of stars. And then we get the X and Y values of the stars within the projection by using the projection method and then plotting the star positions. And then now we can configure the graph values. So I set the chart size to 10, the maximum star size to 100, and the limited magnitude to 10. And then I create a filter here that uses a conditional and only allows stars of a specific magnitude to show up. So stars with a magnitude of less than 10 will not show, only greater than 10 will show up in the projection. And this gets the relative magnitudes of the stars. And then the size of the star will be calculated depending on the magnitude of brightness. So this is the calculation here. As the magnitude gets bigger, so will be the size of the star. And once all these calculations are done, we can visualize everything using a Matplotlib subplot, setting the figure size to the chart size specified here. So it'll be 10 by 10. And then we create a border, which is a circle. And then each star will have a point, which is a white dot in the graph. And then we create a horizon visualization. And then we set limits for the X and Y ranges, title the plot, and then show it. And now you can see here, we have a sky map projection of the Jupiter barycenter relative to an observer's geocoordinates. And you can see here, we have white dots representing each of the stars the observer can be looking at using Skyfield. And these star magnitudes were calculated here in this marker size variable, and each of them are represented by points. They're plotted here. In this lesson, we'll be covering how you can use Utils and SpecUtils. Let's begin with Utils. Utils is a library written in Python for performing photometry, which is the measurement of the intensity of light emitted or reflected by astronomical objects. It provides a range of tools for detecting and measuring these sources, and you can learn more about it on their website here. So first, we'll begin with detecting a source using Utils. You can see from here, we import various libraries. Begin with Astropy. We import the fits, units, CC data, and statistic methods. We also import a handful of visualization methods alongside Matplotlib and the Utils library itself. We import background 2D and mean background. So we begin by retrieving a FITS file. So here is a link to a FITS file, for example, and we open it using the FITS tool. And right now we're just printing out information about the HDUs alongside any data stored within the primary HDU alongside header information. And you can see here if we print out this will import everything and then print all the information out. So we can see it's 5250 by 5250 pixels large and other auxiliary information here. Now we'll be plotting a source detection plot using the libraries. So here we specify the unit, and this creates an image of CC data, including the data in the FITS files. And we configure the header and the masking information. Then we create a figure using subplots from Matplotlib. And then we create a normalized image from the FITS data. And here we set the image normalization configurations. And then we set the styling to be Verdis. And then we set the overlay and the underlay colors. And then we set the masked data to be configured to look like white. And then we clip the image to plot with a logarithmic stretch value. And this is where we plot all the masking information. So we have the normalized image, the CMAP image, alongside the clipped image and the general masked image. And then we define a color bar in order to show the image flux using color. And then we set the labels to be the y-axis. And then we plot out the flux count rate and set all the labels as such. So now if I run it, this will print out a normalized mapping image of this FITS file here. There we go. So you can see the flux. Flux is the luminosity of each of the stars. So as it gets more luminous, it'll become more yellow, and as it gets less luminous, it'll become more purple. We can also do something called aperture photometry using Utils. Aperture photometry is a technique used to measure the flux or the intensity of an object in space by calculating its pixel values within a specific region. So what it does is it gets the central aperture, which is this circle here, and then the nullus, and using the pixel calculations of each, it will get the flux or the intensity of a star. This leads us into the first exercise, where you are tasked with using Utils for aperture photometry. And first, you need to use the circular aperture class from Utils in order to extract relevant details, such as the area, center coordinates, and create a visual plot using Matplotlib. So let's begin by importing the following. So first, we need to import Matplotlib pyplot, and then let's put it under the alias of PLT. And then we can import from the datasets of Utils, import the Gaussian image, and then from Utils we can import the circular aperture and aperture statistics. And we can use a comma in between. So this will import everything we need. Then now we need to initialize the dataset. In order to initialize the dataset, we can just use the make for Gaussian image function and then invoke that. And then we can create a variable called aperture and set it equal to circular aperture. And this is going to be positioned at 150 pixels by 25 And then we can have a radius of 8 pixels. It also asks us to obtain aperture statistics. So I'm going to name this statistics. And I'm going to set it equal to aperture stats and get the aperture data here. And then the aperture itself will be the second parameter. You can learn more about circular aperture and aperture stats by following these links respectively. The next step is to visualize it using Matplotlib. So let's create an 8x8 figure. In order to create an 8x8 figure, we need to use PLT figure. And then at the fig size will be 8x8. And then we can show the data, so plt.imShow. And then data, and then let's set the CMAP to be equal to gray. And then we can plot the aperture by stating aperture.plot. And inside there, we can set the color to be blue and LW to be 1.5, like specified above. And then now we need to create a color bar. So do PLT color bar. And inside these parentheses, we can set the label to be counts. And then it asks us to create a title for the plot. So let's call it circular aperture image. And then finally, we need to show the plot itself. So plt.show. And you can see when we run it, this shows an image in the background that we got from here. And what it does is it creates this aperture, which is this circle here that we defined here. And it overlays it in front of the image. Now we can get details about the aperture statistics. And firstly, we can get the centroid, which is the coordinate of the center of mass. So we can do that by printing out centroid. And then here we can do statistics dot centroid in order to get access to it. And then let's do the same thing for the rest of these values. So the second thing is bounding box. And this will be bbox. Third thing is the sum. And we can access it with the sum property. Fourth thing will be the standard deviation. And then the number of apertures, which is n underscore apertures. And then the median. And finally, the eccentricity. Apertures. Now will give us all the aperture statistics, including the bounding box, the sum of unmasked data values, standard deviation of the unmasked pixel values, and the rest you can read up here. This brings us into SpiceyTils. SpiceyTils is a Python library for spectroscopic data analysis in astronomy, and it provides a set of tools for working with spectroscopy data, which is the measurement of light intensity as a function of wavelength and frequency, and this is a great audit for analyzing stars. So firstly, what's spectroscopy? Like I covered before, it's the study how different materials interact with light across different wavelengths, And by analyzing how light is transmitted, reflected, and absorbed against a specific surface, you can obtain a general gauge as to the composition and structure of the material. All spectroscopy images are visualized along a spectra. A spectra is like a little graph like the following, which represents the intensity of light at different wavelengths across a specific image. So here we have different wavelengths on the x-axis, and on the y-axis we have the intensity. So here we know the blue stars have the highest temperature, followed by yellow stars and red stars. And where they fall on the wavelength determines their color. So ultraviolet and blue is more to the left, as you can see here. So blue stars are more to the left of the graph, while yellow is more near after 500 in wavelength, so they'll be in the middle, and then red we have near like 750, so it'll be more skewed to the right of the graph. And this determines their spectral type, so we can see that the blue star is the spectral type of A, spectral type of G for the yellow star, and M for the red star. We can create our own visualizations to plot our own spectra and create a fitting model to best represent a spectra using a function. So here I import all the libraries we need to do this. I import Numpy, Matplotlib, Astropy, and SpiceyPy. So first we can import that. And then here, this creates a random spectra. So it will create a graph kind of like the following, but very randomized. And I do this by using the np.random.seed. This configures the seed or the configuration of the randomness. And it just predetermines what kind of random behavior we want to set. And then here, I create a linspace method. So it's going to be 0 to 10 with 200 evenly spaced items. And then this will be the plot of a random spectra. This is going to be an exponential graph. And then I add a normalized random shape to it. And then finally, I initialize the spectra using the Spectra 1D method and feeding in the flux values alongside the spectral axis values. Once we've calculated the random spectra, we can fit the flux values and fit the spectra using a Gaussian one-dimensional model. So here I get the Gaussian 1D model with an amplitude, mean, and standard deviation. And then I fit it using the fitlines method by passing in the spectra and the Gaussian distributed model, which predetermines how we want to fit these flux values along the spectra. And then this gives us the output of the y-axis values by running the Gaussian fitted method. And once we've done the fitting with the Gaussian 1D model, we can plot everything out. So I plot the x and y axes and label it the original spectrum. And then the Gaussian fitted spectrum is the fitted model, which does like a best fit of the original data. So here, and then here I give it a title and a grid background and a legend. So when I run this, you can see the Gaussian model is the model we use to fine tune and get a best fit. And this is depicted in orange. And then we have the random code we wrote up here, which gives us this like spiky little graph for the original spectra. So this is how you would fit a spectra using SpiceyTils. And there's also different types of fittings. One special type of fitting is called a continuum fitting. And a continuum fitting is a technique used in spectroscopy to model and remove background noise from a spectra. So here you can see this is a continuum fitting model, and you can see as we get closer to the center, near like the origin of 0, you have a lot of this like background noise, which will prevent you from finding a best fit line. And in order to remove this, you can use continuum fitting in order to get a more focused spectroscopy on it. So this leads us into the exercise where you will be tasked with creating a generic continuum fitting using fit generic continuum from SpiceyTils and visualize it using Matplotlib. So let's begin by importing everything we need. First, we can copy all the baseline methods here. So firstly, We have Numpy. We also have Matplotlib. We have models from Astropy. We have units under the alias of U for the units. And then Spectrum 1D, it also asks us to import spectral fusion from SpecUtils.spectra. And then fit generic continuum. So instead of fit lines, it'll be fit generic continuum. And then this step will generate a random spectra for us to model. So it's going to do something like this, where it creates this like jagged little randomized spectra. And then this is where the code really happens. This is the continuum line, which tries its best to model the spectra that is outlined here, and then creates the Y values. And then finally, we need to create a model spectra using Spectrum 1D. So first, we'll need to define these values. So I'll call this spectra. And we can set it equal to Spectrum 1D. And inside, we can specify the flux. And this is going to be y times u.g jy. This is the units, because we specified units as u. And then this will put the y as the flux value. And then alongside the spectral axis, the axis will be the x values. So I'm going to comma here and then specify the spectral axis with these units. Once we have that, we can define a continuum fit and set it to be the fit generic continuum output of spectra. So let's call this, and then let's invoke this method. And inside here, this takes in the spectra. So this will create a best fit model for the spectra we have. And then let's get the y values of this continuum fit. So y continuum fit is equal to g1 fit. And inside of here, we're going to do x times the units. I think we also need to import g1 fit as well. Oh, instead of g1 fit, it is going to be continuum fit. And this will create a continuum fit y values that are stored in this variable. And then finally, we can visualize the spectra using Matplotlib. In order to do so, let's first create a subplot. We can do this using the PLT subplots feature. So here we can specify the figure and the axes values, and we can set it equal to plt.subplots. And then we can plot the values, so ax.plot, feed in the x and y values for the random spectra. And then now we can do the continuum fitting x, and then we can fit in the y continuum fit variables. And then now we can set the title. And then set the grid background. And then show the plot. And you can see we have the randomized spectra here, and then we have a continuum fitting that cancels out the background noise here. You can see it doesn't do the best job, but for the first continuum fitting, it's not terrible. In this lesson, we'll be covering datasets for astronomy and aerospace. So there are many sources for reliable data sources for aerospace-specific applications, and in order to vet these sources, ensure they are reputable and validated by experts. Here are some reliable datasets you can include within your applications. Include the Astrophysics Data Facility, the NED, JPL Horizon Systems is really good alongside NASA's Planetary Data System. And here are some lists of reliable datasets you can use. So, in order to get access to online astronomical databases and archives, users can query and retrieve data from APIs. And one library in order to help you access online data is called AstroQuery. And this allows you to pretty much get data from any data source without having to figure out the way to do it yourself. So this consolidates a lot of the data archives and data collections of various accredited institutions and streamlines it so you can easily get access to it. So let's use AstroQuery in order to get data from the ESA Sky database. So first you'll need to import the ESA Sky method from the ESA Sky module of AstroQuery. And then I import the units method here. And in order to see the catalogs, the different types of data within the ESA Sky database, you can do the list catalogs method and print it out. So here we can see all the catalogs. It's first going to be fetching the data, so it might take a few seconds, but it should print out the list of catalog options. And you can also see a list of all the available mission maps by using the list maps. So this will print out all the missions and the maps you can utilize. You can see like James Webb Space Telescope, mid-infrared, we have Herschel, Spitzer, so forth. And you can also obtain maps for specific regions using the query region maps. So I use the ESA Sky query region maps, and we can specify the positioning. So let's say I want it to be centered at Messier 51. You can also specify the radius using proper units, and then figure out which missions I need to find. And in this case, it can be any region within any mission. So if I print this out, it's going to take a few seconds. While that's running, you can also fetch spectral data using get Spectra. So let's say you don't want to create randomized spectras like we were doing in the previous episode. You can get your own realistic spectral values using the AstroQuery package. So here from the ESA Sky database, I call get Spectra, and you can just specify the position of where you want to get the spectra. So I put in this position in the universe. I set the radius to be, oh nice, and here we get the region maps for each of the different positions within Messier 51 with a radius, confined within this radius underneath any mission. And this will give you a table list for each mission that fits this query. Moving on to here, we specified only 2 missions this could be part of, Herschel and XSM Newton, and then this will print out any spectra values associated with that. Now that our data is downloaded, you can see the spectra information. We just have a bunch of HDUs for each red, green, and blue value. This leads us into the exercise of this lesson, where you will be gathering data from the ESA James Webb Space Telescope archive. If you want to read more about the ESA James Webb Space Telescope archive dataset, you can visit this link, and this will outline all the methods you can use and general description of the mission. From here, you can see that it's studying the birth of stars and protoplanetary systems and the origins of life by looking at the end of the Dark Ages, the assembly of galaxies, and the birth of stars and protoplanetary systems. So let's begin by creating a cell here, and we're going to be installing the AstroQuery ESA, and then in here we're going to do James Webb Space Telescope, and we're going to import JWST from that. And then now we can import Astropy.units as U. And then we can import SkyCoord, import Astropy.coordinates, import SkyCoord. And once we have all those things imported, we can get a status message from the James Webb Space Telescope in order to make sure that our data is properly downloaded. So I can do jwst.get status underscore messages. And it looks like we're not getting any status messages, but we should be okay in order to use the data. So let's create a new cell, and here we can specify the coordinates using the SkyCoord feature. So SkyCoord, and in here we can specify a right ascension of 44, a declination of -10, units of these values, u.agree, u.agree, and then finally a reference frame. So I can use the standard ICRS reference frame, which specifies how we look up into the air. And then once we have that, we can set the width. So the width is going to be equal to u.quantity. And then inside u.quantity, we can do 5 and specify the units. And then I could specify the height as well. And now that I have that, we can get the result of this, which is going to be JWST, and then we can do query underscore region in order to query the region, and we can set our coordinate points for this query to be equal to the coordinate values we set before here, and then we can pass in the width to be equal to the width, and we can also pass in the height. Now, if we print the result, we get the following output, which gives us the result distances and other values associated with the region being queried. And one last final thing we're going to be doing is getting the product list. So let's create a variable called product list, and let's set it equal to the James Webb Space Telescope dot get product list method. And here we can specify the observation ID. And this is going to be this ID. And now we can finally print it out in order to get a result. And you can see we get all the product list outputs from the James Webb Space Telescope observation here. In this project, we will be creating a satellite tracker from scratch that creates 2 visualizations for satellite tracking, and we'll be using data sources like SatellitTrack in order to gather TLE data that's going to be fed into our program, visualize it using a 2D visualization of the satellite's ground track alongside a polar coordinate plot of the satellite, and we will be utilizing libraries such as Skyfield, Numpy, and Matplotlib. So before we get into the project, let's cover some foundational concepts we'll need to know before we get into the code. Firstly, we need to understand what a ground track is. And you can think of a ground track as a path traced by a satellite as it orbits the Earth when it is viewed from this 2D surface. So you can see here we have 3 different ground tracks. We have the red one. We have these 2 red lines, which are the ground tracks of SC1, the satellite here. And then we have this green ground track, which is the ground track of the second satellite. And this ground track pretty much tells you different orbital characteristics of the satellite, because different orientations of a satellite in orbit will affect its ground track, and also coverage areas. It'll also tell you about the application of the satellite, because internet-based satellites will probably need to have more coverage than, let's say, like remote sensing satellites that's orbiting around a specific point. So ground track really depends on the mission at hand. 2 other things are azimuth and elevation. In the context of satellite tracking, the azimuth and elevation are 2 angles used to describe where a satellite is in the sky. So here we have the azimuth, and if we zoom into this drawing, the azimuth you can think of as a horizontal angle. So we have the observer right in the dead center of the plot, and then the azimuth is from the reference 0 north all the way up to the angle of the satellite. And then we have the elevation, which is the vertical angle. How many degrees is it up in the sky? And the point of knowing the azimuth, elevation, and the ground track is so we can check for passes. And when we're thinking in terms of satellite tracking, a physical pass is considered when a satellite is visible from your location. So if you look up in the sky and you can see the satellite, that will be a visible pass. There's also something called radio passes. Radio passes is when a radio source can detect for a satellite. And you can most often see a satellite pass through a visual pass by using the azimuth and elevation values that I listed above. And mathematically, it is considered visible if its elevation angle is above a specific threshold. Usually it's like 5 degrees above the horizon. So this brings up polar visualizations, and this uses the polar coordinate system with the observer's location at the center. So in this case, the observer would be dead center, and it uses the azimuth and elevation angles to plot the satellite passes relative to the observer. So here we have these blue dots, which indicate positions the satellite has gone in the sky, and we have this, which is the azimuth angle, which goes greater as we move clockwise, and you can see different points as the satellite moves through the sky. So in order to create these effective visualizations, these ground track visualizations, we can use a library called Skyfield alongside a few other ones. So here I import FM, which stands for ephemeris, and this is going to allow us to download ephemeris data, Matplotlib for our visualization, datetime for datetime conversion, and then we're going to be using UTC from Skyfield. So I'm going to import that. And then secondly, we need to define the TLE data. So we're going to use the TLE, which is the positioning characteristics of the International space station. So here, I just load in the TLE from this dataset from Celestrak. If you go to this link, Celestrak has a ton of different TLEs from different satellites, and the first one up here is the TLE for the International Space Station. So what this does is it loads in that data, and then it gets the specific International Space Station TLE, and if we print it out, now we can move on to creating ground track visualizations using Skyfield. Firstly, we'll have to initialize all the libraries required to create the visual ground track. So firstly, I'm importing FM in order to get access to ephemeris or positioning information. We have Matplotlib in order to create the visualization itself, datetime in order to run date and time operations because we're going to be dealing with timestamps. And then from Skyfield, we're going to be importing UTC load, which is going to help us load the TLE file to process, and topos. So first, we begin by defining the TLE data. So if you remember what a TLE is, a TLE is a data standard used to describe the positioning of a satellite. And here, Celestrak has a wide range of TLEs for different satellites. And we're going to be dealing with the first one, which is for the International Space Station. And this is the relevant orbital details for where the International Space Station is currently positioned above me. So this loads all that data in, and then it specifies that it only wants the International Space Station, which is the top one. And then if I print it out, we get the catalog information for the International Space Station. And then next, we need to specify the time range we want to pay attention to the satellite. So we can do this by using the load method to create a timescale. And in here, I specify the amount of minutes I want to be monitoring for the pass. So range takes in the minutes, so I specify 60 times 2, so this will be measuring for 2 hours. And then I convert it to UTC time using the timescale feature. And here I specify the date, so it's 2024. March 21st, and then I put in the minutes to be monitoring the satellite. Once we have the timescale specified, we can keep track of the satellite positioning at each timestamp. In order to do so, I create 2 empty arrays in order to keep track of altitude and azimuth as the satellite moves through the sky. Then I iterate over the time range method, which gives us each timestamp for where the satellite is positioned in the sky. And for each timestamp, I get the positioning information of the International Space Station relative to the observer, hence the minus sign. And the observer is Port Hedland. It's a random spot I picked, which has these geo-coordinates. If you would like to pick a different observer, you can go to something like Google Maps and find the geo-coordinates and input it here. But for now, I'm using this as a reference, and this gets the satellite information relative to the observer, and then it gets that information at that specific timestamp at t, which we're iterating over. And from this orbit object, we can extract a lot of pertinent positioning information, such as altitude, azimuth, and the distance, by running the altes method using dot notation. And then I append these values to the empty arrays I initialized above by using append. So I do altitudes.append, altitude.degrees, and azimuth in degrees as well. So now if I print out altitudes and azimuth, you can see that these arrays are filled with azimuth and altitude values. Lastly is creating the figure itself. In this case, I created a 10 by 5 figure, and I'm plotting the azimuths and the altitudes. Azimuth is going to be on the x-axis, and altitude is going to be on the y-axis, using these little dots as markers with a dashed line style. I title the graph as Satellite Pass ISS. I label the X and Y axes respectively. I put a grid in the background, and then I finally show the plot. So here we get a path, kind of like a little ground track of the International Space Station over the sky with azimuth and the altitude. Let's say you wanted to create a polar plot like this one here. In order to do so, we'll be using the Skyfield library once again. So here I import the Skyfield API method, and then I import time zone from another library here, and then I lastly import Numpy. And then here I configure my time zone to the time zone I live in. I live in California, so it's Pacific time. And then now I access the TLE files using the Skyfield API library again, and I use the same TLE file from Cellestrack, the one here, and I extract the same information from the International Space Station, and once again we can print it out in order to get the proper catalog information. And then here I specified the time range of the paths I want to be monitoring. I want to be monitoring on March 21st, 2024, so I specified March 21st, 2024, and I want to be monitoring for 2 days. The calculation for this is 60 times 24, because there's 24 hours in a day, and then we want to do it for 2 days, and then I invoke timescale here in order to convert this time range into UTC time. And once we have all that information extracted, we can obtain the relative orbital details using the altis function again. So here I specify the geocoordinates of the observer. I'm using Port Headland again, and then I get the characteristic orbital detail information of the ISS relative to the observer at the time range I specified. And then by using the altis method, I can extract the altitude, azimuth, and distance from the orbit. And then I just print out these values below. And you can see here we have 2880 values within the altitudes list, and it contains general positioning information alongside distances as well. And in order to check for a visible pass, again, I mentioned that there needs to be a specific criteria that is met in order for a pass to be considered visible. And in this case, we're going to consider a pass to be visible when the altitude in degrees is greater than 0. So it does this, and then it gets the indices of the result by running the non-zero method. And then finally, I use boundaries in order to get the differences in these visible pass values, and then I run non-zero again. And holistically, what this code does is that it is used to identify places where the satellite is visible and where its visibility status changes boundaries based on its altitude value. So like where it changes and where it is visible. We will need to reorganize the data for boundaries, because if I were to print out boundaries right now, we have this list that is outputted. And what this code block below does is that it reorganizes the data to be in pairs. So it will organize these into pairs, these into pairs, these into pairs, and so forth. And it does this by specifying the start and end indices to make sure it's even, so everything has a pair. And then it reshapes the data using the reshape method. It passes in the length of boundaries, slices it in half, and then makes groups of 2. So now if I print it out, whoops. If your data is already even, I think you just can Okay, I just had to do a little bit of finessing here in order to make sure the values matched. If your data is even or odd, just make sure you can remove these values or add these values as necessary. But the point of this is to create pairs of values that we can match, and the first value represents the index of time where the satellite becomes visible, and then the ending value represents the time where the satellite becomes invisible. So this will be the rising and this will be the setting time. So now we just need to convert these values into the time zone value, because right now they are in UTC and not all locations use UTC time. For example, my location uses Pacific time, it does not use UTC time, so a person using this application from where I live would be confused. So in order to convert this to from UTC to Pacific time, we'll need to write some code. So here, this sets the value to any index from 0 and represents the pass we want to observe. So here we select a path. So right now we have a bunch of passes with different rising and setting times. And let's say I just want to observe this pass here, because all these are passes. I just want to observe the first one. So I just set the index of the pass I want to observe, and then I get the value of it. So this will get 93 and 100. So I extract these values, so rise and set. Rise will be 93 in this case, set will be 100. And then here, I just convert the time zone to my time zone, and I just get the time range here. And this prints out the rise and set information. Finally is visualizing it on a polar plot. This code here creates a subplot with the polar projection. I title it as ISS Pass Polar Chart. And then here I create the circle shape with specifying the theta directions alongside different locational values. And this is where the math happens. We get the azimuth and radians. Theta is going to be the azimuth pretty much. And the radius, how long the line is going to be the altitude. So we can account for both values to track the satellite and visualize it. And then here I plot the azimuth from rise to set. So it will go from here to here from azimuth values, which will be angular. And then the radian is the altitude. So you can see it pretty much stays at the same altitude because the radius doesn't change from the center of the circle. But the azimuth does change. And here I just loop over everything. And then for each timestamp between rising and setting, I plot the points here, and I get the text, which is the text above each dot, by getting the time range values, converting it to the time zone, and then formatting the string to show the hours and the minutes of the pass. And then finally, I plot the text for the timestamps. And that results in this little nice graphical chart here, showing the rising and the setting of the International Space Station pass on March 21st. In this lesson, we'll be covering the foundations of plotting in Python. So firstly, we'll be plotting mathematical functions. And this involves using libraries such as Matplotlib in order to create graphical representations of mathematical relationships. And in space, this could involve modeling physical phenomena. This could include things like orbits, trajectories, celestial dynamics, and much more. So firstly, we're going to begin by importing the relevant libraries. You'll be needing Numpy and Matplotlib, so I import them here. And then we need to create a function that shows a mathematical function. So here I created a function called f that takes in a input of x and returns the sign of x using the Numpy library. Here I generate x and y points. The x range is going to be from -2 pi to 2 pi with 100 equally spaced values. And the y value will represent the sign of values from -2 pi to 2 pi. And then now I plot it using Matplotlib. I plot the x and y values respectively. I label the graph as sign of x, set the color to blue, make it a solid line style, and have it of a width 2. I plot the x and y axes as x and y. I title the graph plot of y is equal to sign of x, and I finally show a legend of the line. As you can see here, here's my sine wave plotted on this graph. You can also plot more realistic values. So for example, you can plot aircraft telemetry, and in the real world, aircraft telemetry is extracted from a system called ADS-B, standing for Automatic Dependent Surveillance Broadcast, which is a universal system for obtaining aircraft values such as airspeed, altitude, and more. So in order to do this, I first import two libraries. I import JSON and Matplotlib. And once that is imported, I open up a JSON file. So here I have a JSON file. A JSON is a structured data file. And you can see that Jupyter Notebook already visualizes it. And ADS-B has these kind of values. An iCal is an ID for an airplane. You can also have different trace items. So here has different telemetry values like airspeed, altitude, geocoordinates, and so forth. So what this code does is that it loads in that data and references it as file, and then it stores that data in the data variable here. So now that we have the data, we can filter through all the flight logs that contain valid JSON data. And the way we detect for this is by checking the index 8 and seeing if there is an object present. So I create a list of filter data, and then I go for all the aircraft in the dataset, and it checks if the property of index 8 is not equal to none, meaning there's something present. There is something present, it adds it to this list. This is something that pertains specifically to this dataset itself, so don't feel like you need to know this. But if you can see here, this will print out, filter data will include data for all the different types of aircraft. So let's say I just wanted to look at the first aircraft being monitored. I'll just put in filter data 0, run it, and you can see we have all this information that we've extracted, such as the heading, the roll rate, if there's an emergency, category of the airplane, and so forth. You can also display specific aircraft data. So here I get the 8th aircraft being monitored, and I mentioned the flight name by getting the flight attribute from this property. We're accessing 8 because here you can see the beginning has these random numbers, but this part has an index of 8 and contains all the information within an object. You can see by these curly braces about the aircraft we're dealing with, so that's why I have 8 here. And this gets the flight attribute, and then it says aircraft is TAS. This stands for true airspeed, knots, and it prints it out. And you can see that here. So we are dealing with flight QTR524, 52F, and the airspeed is 494 knots. So looking a little bit more into ADS-B data, this following table displays the information contained within the fields of ADS-B messages. So here we have the ICAO 24-bit address, we have the call sign, country, time position, latitude, longitude, altitude, velocity, vertical rates, so forth. And we can choose a specific ADS-B field that we want to plot over time by monitoring how it changes over time. So in this case, let's say we want to see how the true airspeed of an aircraft is changing over time. So here I create an empty list of airspeeds, and I loop over the data, and I check if there is a true airspeed value in the aircraft data, and if there is a true airspeed value, it will append it to this airspeeds list, and I print out the first 5 values of the airspeeds list, and you can see that how it changes over time. Currently it's pretty unstable flight because it has very little variance. And now we can plot our airspeed values using Matplotlib. So I do plt.plot airspeeds, which contains a list of the airspeed. I set the X label to be the data point, the Y label to be airspeed. I title the graph aircraft airspeed, set a gridded background, and then finally show it. And you can see how the aircraft airspeed changes over time. This leads us into the first exercise, where you are tasked with creating a spacecraft thruster telemetry visualization. So your task is to read over the spacecraft thruster.csv file. So in here, we can see this is a CSV file. This is another data format used to contain data. And you can Google yourself how you can read over a CSV file or refer to previous lessons. And you can see here we have like this tabular display with rows and columns, and it has time, thrust values, anomaly codes, and so forth. So you need to make an array titled thrust values that contains only the thrust values for each row, and then plot the data using Matplotlib. So let's begin by first running over this import code here. We're importing CSV in order to get data from the CSV file, Matplotlib, and datetime. Let's create a new cell here in order to start writing our code. So let's begin by initializing our thrust values array and making it into an empty array. We'll also need to track time, so we'll make time values, and I'll send it to an empty array. And then now let's get the data from the CSV file, so with open, and I'm going to be referring to this location here. This is because lesson 1 plotting.ipmb is in the same folder as the CSV file, so I just do /, and then I'm going to type spacecraft thruster, which is the name of the CSV file, .csv, and we're going to be reading this file, so I'm going to do R, and then let's reference this file as file, and then inside here we can read over the code. So I'm going to create a reader variable, and I'm going to initialize the CSV reader, and I'm going to input false. And then this line of code here skips over the header file. Since we're not going to be reading any header information, I'm just going to run next reader, and then everything after the header file, I'm going to do for row in reader. This reads over all the rows, and then let's add to our thrust values. So I'm going to do thrust values.append, and then if you look in the CSV file again, that to load. But in the meantime, we can also create a date object value, and we can set it to datetime dot strp time, and this will format the time value. So let's go back to our CSV, and we have time here and we have thrust here. Time has an index of 0 and thrust has an index of 2. So let's begin by appending thrust. So this will be row 2, and since this is a floating point value, let's typecast it from a string to a float. So I'm going to wrap it around a float. And then here, not data time, date time, let's access the date value. So here we have the date value with an index, time row with an index of 0. So I'm going to input row 0, and in this case this is going to be formatted as a string, so we can leave it as a string. And in the second parameter here, we can specify how that datetime is going to be formatted. So I'm going to put in this unique combination here. So this is going to put in the year, comma, month, comma, and then the day. And then I'm going to put in a timestamp value, so hour, comma, minutes, comma, seconds, and then we can put like milliseconds here. So now once we have that formatted, we can append to our time values array, time values.append, and then pass in our date object variable. And then once we have that done, let's print out the first 5 values of thrust values. So here, in order to see what that looks like. Oh, whoops. File. For some reason I thought it was false. File. We're reading over the file contents. So here we have the first 5 values of thrust in this data printed out. So let's cover how we can plot this. So it's going to be very similar to the code we wrote here, just replaced with our values of thrust. So I'm going to do plt plot, and in this time we're going to have an x-axis, which will be time, so I'm going to put time values, and then our y-axis will be thrust, so I'm going to put that. And then plt.x label, and in here I'm going to specify time on the x-axis, and then on the y-axis we are going to have thrust. And then the title I'm going to specify as spacecraft thrust over time. And then I'm going to give this a gridded background. And then finally show the plot. So now if I look here, you can see that there is some kind of variance with the thrust over time, but not really. There are some nice spikes in the data set where it goes from like 0.2 to about 4.5, but relatively it's the same over time. Great, so let's cover how you can use models and fit them using Astropy. So this leverages the built-in functionality of the Astropy library in order to create mathematical models that represent physical phenomena and fit these models to represent observational data. So remember what fitting is when we are given a data set, we're trying to create a mathematical function that best fits that data. So in order to do this in Python, we're going to be needing 3 core libraries, Numpy, Matplotlib, and then finally Astropy that gives us the nice unique fitting features. So I'm going to import that. And here, this is just code that generates a bunch of like random noisy data. So this uses the random feature of Numpy, creates evenly spaced values from -5 to 5 with 200 evenly spaced items. This models a interesting like exponential function, and then this specifies this to give it like a shape. And once we have this data of x and y, this is just like a random math function. We can do something called model fitting, and in this case this will be a Gaussian fit. And a Gaussian fit looks pretty much like a bell curve, and here I initialize it by specifying the models feature, Gaussian 1D, making it have an amplitude of 1 and a standard deviation of 1, mean value of 0. And then I use the Lev Mar LSQ fitter as the fitting model, and then I fit it with this Gaussian 1D method with the x and y values of the math function the data of the math function I'm also trying to model. So these 3 lines of code does pretty much all the magic in the back end, and now we can just go ahead and visualize it. I create a figure that is 8 by 5 in size. I first plot the random function we generated here, and then here I specify 2 ways of fitting the data. This line of code doesn't need to be there. So you can see this uses the Gaussian model, which creates a fitting model that tries to describe this data as much as possible. So the black dots are the x and y plotted values that are just interspersed. And I plot the fitted model, which is the line in solid blue, that tries to best fit the data points. And then I label the x and y values and give it a legend. And lock2 specifies the location of it to be in the left corner of the screen. You can also use Astropy in order to model physical phenomena. And this is really useful when you're trying to understand and simulate astrophysical situations. So one example of this is black body radiation. And this black body radiation, it's this pretty scary looking mathematical equation here, but don't be intimidated. This just describes the electromagnetic radiation emitted by a perfect black body. And what a perfect black body is an entity that absorbs all radiation and emits radiation thermally depending on its temperature. So you can think of it as this object that like absorbs or like soaks in all the outcoming electromagnetic waves, and then it only outputs temperature. And the equation that models this behavior is called Planck's law, and this is what Planck's law looks like. And these are what each of the values stand for. C is the speed of light, K is the Boltzmann's constant, T is the temperature of the black body, and V is the velocity of the particle. So in our exercise here, your task will be to model that above equation using Numpy and a specific modeling tool from Astropy called Blackbody, alongside units from Astropy and their visualization features, and create a specific variable that will mimic the model, and then obtain the flux values, and then run the code to test the model. So let's begin by importing everything we will need. So it states that we need to import Numpy, and then let's give it an alias of MP. Let's import matplotlib.pyplot as plt. Let's import Astropy, and then import Blackbody from there. And then from Astropy, whoops, I put in import instead of from. So from Astropy import units as u from Visualization import quantity support. So these are going to be all the libraries we'll need access to. So I'm going to import that. And underneath here, I'm going to specify the variable. So it says to create a variable called blackbody. And this will represent our blackbody model. And in order to do that, I'm going to use this feature of Astropy. And its first input parameter will be its temperature. We only need the temperature for it to compute the model. So I'm going to do temperature and set it to 3000 Kelvin. So to do this, I'll do 3000 and then I'll multiply it by units.k for Kelvin. And once I have that specified, I'm also going to create a Numpy range that is stored within the wavelengths variable. So set it equal to np dot, and I'm going to use the aRange method that goes from 2000 to 20,000 millimeters. Or is it 200,000? 200,000 millimeters. And this is going to be in these units. And then finally, I'm going to do the flux values. And you can obtain the flux by running blackbody wavelengths and then storing it within flux. So I'm going to specify this function here, and inside I'm going to put in wavelengths, and that will give us the flux output values. And now that we've extracted those values, we need to plot it out. And this pretty much does the code. So what this does is it will use quantity support, and using quantity support, it will create a figure, and then it will plot the wavelengths and the flux, wavelengths on the x-axis, flux on the y-axis, and then it'll create a line here that will model a spectra. So it'll create a vertical line in the middle of the screen with these units and show us the dead center of the spectra, and finally it will plot everything out. Oh whoops, instead of wave, it's wavelengths. And I didn't run the code above it. And you can see here that we have a plotted out spectra value. And, oh, BB is not defined. Blackbody. So now this line plots the direct center of the spectra here. A spectra is like any kind of bell-shaped curve that looks slightly stretched to the center. And then this will give you the center of the spectra. In this lesson, we'll be covering SciPy and differential equations. So firstly, what is SciPy? SciPy is a Python library used for scientific and technical computing. It was built on Numpy and offers more robust capabilities. You can learn more about it on their website here. And today we're going to be using SciPy in order to model differential equations. So if you haven't taken calculus yet, don't fear. A lot of this is going to be code, so we won't be really going into the nitty-gritty of this math. But a differential equation is a mathematical equation that relates one or more unknown functions to their derivatives. So it describes how a function or a set of functions change in respect to one or more variables. So here we have a function y plus dy dx, which is known as a differential, also known as a derivative, and dy dx is the derivative of the function y. And then we have the equation here that's set to 5x, And this is important because differential equations form the backbone behind a number of aerospace applications. Anything from like orbital maneuvers to other like aerospace phenomena that occurs can be modeled using a differential equation. And one very popular differential equation is known as the rocket equation, and it can be modeled using a differential equation to describe the rate of change of a rocket's velocity with respect to time as a function of mass flow of the propellant expelled from the rocket and the velocity of the exhaust gases relative to the rocket. So here is like a very robust proof of the rocket equation. You don't have to know this, just know the general flow of the math and that it is like a differential equation. If you want to understand differential equations and more of the underlying calculus concepts, this is a more math-intensive module, but feel free to just do it to learn how to code it. You don't really need to understand the math behind it, and it is a good leeway to some calculus projects you will definitely need in the aerospace sector. Here's a video by 3 Blue 1 Brown that I really enjoyed about differential equations if you're struggling. So, in order to solve an ordinary differential equation is just a fancy word for the simplest case of a differential equation you can have, which is one single independent variable. So, an example of a ODE, as it's called, is as follows. So I have dy dt is equal to negative yt plus 5. So I have my differential here, and then I have my function here. And in order to model this exact ODE in SciPy, you first have to import the relevant libraries. So first I import Numpy, I import the ODInt, which is the ODE solver in SciPy, and then finally I import Matplotlib in order to plot everything. And then I define a function here called differential equation that models this exact function up here. So we have dy dt is equal to negative y and t. It takes in y and t as input parameters because that's what's stated in the equation, and then it returns dy dt. So now in order to test this out, we need to set our initial conditions. So I set my initial equation addition for y to be equal to 1 in this case. And then I also create values of time for the initial equation, which is state space values from 0 to 5. And then I feed this into the ODE and get the outputted y values. So for each time value here, this is like a list of times, it will get the solved equation up here for that time by passing in the initial input parameters and the differential equation function itself. The function will be the first input parameter followed by the initial conditions. So then I have this solved solution of y values, and I plot it over time. So I do plt.plot. I put time on the x-axis, y on the y-axis. I title the graph, and then I show it. And you can see here, oh, I didn't run the code above. And you can see here, as we progress over time, the solutions change, and you can get numeric solutions for each timestamp. This leads us into the first exercise. Your objective is to create a differential equation that models the following equation here, pretty similar to the one above here, but the function is different. Make sure you set the initial y condition to be 1 and the time range to be 1 to 2, and visualize the ordinary differential equation using the Matplotlib library. So let's begin by creating a code cell. And in that code cell, let's first begin by importing all the relevant libraries. So let's import numpy as np. Let's import the ODInt method. So import ODE int for our solver. And finally, let's import pyplot. As PLT. And once I have these things imported, we can create a function that models our differential equation. And in this case, our input parameters are only going to be y and t, because dy dt is equal to y squared t plus at. So I'm going to do y and t. And then inside, I'm going to pretty much just state the value, this output in code. So dy dt is equal to, I'm going to use parentheses to help me, y squared times t plus 8 times t. And then now I have that, I can return dy dt, and then we finally have our equation here modeled in code. So now that I have that, I'm going to set my initial conditions. So I'm going to set y naught to be equal to 1, and then I'm going to set the initial conditions for time. So t is equal to np.linspace, equally spaced values from 1 to 2. And then I'm going to outline the solutions of this by using the ODINT method, and I'm going to plot the differential equation. And then I'm going to pass in all the input, the initial condition values, so t. And then finally I'm going to visualize this. So I'm going to do PLT, plot, and then I'm going to plot t is going to be in the x-axis, y is going to be on the y-axis, and then let's set the x and y labels respectively, time, set this y, and then set the title of this to be visualizing dy dt ODE, and then finally let's show everything. So now you can see here we have the ODE output visualized here. So you can see like the solutions are all 0, but at near this point of 1.4 it has a spike to 3.5. You can also model physical phenomenon using SciPy that use ODEs. So for instance, we can define a set of differential equations representing motional values for a rocket, including its position, velocity, and acceleration, that also takes into account external forces, like the forces of thrust, gravity, and drag on a rocket. So you can see here, we have an example of an ordinary differential equation for vertical motion. So here we have acceleration is equal to the thrust minus the force of gravity, which is mass times gravity, divided by the mass. And in order to model this ODE, we can use SciPy. And in this case, we can use the solve IVP method. So firstly, I import Numpy, SciPy, and Matplotlib. And I set my, since we are modeling a realistic scenario in this case, we'll have constants we need to consider. So here I have the gravitational constant, which is the acceleration due to gravity of the mass of the rocket and the thrust of the rocket in newtons. And here I have a function that pretty much solves the acceleration modeled above. So here I have the initial input conditions. In this case, we're going to have t, and I'm inputting a state variable. And the state variable is going to contain two things. It's going to contain x and a v. And here I return two variables. I return the velocity and the acceleration of a rocket, and I compute the acceleration according to the equation above I use above here. And now this is going to help me model both the acceleration and the speed of the rocket as it flies through the air. So here I set the initial position to be 0, I set the initial velocity to be 0, and I assign them a default state value. A state is a list with the position and the velocity, and then I set a time range, a time span value. And then I outline the solutions to this ordinary differential equation using the SolveIVP method. I first pass in the function representing the rocket motion. I pass in the time range, and then I put in the input conditions. So I put in the input state, the original input state, and then this is going to be the time span. So it's going to be from 0, because it's time span 0, to 100, which is time span 1, with 1,000 evenly spaced values. And then finally, I have the solution saved to this variable here, and then I plot the solutions. I plot the t, just time, and I plot the y output. And then I label time and position, and then title it, and put a grid up to it. Oh, whoops, I forgot to run the code above it. So now, when I visualize it, you can see over time, the rocket goes further and further higher into the sky as it accelerates, and it goes at a faster rate too, as it takes up speed, and it gains more speed per second as it accelerates. In this second exercise, we'll be modeling the horizontal motion of a rocket using another ordinary differential equation. In this case, the differential equation describing the horizontal motion of a rocket is as follows. We have dv dt, which is velocity, is equal to t time minus the distance over m. T minus the drag force, I did not mean distance, over the mass of the rocket. So here I import Numpy, SciPy, and we'll be using SolveIVP again alongside Matplotlib. And then in this case, we're also modeling a realistic scenario, so we'll need to consider physical constants. So here, the mass of the rocket is 1,000 kilograms. The thrust of the rocket is 20,000 newtons. And then here I assume constant drag force. Usually drag force is variable in the atmosphere, but here it's constant. And this will be a function of time. So as time changes, the drag force will get higher and higher and higher. And now let's begin writing our code. So first we'll need to define a mathematical function that models this ODE behavior. So I'm going to call it rocket motion ODE, and it's going to take in two things. It's going to take a t value, a timestamp, and a state, similar to the rocket motion ODE solver. And in here I'm going to set v, and I'm going to extract the velocity from the state. And then here we can have the drag force, and instead of having the drag force as a constant up here, I'm going to move it into here. I think that's what it was meant by the problem. So I'm going to have drag computed inside of this ODE solver. And then here I'm going to compute the acceleration of it. So I'm going to set a is equal to pretty much the mathematical function I have here, t minus d over m. And then once I have that, I'm going to return this as a state and then put only the acceleration in there because we won't be needing velocity. Okay, so now that we have that, let's create our initial conditions. So v naught is going to be equal to 0 because its initial horizontal velocity will be 0. It's going to start from rest. And then I'm going to set its initial state, state 0, let's call it, and put in only v0 because that's the only state we're extracting from. And t span, time span is going to be 0 from 100. And the reason why I use a state here with a list of only one item is just for conventional patterns. Let's say you have just a generic differential equation with multiple variables, then you'll probably need to do some kind of standard like this, where you have a list here with each of the variable values. But in this case, I'm just treating it as is. You don't have to do it. You can just make it a variable and not assign it a state, but I'm just doing it for the fun of it. And now that we have these initial conditions written, let's solve it. So I'm going to set the solution sol equal to solve IVP, and then we're going to input first the mathematical function, followed by the time span, the initial state, and then t-val, which is going to be the time range. It's going to be np linspace, and I'm going to pass in t-span of 0 to t-span of 1, so 0 to 100. And then I'm going to have 1,000 values. And then once we have that solved, let's finally visualize it. So I'm going to do plt.plot, and I'm going to plot sol.t, the solution time range, and then the solution y coordinate values. And then let's label the x and y values respectively. So let's do time, and this is going to be in seconds. And then we're going to have horizontal velocity, which is in meters per second. And then let's give this a title. Let's call it rocket. Let's give it a gridded background, and then finally show it. So you can see here, we can see how the rocket horizontal motion changes over time. We can see as it is launched, it gains horizontal motion and keeps going, keeps going, keeps going. And then at some point, it starts moving in the other direction as it becomes more negative. Welcome to the third lesson, where we will be covering partial differential equations. So unlike ordinary differential equations, which we covered in the previous lesson, which only involved one variable, PDEs are a little bit more complex because they involve functions of two or more independent variables, and describe how these functions vary in respect to each independent variable. So for example, I have a PDE as follows. We have the second derivative of u over dx squared plus du squared over dy squared is equal to 0. And in this case, we have u, which is the dependent variable, and x and y are the independent variables, because we are taking the derivatives of u in respect to x and y independently. And then within a physical context, partial differential equations are used to model situations where more than one independent variable affects the behavior of a system. And these situations often involve phenomena that vary in space and time and across multiple spatial dimensions. So PDEs open a wide range of doors in terms of their relevant applications. Some applications of PDEs include orbital mechanics, astrodynamics, and mission design, alongside spacecraft thermal analysis. You can also use PDEs to model the parametric design of an aircraft. You can see here, this aircraft is defined parametrically using a partial differential equation. So we can use SciPy in order to solve PDEs as well. And what's great is SciPy provides us with a wide breadth of tools to do so. So let's use an example of a PDE of a physical phenomena. In this case, this partial differential equation describes how temperature, u of x of t, which takes in position and time, of a one-dimensional rod. So here we have a one-dimensional rod, and it describes how heat diffuses through this material that comprises this one-dimensional rod. So we have this equation here. We have du dt representing the change in temperature, is equal to the thermal diffusivity of the material multiplied by the spatial curvature of the temperature profile. So in order to do this, I first import the relevant libraries. I import Numpy, and from SciPy integrate, I also import solve5vp, which is going to help us with the partial differential equation, and then pyplot. So here I set the initial conditions. So I set the length of the rod to be 1. I set the thermal diffusivity, how easily the temperature or the heat passes through the material, which is represented as alpha here. And then I set the initial temperature distribution, and I use the lambda function to do so. And in this case, I just use like an arbitrary sine function, pi of x, in order to get my initial t values. And then I set the boundary conditions of the left and right values, which is going to bound our answer solutions. And then here I model the math equation described up here. In this case, this is going to be referenced as a second spatial derivative. So I use heat equation PDE. I take in the timestamp and the temperature, and I return dt dx2, which gets like the gradient value of t, and then I multiply it by alpha. It gets the second spatial derivative. So in this case here we have d2u over dx2. This is referred to as a second order derivative. So in Numpy, we can just do this by doing np.gradient twice with the temperature variable, and then I just multiply by alpha, the constant at the beginning. So once I have this formula, I go from 0 to the length of the rod, because we're modeling the heat flow through the length of the rod, with 100 equally spaced values. I get the initial temperature by running t initial on x, and then I get the solutions for this by running solve5vp. I pass in the function, and then I give it the range. I give it the initial time temperature, and then t val, which goes from 0 1 with 100 spaced values. And then finally I plot everything on a 10x6 plot, and I do this by iterating over the range of solutions here. So I do for timestamp value here, I plot the x and y respective values, and then I title the axes. So you can see here this represents the temperature distribution over time, also known as the 1D heat equation. And you can see as the position of the rod goes more to the center, its temperature increases, and then as it goes more to the end, its temperature decreases. So you can see here it's most hot in the middle and then decreases near the end. There's more partial differential equation applications within the aerospace sector. And this is because PDEs allow us to capture the complex physical phenomena involving multiple independent variables alongside their derivatives. So here I have an exercise for the Laplace equation, partial differential equation, and this is often used within the aerospace context for solving problems regarding steady-state heat conduction, electrostatics, fluid flow and potential flow around aerodynamic bodies. And you can see that the PDE described as the following. It's the divergence squared of u is equal to this PDE here. We have our independent variables of x and y, and we have a dependent variable of u, and we have the second order spatial derivative of u in regards to x, alongside the second order spatial derivative of u with respect to y, have it set to 0. And this is what the Laplace equation looks like when it is visualized mathematically. It's a pretty funky looking equation, but there's a lot of beauty and symmetry to it. And in order to solve more complicated physical phenomena related partial differential equations, we can use a tool called PyPDE. And this is a tool specifically for solving partial differential equations numerically. And you can learn more about it here. And rather than fabricating our own equation solver, we kind of had to finesse our way through solving it here. And it was a little bit of a crunch to organize and everything so it can be properly plotted. PyPDE does most of the groundwork for us. So let's go through this exercise together. So first you'll need to import Numpy. So let's import Numpy as np, and then we need to import from PDE, import the Cartesian grid, which is a standard grid, and then the Solve-Laplace equation. Solve-Laplace equation is intrinsically within the PDE library itself. So the solver is already written for us. We just need to use it again for our specific scenarios and initial conditions. So now that I have the libraries imported, I'm going to define the grid and boundaries. So here we have a Cartesian grid defined spanning from 0 to 2 pi, and then it is 64 by 64 pixels. And then I set the boundaries for the boundary conditions. With partial differential equations, you'll need to set boundary conditions in order to contain your answers. So here I set the boundaries to be sine of y and sine of x. And then finally, we can solve the equation. So we're going to create a variable called result, and then we're going to contain the output of Solve-Laplace equation. And in here, all we need to put in is the grid and the boundaries. So I'm going to put in the Cartesian grid and the boundaries as parameters. And then now we can plot the output by running result.plot. And you can see here we get this two-dimensional, really fancy looking solutional value to the Laplace equation that uses a color map to give us the solution. So you can see here at 5, 0, we have a solution of 1, as compared to 2, 6, we have a solution that's close to 1. So it's a really nice way of visualizing a solution to more complicated equations like partial differential equations. In this lesson, we'll be covering image and spectra analysis. Firstly, let's begin with image analysis for aerospace. So image analysis plays a crucial role because it provides valuable insights into celestial objects, spacecraft, and various space missions, and it's oftentimes utilized for object detection and classification, where Python programs are used to study astronomical images to classify various objects using machine learning. There's also used for remote sensing, where you can analyze pictures of the Earth's surface and figure out different patterns such as climate change, agricultural growth, and so forth. Planetary exploration is handy because image analyzers are used within their missions in order to study the surfaces of planets, moons, and asteroids. And then it's also used for spectral analysis and photometry, where astronomers use spectral analyzers to classify stars, galaxies, and other objects within space using their spectral signatures. So talking a little bit more about photometry and spectral analysis. Spectral analysis is really handy for image analysis and so forth because it's crucial for understanding different compositions of the celestial object in terms of materials, alongside observing stellar events such as stellar pulsations, eclipsing binaries, and supernova. And photometry works by measuring and analyzing the brightness or intensity of light either emitted and reflected by celestial objects across different wavelengths. And spectroscopy refers to the process of analyzing these spectra in order to study the composition, movement, and temperature of celestial bodies. So depicted below is an image of a spectra of a sun alongside the spectra of a fluorescent light lamp. And you can see here the sun is a little bit more smooth in terms of its spectra. And you can see it kind of increases during the nanometer wavelengths of blue and then diminishes. As with a fluorescent light bulb, you see spikes of brightness for specific wavelength bands. For example, the wavelength band of green is very high in brightness alongside like orange, but you can see it's very dim in other areas. So there's a wide range of tools and libraries you can use for image analysis, but some popular options I like to use within my programs are Astropy, which is a core Python package for astronomy that allows you to handle spectral data. Utils is a Python package specifically for spectroscopic data analysis and using tools for things such as spectrum plotting, continuum normalization, and spectral line identification. There's scikit-image, which is a Python library for image processing and computer vision tasks, which is really helpful for analyzing remote sensing images. So let's begin with a quick example where we analyze the spectra of Ceres using SpecUtils, and we'll be analyzing a one-dimensional FITS file representing Ceres. Ceres is the largest object in the asteroid belt and the only dwarf planet located in the inner solar system. And this data is sourced from the HARPS Solar Spectral Database. It's linked below if you're interested in learning more. And this is like an image of Ceres. And what we're going to be analyzing is the spectra of it. So first I'm going to begin by importing two libraries. First I'm going to import astropy.io and FITS from it, and then the spectrum 1D from SpecUtils. And then from there we're going to open up the FITS file. So here I have the FITS file of Ceres.fits, and it includes all the data for the Ceres FITS file, and I just get information about that file. So you can see here it has a primary HDU with these dimensions. It has a lot of items, and it uses the float32 data format. And I extract a little bit more information from the primary HDU by selecting it from the index here using an index of 0 and using from the header. And you can see here if we print out the contents of the header, I'm going to print out a little bit more. We can gather its file format, volume settings, where the data was sourced from, alongside other like coordinate values. And here we kind of have to modify. This is a slight adjustment I made in the code. This deletes the B-unit row. This is just to deal with a small unit handling issue that arises when we're dealing with these files specifically. But just make sure you run this. And then now we can plot the spectra using the Spectra 1D data class. And what I do is I do spectrum1d.read, and I read the FITS file contents. And then now if I print out the spectra, you can see we have different values printed out. So we get the flux, which is the amount of luminosity emitted. We have the shape, the mean, and the spectral axis. And now that we have the data, we can finally visualize it using Matplotlib. So here I import the Astropy visualization quantity support alongside Matplotlib pyplot, and then I invoke the quantity support method, and this is because we want to numerically convert the values before plotting them. And once that is supported, I create a subplot I title it 1D Spectra Visualization of Series, and then I create a step function where the x is the spectral axis and the y is the spectral flux. And you can see here this plots the spectra of series, and you can figure out from here which wavelengths correspond with high luminosity or flux outputs. So you can see like here series, like near the beginning wavelength, series has a really high spectra output, but it kind of diminishes as the wavelengths get bigger. This brings us into the first exercise, where we will be not visualizing the spectra of Ganymede, and this is the largest moon of Jupiter, and also the largest moon of the entire solar system. And in this exercise, you will be analyzing the spectra fits data for it, and visualizing it using Matplotlib and SpecUtils. So here are the objectives, and give it a shot. So I'm going to create a data cell, and first we're going to import all the necessary libraries. So first I'm going to import fits from Astropy. So I'm going to do astropy.io import fits, and then let's import from SpecUtils, import Spectrum 1D, and then let's also import quantity support. I'm going to grab this code up here alongside Matplotlib. So that should be all the libraries we need. And now that we have that, I'm going to create another code cell, and I'm going to extract the data from the fits file. So I'm going to do fits.open, and in here I'm going to get the fits file for Ganymede. So I have this file here, it's called this. So let me specify that. And then we can do file.info in order to get information about it. So let's see here, we see it only has one HDU, and these are the dimensions adhering to a float32 data format. And we can also get information about the header. So let's do that. I'm going to create a header variable, and then get the primary HDU, and then get the header. And then we can print out the first 5 rows of the header, like the following. And then once we have the header information, let's go about extracting the spectra. So first, we will get the same funky little error if you don't run this code. So let's just delete the header column first, in order to avoid that error. And now we've done that, we can extract the spectra. So let's do spectra is equal to spectrum 1D dot read, and let's read in the file. And now that we've read in the file, we can do spectra in order to see the output. And we can see here we get the flux values, the shape, so forth. And now that we have the spectra, let's create a visual plot of it. So first, let's use quantity support. And then let's create a subplot. So fig x is equal to plt.subplots. And then let's title it. Let's give it a title of 1D Spectra Visualization of and then let's use a step function in order to plot the spectra. So I'm going to do spectra dot spectral axis, and then let's plot the flux. So you can see here the 1D spectra of Ganymede looks a little bit different than that of Ceres. You can see its flux output is a little bit stronger, meaning it emits a lot more electromagnetic radiation, it's more visible. You can also use Python libraries in order to visualize satellite imagery. And satellite imagery are crafted by a bunch of satellites in orbit called remote sensing satellites that capture images of the Earth's surface. And these satellites are responsible for a wide range of remote sensing tasks such as environmental monitoring, weather forecasting, urban planning, disaster response, and more. And compared to normal cameras, which are only limited to capturing optical information, satellite cameras are a little bit more special because they are equipped with multiple sensors capable of detecting various parts of the electromagnetic spectrum, such as visible and near infrared. And with this enhanced capability, these satellites can gather a lot more information about the Earth's surface, ranging from climate patterns and geographical events. So some examples of remote sensing satellites that conduct satellite imagery include Landsat, which is a NASA-operated satellite system that capture multispectral imagery. For climate monitoring, there's SETINTEL, which is an ESA program specifically for environmental monitoring and emergency response. And then there's GOES, which is short for Geostationary Operational Environmental Satellites, which is operated by NOAA and provides continuous weather monitoring. So when we look specifically in the satellite imagery data formats that are crafted by these satellites, they're a little bit different because they fall within the geospatial category, and this means that you will be working with another file format, and it's usually the TIFF file format, which is really closely tied to geographic information. If you've played around with Google Earth Pro before, you might have seen it. And TIFF stands for Tagged Image File Format, and it's a widely pervasive file format that stores rasters of graphics and images, and it's super flexible, allowing for more like high resolution geospatial imagery to be stored. And these images are stored as rasters, where each image is represented by a grid of pixels, each corresponding to a specific value, and this value is usually how much light is reflected off of the surface of the Earth. So in order to read and process TIFF files, including geospatial information of the surface of the Earth, we can use a library called EarthPy. And using this, we can read about satellite imagery. And one more core concept about satellite imagery are bands. So whenever you're dealing with imagery, you'll have different layers, each representing different aspects of the image. So for example, here we have a satellite image, which is usually like a TIFF file that's condensed into multiple bands. So I have 7 bands here, and there's the blue, green, and red bands, and when you combine multiple bands together, you can get a finalized image output that gives you specific information. So usually researchers like pick and play with different band combinations. The most common band combination is red, green, blue, but you can also add like different band types in order to get other types of imagery information. So we'll be covering how you can analyze satellite imagery using EarthPy, and you can learn more about the library here. So let's begin by plotting bands of satellite imagery and creating some visualizations. In order to do so, we'll need the following libraries. We'll need the Numpy, of course. We'll need glob and raster IO for processing the TIFF file format, and then we'll need EarthPy in order to process the satellite imagery bands and display it. So let's first begin by importing the band data collected by the satellite that's stored within the TIFF file. So you can import all these band files in bulk using the glob function. So here, this is just me configuring it, and then here I just get all the band information, right, which store different characteristics of the satellite by using this glob command, and you can see I have a folder here called satellite bands that includes all the TIFF files for each of the imagery bands collected by the Sentinel-2. So I first glob them together and get each of the data for the bands, and then I sort them. And now that I have these bands, we can see here, all sorted, I can visualize the data. So we do this by first initializing an empty data list that will contain all the data embedded within the bands themselves. And then here I iterate over each of the satellite imagery bands, and then using the RIO tool, I open the bands in read mode, and then I append to the data I am able to read from the band file. And then once I have read all the data and it's stored in this list, I stack it together, meaning I overlap them together. And then I plot each of the different bands using the earthpy plot bands method, using the stack of bands, which are all the bands that comprise the image. And then CMap is the style I chose, so I chose the just earth style. I make sure the figure size is 20 by 12, 6 columns for 6 bands per each row. And then if I show it here, it displays each of the bands that comprise the image we are studying from the Sentinel-2. And you can see like they take the same image over the same geographic location, but they're just looking for different parts of the electromagnetic spectrum that are reflected off of the surface. So they look a little bit different in composition, and researchers look at each of these bands one by one in order to study different phenomena. So let's do like a special combination where we create an RGB composite image. Where you combine multiple of these bands together, you end up with a resultant composite image, and RGB is a pretty popular one. So this is derived from where we get the band data from adding the 3 spectral bands of red, green, and blue in order to create a single color image. And this is widely used in remote sensing because this is the way the human eye perceives color. And in this case, in order to create an RGB composite, we need to understand the respective red, green, and blue band numbers. So in this case, band number 3 is going to be red, band 2 is green, and band 1 is blue. So in order to create an RGB composite image, I use the earthpy plot RGB method, and I input the entire stack data, but I specify the band numbers in the RGB parameter property. So red is band number 3, green is band number 2, and blue is band number 1. And then I plot it in a figure of 10 by 16. And you can see here we get a complete color image. And if you were on the satellite looking down, you would most likely see this as a result, and tools like Google Maps display RGB composite images. So in this exercise, we'll be taking things a step further and creating your own custom composite that is not RGB. It's going to be called a false color composite. And you'll be crafting this band combination, and this false color composite is usually used by remote sensing analysts to look for signs of vegetation, and it really helps with distinguishing between healthy and stretched vegetation. So one hint here that I would take into consideration is the band breakdown. So in order to make a false composite, you'll need near infrared, which is band number 4, red, which is band number 3, and green, which is band number 2. Give it a shot and good luck. So I'm going to begin by importing all the libraries we'll need. So first we'll need to import Numpy, and I'll import it as MP. I'll import glob in order to import our TIFF files in bulk. I'll also import raster IO as our I/O in order to process our raster information. I'll import EarthPy as ET. I'll also import spatial from EarthPy. And then so these are all the libraries we'll need. Now we have everything imported. I'm going to import all the band data in bulk, so we can pretty much copy what I put here. And then it's going to be the same imagery bands, so it's going to be the same file specified here. And these just WildStar symbols. Just get the stuff, all the text before and all the text after, and glob them together into a single bands unit and sort them. And then now we've done that, let's derive the data from each of these bands. So I'm going to create an empty data list, and I'm going to iterate over the bands. And for each band, I'm going to use raster I/O to open the data under read mode. And I'm going to refer to it as file. And then I'm going to append the processed data to the data list by reading the contents. And then I'm going to create a stack of the data, referred to as stack data. And I'm going to create it by using np stack and feeding in the data values. And then now we can create the false color composite. So I'm going to call it false color FCP, and I'm going to set it equal to earth plot, and then do plot RGB, but instead of RGB bands, we're going to specify the false color. So I'm going to do stack data and RGB. So first we're going to, instead of red, we're going to put near infrared. So we're going to put band 4, and then instead of green, we're going to put red, which is band 3, and instead of blue, we're going to put green, which is 2. And then let's set the figure size to be equal to 10 by 16. And then finally, we can plot everything by doing plt.show. As file. Oh, dot open. If I go up here, oh, band, apologies. So we're going to open the band data and then append the data extracted from the band. So here you can see it looks a little bit different. In my opinion, it looks a little bit more red. The blue, the ocean is a little bit more red. And this helps with making the vegetation pop out a little bit more. So you can see here, like this part has more decayed vegetation, while the vegetation here looks a little bit more healthy. In this lesson, we'll be covering how to create effective simulations for the aerospace sector using Python. So firstly, simulations are used within the aerospace industry in order to design complex models using software, whereas it would be difficult and very expensive to replicate within a physical environment. So in order to do this, programmers create a digital engineering environment where they can model and analyze behavior of various aerospace systems within a software environment, making it a lot more cost-effective. Applications of simulations include performance analysis for aircraft and other spacecraft, mission analysis for satellite deployments and planetary landings, alongside digital engineering computational models as depicted here. So we're going to begin by creating a two-dimensional orbital mechanics simulation. And this simulation is going to model the behavior of a two-dimensional orbit, kind of like the orbits we've been dealing with thus far, by numerically integrating differential equations that describe the motion of the orbiting body. So it's going to combine two of the previous things we've been working together, differential equations and orbital mechanics, in order to create an effective simulation. So before we get into the code, let's go over the math. So in order to create the simulation, we're going to have to define a ODE, a ordinary differential equation, which is just a differential equation with one variable we're dealing with. And this equation describes the motion of the orbital body with the gravitational field acting as the central mass. And in order to do this, we need to first establish some key equations. You might have seen this one before. It's pretty famous. F is equal to ma. And this describes all the forces. And then in this example, we're going to be dealing with a gravitational force because all satellites deal with some kind of gravitational force that is exerted on it by a central mass. For example, the International Space Station's central mass is the Earth. So this is indicated by Newton's law of gravitation, which is force is equal to gravity times the mass of the central body times the mass of the satellite over the radius, which is the distance between the two bodies squared. And then from this equation, we can obtain the centripetal acceleration of the celestial body. And this is acceleration is equal to v squared over r. This course does not cover the scope of the physics behind this, but just understand that these are the three equations we're going to be dealing with in order to create our simulation. So in order to create our simulation, we're going to need to initialize state vectors. And you can think of state vectors as snapshots which store information about the orbit at a specific timestamp t. And the state vector breakdown for this simulation is as follows. So the state vectors is going to be a list, and the first item in that list is going to be the x position of the satellite. The second item is going to be the y position of the satellite. And then we have the third item, which is going to be the velocity of the satellite in the x direction. And the last item is going to be the velocity of the satellite in the y direction. And by using these values, we can derive for acceleration, because we know that acceleration is the derivative of velocity. So we can easily do this by doing the dx dt and dy dt values. So this just extracts the velocity. And then we can use the equations above, which is Newton's law of universal gravitation, in order to do a quick derivation for the acceleration value. So here we know that F is equal to F. So we have Newton's law of gravitation is equal to F, which is mass times acceleration in the x direction. And then we simplify the equation, which gives us gravity times the mass of the central body times x over r cubed. And we can describe the following in code here. You don't need to understand the complete complexity of the math here. Just understand that this is what the equation we are going to be numerically dealing with. And this is going to be the acceleration. Because you can see here, within our state vectors, we don't have acceleration included, so we have to compute acceleration ourselves. And this is the output, dvx dt, which is going to be acceleration in the x direction. And we can do the same thing, dvy dt, but with the second state vector, so we'll be using dy dt as the variable. So in order to do this, I first import 3 libraries. It's pretty straightforward. We're going to be importing Numpy, the integration ODINT method from SciPy, and then Matplotlib, of course, for visualization. And once we have these 3 imported, we're going to create a mathematical function that represents this up here. So this takes in the state vectors list, which is as follows, and then it takes in the timestamp t, gravity, which is a constant, and then the mass of the central body. And we just get dx dt from the state vectors list, pretty straightforward. And then from there, we run it through the mathematical equation here that we represented in code here. And I just get it for both acceleration in the x and acceleration in the y direction. And then I finally return a state vector here, including the velocities in the respective x and y direction, alongside the newfound accelerational values in the x and y directions. So now we need to define our initial conditions. The initial conditions describing the x and y position alongside the velocity is going to be x is going to be 1, y is equal to be 0, velocity in the x direction is going to be 0, and then velocity in the y direction is going to be 1. And then I defined the time points for integration, so this is going to be the time range we're going to be integrating over. So this is going to be 0 to 10 with 1,000 evenly spaced values. And then I define constants here. This is going to be theoretical, so I'm setting the gravitational constant to be 1 and the mass of the central body to be 1. Is it realistic? No, but we're just using it for testing purposes. So I'm going to set these initial conditions, and then now we can simply perform the numerical integration. Luckily, the ODINT method makes it really easy for us. So I created a new variable called solution. I set it equal to ODINT, pass in the mathematical function I created here with the initial state vectors over the time range, and I set the arguments of the gravitational constant and the mass of the central body. Now it's time to plot the orbit trajectory. To do so, I create a figure of 8 by 6, and then I plot the solution range from the beginning all the way to 0 for the x coordinates, and then 0 to 1 for the y coordinates. I plot x and y, and then I create a 2D orbit simulation, setting the gridded background with equal axis lengths. And you can see here we get a circle as our solution point. This brings us into the exercise for this lesson. You are tasked with simulating another 2D orbital mechanics scenario, but in this case using realistic values for an orbit of a celestial body around Earth. So in order to do this, I'm going to first import the 3 libraries we used above. So I'm going to import Numpy, and then I'm going to import ODINT dot integrate. And then I'm going to import Matplotlib. And then after importing these libraries, I'm going to define the mathematical equation. This is going to be pretty straightforward because it asks us to take in the same state vectors and return dx, dy, dt, so it's going to be the same code as above. So you can pretty much copy the code up here. And this is going to take in state vectors of velocity, and then it's going to return state vectors of velocity alongside the new calculated accelerational values. And once we have that, let's define our initial conditions. So we need to have initial value of altitude, so let's create altitude. And this is going to be 400 e times 10 to the third power. And then initial velocity is going to be 7,800. And then let's set the initial condition for the state vectors. So this is going to be a list containing 4 values. So it's going to be let's set the x to be 0 because we didn't specify an x here. The y is going to be the altitude. So I'm going to pass in altitude. And then initial velocity here. And let's set the initial velocity for the y direction to be 0. And then let's define the timestamps for integration. So I'm going to do np linspace. And this is going to be 0 to 10 with 1,000 evenly spaced values. And then let's define our constants. So gravity is going to be this. Okay, this is not realistic, but let's play along with it. And then mass is going to be this value. So now that we have our initial conditions defined, let's numerically integrate. To do so, we're going to use the odent method. So solution is equal to odent. Let's pass in our function here. Let's pass in our initial condition states, our time range, and then our arguments for gravity and mass. And while that is computing, let's write the code. Let's write the code to visually plot our trajectory. So I'm going to do plt figure, and this is going to be of size 8 by 8. And then I'm going to plot it. And the solution is going to be from here. And then like that. Let's label our values in the x and y directions respectively. Y label plt.title. And here we're going to specify orbit simulation for Earth. Let's give this. For this project, we'll be creating a numerical solver that models the rocket equation. So firstly, what is the rocket equation? The rocket equation, also known as the Tsiolkovsky rocket equation, is a fundamental equation used pervasively throughout aerospace to describe the motion of a rocket in terms of its mass and the velocity of the exhaust gases expelled from its engine. So the equation is as follows. We have the change in velocity is equal to the exhaust velocity of the propellant times the log of the initial mass of the rocket, including the propellant, divided by the final mass of the rocket after the propellant is expelled. So in order to understand this, we need to get an intuitive understanding of this concept called thrust. And thrust is a force that propels an object forward. And for a rocket, thrust is generated using its propulsion system, which includes its rocket. And we know that according to Newton's third law, F is for every action there is an equal and opposite reaction. So in this case, thrust in a rocket is produced by expelling a propellant in one direction, in the downward direction, and the reactionary force in the opposite direction is what propels the rocket in the upwards direction, allowing it to blast up in the sky. And thrust can be calculated using the following equations. So we have J is equal to mass times volume, and we can derive thrust. So the force of thrust is going to be equal to J divided by T. And now we can plug in values of J, which is mass times velocity, momentum. So thrust is equal to momentum divided by T. And then we can rearrange the values here to get the force of thrust is equal to mass over time times velocity. And we can rewrite mass over time to be dm dt, because m divided by t represents the rate of change of the propellant mass. This is also referred to as the mass flow rate. And we can just plug in it as dm dt as a derivative of the change in mass times velocity. So now we have this rewritten equation for the force of thrust. And now we have the equations necessary in order to derive the rocket equation. So here we have this equation describing the force of the upward thrust. So J rocket is equal to mass of the rocket times d of v, and then J propellant is equal to the escape velocity of the propellant times the dm, which is the change of propellant mass. And from Newton's third law, we know that the force of the upward direction of the rocket must equal the force of the downward downward force created by the propellant being expelled. And now we're just plugging in values from up here to here. So you have the mass of the rocket times dv is equal to the escape velocity times dm. We rearrange it so we have the dv expressed as the following. And then now we take the integral from the boundaries of the final velocity from the initial velocity and the final mass to the initial mass. And this leads us to this equation here. And then finally we get v final minus v initial is equal to the escape velocity of the propellant times this integral here. And then we rewrite it in terms of logs, and we finally derived the rocket equation. Don't be intimidated if you didn't completely understand this. I was just showing it in order to prove the mathematical background of it, but you just need to understand this equation here. Once you have it, we can create the numerical solver. So first, let's begin by importing the libraries. So let's begin by importing Numpy as np, and then we'll import pyplot here as plt, import SciPy as sp, and then let's import the solve IVP method in order to integrate everything. And then now, a line below are the constant variables we'll be using for our ordinary differential equation solver. So here I have the effective exhaust velocity of the propellant, how fast the propellant is being expelled by the rocket, the initial mass, how heavy the rocket is in kilograms, and then I have the mass flow rate, which is in kilograms per second, delta m. Whenever you have a delta in physics, it's going to be the final minus the initial, so it's going to be how much the rate of which the mass of the propellant was being expelled. And then I have here defined the time range for integrating. And then now this is the bread and butter of our project. We need to create a function that describes this mathematical expression here of the rocket equation. So let's create a function called the rocket equation, and this is going to take in the state vectors of time and the exhaust velocity of the rocket. And then from there we can create an expression, let's call this delta v. For delta v, this is going to be equal to the escape velocity, so v of e, this is a constant up here, and this is going to be multiplied by the log, so np log, and m initial is a constant, divided by, we need to calculate mass of final, and the mass of final is going to be the mass initial, because mass initial is going to be heavier because mass initial includes the total rocket mass, subtracted by delta m. Delta m is how fast the mass propellant flow, so how fast the propellant is being expelled, times the time. So how much is being expelled per unit time multiplied by the time, the amount of time it was actually being expelled. So that describes mass final. And then let's return our delta V. Okay, so now this outline below is the code that describes the solver. So here I have solution is equal to solve IVP. I plug in our mathematical expression for the rocket equation here, the time range we want to integrate over, our initial state vector, and then here I define the time evaluation range, which is going to be from 0 to 10, and then I outline the solution and save it to a variable v. So now that we have that, we can finally plot and visualize our results. So it says we need to create a Matplotlib figure of figure size 10 by 6. And then we need to plot our visual output results. So it's going to be from our evaluation time range, plug in our initial velocity, and then we need to label this as the rocket velocity. And then finally, let's label our x and y axes. So our x axis is going to be time in seconds, and then our y axis is going to be our velocity, which is going to be in meters per second. And then let's title our plot to be rocket velocity over time. Let's give this a gridded background. I'm going to set it to true. And then let's give this a legend. And then finally, let's show our plot here. So you can see this is a visual graph of the rocket velocity over time. We have time here. So as the rocket is deployed and launched, it gains velocity like the following. It looks kind of like an exponential curve because we know the rocket is accelerating through the sky. So we have this curved looking graph here. In this lesson, we'll be focusing on creating GUIs. So what is a GUI? A GUI stands for a Graphical User Interface, and is a type of user interface that allows users to directly interact with it using elements such as buttons, text inputs, selection menus, and so forth. And the GUIs are pervasive amongst modern software. They're used for a wide range of technologies such as operating systems, mobile applications, and websites on web browsers. So in order to create GUIs, we're going to be using a library called tkinter, and tkinter is a standard GUI toolkit for Python, and it has a wide selection of components. You can check out it below, and in order to import it and use it, we need to run this command, import tkinter as tk. And we can first begin by creating a basic GUI using tkinter, and we do so by initializing a window. In order to initialize a window, which is like its own screen pretty much, we use the tk class. So I initialize the class here, and I want this GUI to have text in it. So I create a label element, and I specify tk label, and inside I specify the parameter of text to be hello world. So this is going to display a label stating hello world. And in order to display this onto the window, we do label.pack, which packs this into our window display, and then we finally execute this code in order to make sure the application is running continuously and listening for user input by running the main loop command. So you can see here, if I run this, it will create a mini window that looks like the following, and we can expand it. And you can see here it's called TK because we specified it using tkinter. You can see that this generates a user form, and here we have our two labels. So remember, we have two labels here. We specified this name to have a row of 0, so it'll be the first row, and it'll have a column of 0, so it'll be on the leftmost column. Age is on the second row here, and it'll be on the leftmost column. You can see there's a little bit of spacing in the x direction. This is because we added a padding of x of 10. You can also see there's a little bit of spacing in the y direction. This is because we added a padding of y of 5. And these are the entries, these little text fields that I can type stuff in. And this is the name entry here that we specified to be on the second column, which it is, on the first row. And then the age entry, which is on the second row, second column, which is right here. And then we created the submit button, which is on the thirdmost row, index of 2, first column, and we set the column span to be 2. So it's dead center because it takes up 2 columns, so it takes up the entire row here, and we set it to be center. And we gave it a padding x of 10, padding y of 10. And then currently the dynamic label is all the way down here on the bottommost row, but its text is empty, so we can't see it until we submit something. So let's test this out and put in a name. So I'm going to put in Bob, and his age is 44. And when I click submit, you can see that our dynamic label, our info label here, adjusts because this function is run, and it configures the text and formats it to the name by getting the name from the entry. And it says name, Bob, puts a comma in between, and then gets the age from the age entry here, and then displays it in the info label down there. So now you are tasked with applying your newfound knowledge of tkinter in order to create an addition calculator. So give this a shot and come back to this video when you're done. So let's create a code cell, and let's begin. We already have tkinter imported, but I'm going to import it again just to make things clear. And then let's initialize a window, so it'll be tk.tk, and in our window, let's give it a title, and this is going to be addition calculator. And now let's begin by creating our labels. So I'm going to create 2 labels. So it's asking us to create inputs for number 1 and number 2 respectively. So I'm going to first create labels for the inputs of the numbers. So let's begin by creating the number 1 label. So I'm going to call this number 1 label, and I'm going to set it equal to tk.label. And in here I'm going to specify the window because we want to embed it within the window, and then the text is going to be equal to number 1. And then let's add this to our window by doing pack. And then let's create an entry for number 1. So number 1 entry is equal to tk.entry, and I want to show this in the window. And then let's pack this here, number 1 entry.pack, and I'm going to give this a padding y of 5 just to give it some vertical padding. So let's do the same kind of thing just for number 2. So I'm going to call this number 2 label, and then set this text to be number 2. I'm going to pack it onto the screen, and then I'm going to create an entry for it. So number 2 label, tk entry window, and then pack that onto the screen as well with the padding y of 5. So now let's define the function that gets executed when we press the add button. So I'm going to call this def add numbers, and this will get the added result of the values defined in number 1 plus the number 2 entry value. So let's set the result variable, and let's set it equal to number 1 underscore entry dot get. This gets the value from number 1 entry. And let's make sure this is going to be a string by default, so we're going to typecast it into an integer. And then let's do it again, but for this time number 2. And then let's configure our result label. So I'm going to make this result label in a second, but we're going to configure it in order to show the sum of these values. So it's going to say sum, and in here I'm going to show the result. And then let's define the add button now. So add button, and then let's set it equal to k.button, and this is going to be window. I'm going to set the text to be add, and then the command is going to be the add numbers. And then let's pack this. Oops. Add button dot pack, and I'm going to give this a little bit of vertical padding. And then let's add the result label. So I'm going to create the result label variable. Going to set it to k label, and in here we'll set it window and set the text to be empty in the beginning, but this will update once we press the add button. And then let's pack this onto our screen, and then finally you can see the output of the program is this function here on a Matplotlib visualization, and you can tell that it's a simple harmonic oscillator just by the motion of this graph. You can see it always returns back to its original state, and this would describe something like a mass suspended on a string, and you can see here its position decreases and then goes all the way back. It decreases, goes all the way back. It decreases, goes all the way back, which describes the periodic nature of the mass itself as it moves over time. And we have our cool little toolbar at the bottom and our title here. This leads us into our second exercise, where you are tasked with creating a Tkinter plot of an ordinary differential equation that describes an object in freefall. And the ordinary differential equation describing an object in freefall is as following. We have the acceleration alongside the y-axis, because we have an object that's falling, is equal to negative g, where y is the vertical position of the object, t is time, d squared y over dt squared is the acceleration of the object in the vertical direction, and g is gravity. So let's begin by firstly defining our constants. We have gravity, which is equal to negative 9.81 on the surface of Earth. We have the time range, which is going to be 0 to 10 with 1,000 evenly spaced values. And we have the initial conditions. Our initial condition is going to be the vertical positioning of the object and the velocity of the object in free fall. So it's going to start at rest. No one's throwing it downward, and it's going to start at 0. So we're going to define that. And let's begin by importing our libraries. So here I'm going to start by importing Numpy for mathematical functions. And then I'm going to import the SciPy integrate feature. I think from import it's going to be odent, and then import then we're going to import tkinter as tk. Underscore tcag, and then we're going to import. I'm going to steal some of my previous code above here because it's a pretty long import. And then we're going to define the mathematical function. So let's call this def free underscore fall ODE, and inside we're going to take in y and t, and then we're going to return a state vector, and this output state vector is going to contain the velocity downward, and we already get that from here, which is going to be this thing, but we want the second value here, which is going to be the velocity downward. So I can do y1, put a comma, and then g. And then I'm going to get the solution for this. And then I'm going to pass in the freefall function, the input state vector, and then the time range. While that's going, let's define the solution values. So here we need to extract the velocity outputs. So it's going to be this, and then we're going to pass in 0, which will give us our velocity. And then v, and then here I'm going to get the acceleration values. So this will be solution, and then 1, and this is going to be our acceleration, which is going to be g, because acceleration when an object in free fall is always going to be constant. It's always going to be gravity. So now let's create our tkinter window in order to show this plot. So we're going to do window is equal to tk.tk, and then we can title our window, and let's give this a title of object in freefall. I'll put like ODE at the end of it as well. And then let's give this a dimensional value. So this will be 600 by 600. And then let's create a figure for our plot. So it's going to be figure, and in here I'm going to set the fig size to be equal to 8 by 6, and then I'm going to set the DPI value to be 100. And then let's create a plot for this. So plot1 is equal to fig.add subplot, and inside the subplot we're going to do 1, 1, 1. And then let's plot our values. So plot 1 dot plot, and over time we're going to plot the, let me think about this. Oh, pardon, this is going to be velocity, and this is going to be our position. And then here we're going to plot our position over time. And then let's label this as vertical position. And then let's set the x-axis labels to be time, and set the y-axis label to be the vertical motion in meters. And then we can give our graph a title, and let's call it Solution to Freefall ODE using ODINT. And let's also give this plot a legend. Give this a gridded background of true. And then we can create a canvas in Tkinter in order to hold this Matplotlib plot. So in order to do this, let's define canvas and let's set it equal to this. Embed our figure inside of it. Set the master to be the window itself. And then let's draw the canvas. And then we can pack everything into the canvas, so we can do canvas dot get k underscore widget, and then we can pack it. And then let's create our toolbar. So I'm going to call this toolbar. And then we can pass in our canvas and window. And then we can do toolbar.update. So now this code should generate a window called addition calculator with two labels, number 1 and number 2. And then we have two entries for number 1 and number 2. So I'm going to get the sum of 3 and 4. And when I press the add button, it returns the sum output here with the addition of these first two numbers. In this lesson, I'll be going over how you can make your simulations interactive using Tkinter. The first thing we'll be doing is embedding Matplotlib charts within Tkinter. And Matplotlib allows us to embed our plots into Tkinter within the graphical user interface. And in order to do this, let's demonstrate how you can embed a simple line graph into a Tkinter window. So in order to begin, we need to import Tkinter, and then we need to import the Matplotlib libraries. Once they are imported, I'm going to create a window here. I'm going to give it a title of line graph using Matplotlib and Tkinter, and then I'm going to establish the dimensions of the window to be 600 by 600. Once that is established, I'm going to create a Matplotlib figure in order to embed our plot in it. And in this case, I'm going to make a standard line graph. So here I make a figure of size 5 by 5. I set the x-axis range of the figure, and then for the y-axis, I just square each value of the range. So it'll be like x squared, starting from 0. So it'll be like an upward parabola. And then I set a subplot to the figure by running this method, and then I finally plot the line graph. And you can see here we have a figure created. And in order to embed the figure using Canvas, this code is going to do that. So here I create a class instance of figure canvas tk adge, and this is going to allow us to embed our Matplotlib figure inside of Tkinter. So here I put in the figure which we defined up here, and then I set the master parameter variable to be equal to the window, and the window is the tkinter window you want the figure to be embedded inside of. Once I do that, I do canvas.draw in order to outline the graph, and then I place the widget. So the canvas is going to be a widget, just like any other widget we've played around with, like labels, buttons, text inputs, and so forth. The figure canvas is going to be another widget, so this gets the widget component out of it, and then we pack it within the tkinter window itself. And then lastly, we're going to be embedding a toolbar. This is going to be called Navigation Toolbar to TK, and this is a toolbar utility which provides an assortment of button options at the bottom of the window that allows us to configure our plot. So here I embed it inside of canvas, and we pass in window, and then we call toolbar.update in order to show the toolbar, and this places the toolbar within the window. And then finally we run window.mainLoop in order to execute the program. And you can see here what I get as an output is a window in tkinter called line graph using Matplotlib in tkinter, and embedded inside of our tkinter program is going to be our line graph. And then here we have a toolbar of options we can play around with, like reset original view, previous view, left bottom pans, save the figure, and so forth. So this leads us into the first exercise of this lesson, where you'll be creating a plot with tkinter and Matplotlib, but in this session you're going to be creating a plot of sin of x rather than a standard line graph. So let's begin by importing all the libraries we need. So I'm going to import tkinter as tk, import numpy as np, import matplotlib.pyplot as plt, import matplotlib.figure, import from the figure import figure, and then from matplotlib dot backend underscore tag import, and then from here we're going to be importing the figure specific components, so figure canvas, tk edge, and then navigation toolbar to tk. And now that we've imported all these libraries, I'm going to begin writing the window code. So in order to do this, let's create a window variable, and then let's give it a title. Of sine graph using tkinter. And then let's establish the dimensions of it to be 600 by 600 by doing window geometry, and then within quotations specifying the intended dimensions of the window. And once we do that, let's define a function for our sine graph. So I'm going to call the sine function, and we're going to be taking an x, and let's return the sine of x. So we're going to be using numpy for that, np sine of x. And then now we can go about creating the x and y axes for our graph. So we're going to use linspace in order to create equally spaced values from 0 to 2 pi, because that's the range of the sine function, and then 100 spaced values. Y is going to be equal to the sine of the x range, And then let's create a figure instance. And I want this figure to be 5 by 5, and then set the DPI in order to be 100. And once we have that established, I'm going to create plot 1, and then I'm going to make a subplot. And then now we can go about plotting the function itself. So I'm going to do plot1 dot plot and plot the x and y values, and then label it as sine of x. And then we can establish the x and y labels. So I'm going to label the x-axis as x, and then I'm going to label the y-axis as y. And then let's give this a plot title. So I'm going to do plt.title, and this is going to be plot of sine x. And then we can finally finish this by giving it a legend. So now that we have that created, we can go about embedding it in our graph and then just finally displaying it. In order to embed this figure into our graph, we need to do a couple of things. So firstly, we need to create a canvas. In order to do so, we're going to create a variable called canvas, and then we are going to be using the figure canvas tk_adj feature in order to embed our figure into our canvas. And I'm going to set the master parameter variable to be equal to window, and then finally we're going to do canvas.draw to show our line graph. And then in order to place this within our window, we have to do canvas, and we need to extract the widget from the canvas and then pack it within the Tkinter window. And then we need to create a variable called toolbar, set it equal to the navigation toolbar, and then put it within canvas and window, and then do toolbar.update in order to display it. And then finally we can also pack it within the Tkinter window itself by doing canvas.pack, and then we can run the application. You can see that the output of that program resulted in the sine graph here. You can see it goes from 0 to 2 pi, so it's one cycle. And we have our Matplotlib figure embedded here, we have our toolbar down here, and we have our title up here saying the sine graph using Tkinter. You can also simulate mathematical models using Tkinter. And in this example, we'll be creating a plot that plots the solution for the following ordinary differential equation of a harmonic oscillator. And the ordinary differential equation of a harmonic oscillator can be described by this equation here, where W is the angular frequency, T is time, X is the position of the oscillator, and d squared X over dt squared is the acceleration of the oscillator. And this is a quick little animation of what harmonic motion this equation is describing. You can see here it's of a mass suspended from a string vertically. So in order to create this, we first need to import our libraries. I use Numpy for mathematical functions. I use the integrate feature of SciPy and Matplotlib. And here is the function that defines the ordinary differential equation for the harmonic oscillator. I take in y, which is the positional state vector, so it'll take in x and v. T takes in time, and omega stands for the angular frequency, which is related to the spring constant and the mass of the spring here. So here I extract x and v. X is like the positional element, it's y in this case, but imagine this like rotated 90 degrees, that would be the scenario here. And then I take dy dt, and this is a state vector including the output equation. So we get the output of this equation here, which is going to be a negative omega squared times x, right? Omega squared times x, and we're just setting it equal to d squared x over dt squared is equal to, we're moving this part to the other side of the equation, so we get negative w squared times x as the output, and returning it as a state vector with v in the front and the output here, and we return a state vector. So here I define the constants and initial conditions for the ordinary differential equation. I define the angular frequency, I just use an arbitrary value for the sake of demonstration purposes, and then the initial conditions. I set the initial condition for the positioning to be 1, and I set it to be initially at rest. And then here I specify the time range that I want to integrate over. And then now I run the ODE solver with the mathematical function of the harmonic oscillator, the initial state conditions, and the angular frequency passed in. And then I extract the position and velocity from the solution. This extracts, since our solution returns a state vector, we just need to extract each of the positions from the state vector itself. So this extracts just like the v values, and this extracts just the omega squared times x values and stores it into their respective variables. And now that we have this solved, we want to display the output using a tkinter window. So here I initialize a tkinter window, I name it simple harmonic oscillator solution, and I give it dimensions of 600 by 600. And then I create a Matplotlib figure that's 8 by 6, and I add a subplot to the figure. I plot the line graph solution of time, so t on the x-axis, y on x on the y-axis, which is the positioning of the block here as it moves, and label the position. I do x and y labels, and the title of the graph I put a legend and set there to be a gridded background. You can see that the output of this will be a downward looking like parabola, and this will describe an object in freefall. So let's say like you take an object and then you drop it, so it'll go down, and go down, and go down. Its y value as it goes down will descend at a faster rate. So you can see here, like it starts off pretty slow and then it starts dropping by a lot. This is because as a object stays in free fall longer, the acceleration will make its velocity downward faster. So go down faster at a faster rate. Hence this parabola looking graph here as it drops. So its y value will drop faster, 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 faster as it spends more time in the air due to the gravitational constant of 9.81 of Earth. And you can see we have our cool menu bar down here and our title object. In this lesson, we'll be going over how you can style your interactive applications in tkinter. So in order to do this, we'll need to cover styling components, and Python's built-in GUI involves customizing the appearances of specific widgets like buttons, labels, frames, in order to make them more visually appealing and user-friendly. So here, Tkinter has its own basic set of default styles, which you can check out here, but we'll be using a specific theme called the Sun Valley theme, and it looks a little bit better than the default theme in my opinion. Here are some of the components, what they look like. Here are check buttons, radio buttons, tabs, sliders, and so forth. And there's different types of themes. If you want a more modern look, you can check out the Forest theme, Azure, TTK Bootstrap, which matches the Bootstrap CSS library themes if you're into that. And let's begin by importing all the necessary libraries. So here I'm importing Tkinter, and then I'm importing the Sun Valley theme. And then here I create a window, I call it root, and then I add a button to the window and I pack it onto the window, and then this last line here sets the theme of the components to be in dark mode, and it sets it to be in the Sun Valley configuration. And you'll see, so you can see here in our pop-up window we have this cool little button that's in dark mode. It's kind of hard to see since it's a dark themed, but it looks a lot more different and a lot better than. This leads us into the first exercise, where you'll be creating your own component using the Sun Valley themed. So here let's create a new code cell, and let's begin by importing our library. So I'm going to import Tkinter, then I'm going to from Tkinter import TTK, and then finally let's import the Sun Valley themed, SV for Sun Valley, and then TTK. And now we have all these imports initialized. I'm going to create a window called root, and this is going to be a tkinter.win.tk. And then let's create some text that we can embed within this window. So I'm going to call this label. And inside here I'm going to pass in root and then set the text to be hello world. And then we can pack this text onto our window display. And then let's add a button. So we can do button is equal to ttk.button. And then we can embed this into our root window and set the text to be equal to click button. And then we can also pack this onto our window as well. And then finally, let's set the Sun Valley theme. So it's going to be SV, TTK, and then we can set the theme to be in dark mode. And then finally, let's run the application itself by running root.main loop after we set our theme to be in dark mode. This creates a window here with our text hello world and a button with click button inside of it, and it's in dark mode and it adheres to the Sun Valley theme. We can also create forms using Tkinter. So before we had forms that look like the following, but we can embed our Sun Valley theme in order to make them look a lot more visually appealing. So in order to do this, you can create a window. Here I create a window, call it user form, and I make it 500 by 300 in dimensions. And then I set the theme to dark mode using Sun Valley. And then we can configure more styles. And this is where you want things to have a specific look to it. And in order to do that, we create a style instant in order to make our own customized styling. So here I call it TTK style, And then you use configure in order to create a class name. And what this name is going to do is it's going to create a universal kind of palette in order for us to configure specific styling values. So here I call this margin.tlabel, and this is going to be applied to some labels, and it's going to give it a margin, a top margin of 10 pixels, hence .tlabel, because top margin, like top, and then to the label itself. And here all the style is going to do is it's going to give whatever label it's applied to a top padding of 10 pixels. So here you have 10 pixels added as padding. And then now the code below will initialize the form. I create a label for the first name with the margin tlabel styling class. So you'll see visually this is going to have a little bit of padding, a little bit of white space at the top of it, and then I pack it onto the display. I do the same, but in this case this is going to be an input for the first name, and I pack it. No custom styling here. I add a last name label, and then create a last name input entry, and then I create one more label for the email, an input for the email, and then I create a label for the result output with the tlabel style, and then I pack it onto the display. Here I create a submit form action function. So this, when invoked, will get the first, last, and email from each of the different inputs by running the get method on the entry variables themselves. And then you can see the output form looks like the following. We have the first name, last name, email, and their respective entries. And you can see here we have our custom class, what is it called? Margin tlabel style here. And you can notice it because above each little text here, we have a little bit of white space, and that's our padding top, which was initialized here, which gives it 10 pixels worth of padding at the top. And now we can enter in our details in our user form. So I can say Bob Doe at gmail.com. And when I press this create account, it retrieves the values from each of these input fields and then prints it out into our result label here. And you can see each of our entries look a little bit different. They have the Sun Valley theme, so that they look a little bit more sleek in my opinion, and it's a lot more visually appealing, especially if you're creating a more mainstreamed application that's going to be used by more users. So now this moves us into the final exercise of this lesson, where you'll be creating a rocket ship form using the Sun Valley theme. Give it a shot and come back to this video when you are done. So let's begin by importing the libraries you'll need to create this form. So let's first import Tkinter, and then let's import from Tkinter, import TTK, and then finally let's import the Sun Valley theme. And once we have these three things imported, let's create a window called root, and let's call it tkinter.tk. Let's title the window rocket ship form, and then let's give this dimension values of 500 by 300. And once we create this window, let's set the theme. So it's going to be svttk.set theme, and let's put this in dark mode. And let's create a styling class because it wants us to create a custom style called padding.tlabel that applies a top padding of 10 pixels and a bottom padding of 5 pixels to all labels. So we need to create a style class to do that, so I'm going to call the style, and you can do ttk.style in order to create an instance of it. And then we can use the configure method, and this is going to be called padding.t label, and this is going to apply a padding. And remember, we go in the direction kind of like a clock, so we'll go left, top, right, and then bottom. So we don't want anything, we don't want anything on the left. We want 10 pixels at top, 0 on the right, and 5 pixels at bottom. And then let's create our labels. So let's first create one for the name. So this is going to be ttk.label, and in here we're going to put this under the main window root, and then let's ask for the rocket ship name. So rocket ship name, and we're going to give it a style of padding.t label, which we initiated here. And then let's pack it into our main window. And then let's create one for the destination and the mass. So destination label, rocket ship destination, and then let's pack it onto the display. And let's make sure we make entries for each of these. So let's create name entry, and this is going to be ttk.entry, and we're going to pack it into our main window. And then let's make sure it will display. And let's do the same thing for our destination. So we're going to call this destination entry, and then we can pack it onto the window display here. And then let's create one more for the mass. And we're going to call this mass label, rocket ship mass. We're going to have a padding top to it, and then mass entry. So this will be all the component specifications for the form in order to get user input. And once we have that, let's also create one final label that will hold the output. So we're going to call this result label, and this text will show the output of the form. And let's set it to be like output by default. So this is what will show before the user submits the form. And then we're going to give it the T label, class name. And then let's pack it onto the window. So that should be all we need before the action. So let's call this action blast off, and this will run when the user submits the form. So when the user submits the form, we want to extract the name, the destination, and the mass. So we're going to do this by using the entry.get method, which will extract the user input from the entries themselves. So we're going to get the name, the destination, and then the mass. Mass entry.get. And once we extract each of those different values, let's create the output, which is going to be a formatted string including the name. And then let's see, the output should look like the following. So we have the rocket ship name here, Falcon 9, is heading to the destination, International Space Station, and weighs the mass kilograms, exclamation point. So I can use this as a template. So Falcon 9, that's the name of the rocket. So we'll put a name, International Space Station, that's going to be the destination. And weighs the mass, kilograms. And then now we can configure our result label to contain the output text. So I'm going to set text is equal to output. And then now let's create a button. I'll call this register button. You can see this is the output here. We have our rocket ship form, and we have our 3 labels here describing the entries. We have 3 entries, and our output label and our blast off submit form button. And you can see this is all in the Sun Valley dark theme styling, and each of our labels has the padding T label styling on it, which gives it a top padding of 10 pixels and a bottom padding of 5 pixels, which you can kind of see by looking at the labels. And let's try submitting this form. So I can put in Falcon 9, and it's going to the International Space Station, and it has a mass of 1,000 kilograms. In this lesson, we'll be covering how you can export data using files in Python. So firstly, in Python, saving data with files is pretty common, and there's different ways you can accomplish it. Python provides various built-in modules and libraries for you to work with different file formats. And here are some of the most common formats. There's CSV, which we've explored before, which stands for comma-separated values, where each row represents a record of data, and the columns represent attributes of the data or different variables. There's also JSON, which stands for JavaScript Object Notation, and this is typically used to store structured data. It looks a lot like dictionaries in Python, and it's pretty easy to parse, and it's supported by a wide array of languages. Python has a built-in JSON module. For more astronomy-related datasets, HDF5 data structures are pretty popular. It stands for Hierarchical Data Format version 5, and it's commonly used for storing large data sets and complex hierarchical structures, and you can use the H5Py library in order to interface with it. And lastly, you can use Excel files directly with Python using the OpenPy Excel library for reading and writing from Excel datasets. So let's cover how you can save data into a CSV file. In order to do it, you can import the CSV library here, and then here is a list of structured data I created containing the names and ages of various people. So I have one object here and another object here, and this is the data I'm going to be saving into a CSV file. In order to save this into a CSV file, I'm going to be using the writer functionality of the CSV file. So let's say I wanted to write to a CSV file named people.csv, and we're going to use W mode because that stands for write, and we're going to be writing directly to that file. And then I'm going to reference this file as file and use that variable here. And then in this line, I create a writer instance, passing in the file we're going to be working with, and we're going to be passing in the field names. So in this case, the field names are going to be the name and the age of the person by using the keys. And then I write a header to it, and then I write each of the rows of the data. So I'll save John age first, and then Alice and her age as well. So this writes the data into people.csv. And if we open this up here, you can see it generated a CSV file. And the cool thing about Jupyter Notebook is that it will visualize it for you. So under the hood, it's a bunch of values separated by commas, but you can see this interface makes it look like a table using the delimiter of a comma because it's comma separated. So you can see here we have 2 rows, John who's 30 and Alice who is 20. So what if you wanted to read from a CSV file rather than write from it? So you would do the same open command, but in this case you only need to use the R mode, which stands for read. Set new line to this value, and then reference it as file. And then now you can use the reader functionality. So I create reader here, and then I create CSV reader and pass in the file. And then we can iterate for each of the rows in the CSV file by using a for loop. So I say for row in reader, it'll print out each of the rows, and in this case we have 3 rows, one for the column values, so name and age, and then 2 for each of the people, John who's 30 and Alice who is 20. We can also work with JSON files. So in order to do this, we're going to import the JSON library, and writing to a JSON file is pretty simple. So here we want to save the data, which we instantiated up here. It's the same data we saved into the CSV file, and all we have to do in order to write to the JSON file is do json.dump, pass in the data you want to write, and then pass in the file. And it pretty much works whenever you have data that's structured like the following, where you have a list of values and each of them are dictionaries. So you can see here, this will load it into the JSON file, and if we go back here, you can see we created a JSON file here. And Jupyter Notebook has a funky way of visualizing it, but you can think of each of these as curly braces surrounding the internals. So we have name John, who's 30, and then we have Alice, who is 20, each having their own little value with an index associated with it. Reading from a JSON file is pretty easy as well. You can do with open people.json in read mode, reference it as file, and then you can use the json.load method, pass in the file you want, which is people.json, and then you can print it out here. So you can see it returns a list, pretty much the same kind of format we had before, with dictionaries containing the attributes of the data. This brings us into our first exercise, where you will be saving telemetry logs both in CSV and in JSON. So here I have this hard-coded array of telemetry values that contains values for temperature, pressure, velocity, altitude, power level, and orientation of a spacecraft. So roll, pitch, yaw. So this would be like telemetry of a spacecraft or a satellite in orbit. And it's saved in a list in dictionaries here. And in order to solve this, let's begin by importing libraries. So I'm going to import CSV and then import JSON. And then let's first save into a CSV file. So I'm going to do with open. And let's call this telemetry.csv. I'm going to put this in write mode and then set new line to empty. And let's reference it as file. And let's use the writer tool, so csv.dict writer, in order to create a write to this file. So I'm going to pass in file. And we need to set the field names, and that's going to be represented by the keys here. So like timestamp, temperature, pressure, velocity, altitude, and so forth will be their own column. So each column will model the key values. So telemetry, get the first index. This just gets to the first item here, and this just returns the keys, each of the keys. And then dot keys. And then let's create a head for this, write header. And then let's write to the rows. And then we can pass in telemetry. And then it wants us to also read from the file once we write to it and then print out the contents. We can do that by following the same kind of process. Let's see, let's copy this here. But in this case, we're going to be reading from it only. And then let's use the reader, which is going to be equal to csv.reader with the file reference passed in. And then let's iterate for each of the rows. And then we can print the row contents. Let's see. And then I have hard-coded data that I want to be saved. And I create a method here called downloadFile that opens up a CSV file called data.csv in write mode and saves these values inside the data variable into the file itself. And the field names, the columns of the CSV will be name and age. It'll write to the header. So you can see here it created a Tkinter window with the download data button. And when I press download data, it created a file here called data.csv containing the values that were hard-coded that we told it to save. So it has John in 30, Alice in 20, and this is a CSV file. So now it's your turn to try this out. Your objective is to create a Tkinter window of your own that saves this hard-coded data. So let's begin by importing the libraries. So import Tkinter, import from Tkinter, import TTK, import the Sun Valley theme itself, sv_ttk, and finally import JSON. And then after we import that, let's create the window. So it'll be tkinter.tk, and then we can set the Sun Valley theme. So svttk.set_theme, and we can set it to be in dark mode. And then we can define the function that will occur when we press the button. So we want it to be downloaded in JSON this time, so we'll open up the file name. It wants us to name it rockets, so rockets.json, and then we can have this in write mode and have it referenced as file. And then we can use json.dump in order to have rockets saved onto their program, and then reference the file. So it'll save this data into the JSON file. Now let's create the buttons themselves that we want to be displayed. So I'll create button, ttk.button, save it to the root window, and let's give it a text of download JSON, and the command is going to be set to execute the download JSON function. And then let's pack it into our display. So now you can see we have this window here with the download JSON button, and when I click it, it should create a JSON file. You can see it created rockets.json. In this lesson, we'll be covering how you can create your own completely integrated application using Tkinter. So here I import Tkinter, and I import the Sun Valley theme, and then I create a Tkinter window and title it Sliders with dimensions of 500 pixels in width and 200 pixels in height. And then here I use the scale widget to display a horizontal numerical slider from 0 to 200 with a tick interval of 20. As you can see, it created a horizontal numerical slider with its default value set to 40. You can also display plots using Matplotlib and Tkinter. So here I import Matplotlib and Numpy alongside the figure and canvas figure values in order to use the Matplotlib figures inside of Tkinter. And then I create another Tkinter window with a custom sign plot and dimensions of 500 by 800. And then inside that window, I want to embed a amplitude slider. So this is going to be a horizontal numerical slider starting from 200 going up to 20 with a tick interval of 1 and an orientation of horizontal with 400 in length, 400 pixels in length. And then I set the default value in order to be 1 and I pack it onto the window. Then I create an instance of a figure that's 8 by 6 and embed the Tkinter, embed the Matplotlib plot for the Tkinter window. And then here I create a generate plot function that will allow us to update the plot when a generate plot button is clicked. So here I check if there is a figure that's created in Matplotlib, and then I clear it, making sure that everything is blank. And then I get the amplitude from the amplitude slider, which is configured by the user. I set the x range of the function, so it's going to be 0 to 10 with 100 evenly spaced values, and then the y will be the amplitude inputted by the user multiplied by the sine function. So what the user inputs will control the amplitude of the sine wave, which is like how large the sine wave is in magnitude. I create it as a subplot, and so you can see here this is what the application looks like. We have the initial sine wave function visual plot here from Matplotlib with an amplitude of 1. You can see the topmost value is 1 and the bottommost value is -1. And I can input the amplitude I want here. So let's say I want an amplitude of 10. I can then press this generate. You can export data files within this application here. And in this case, let's export the data from the plot of sine of x we've created. So here I import all the libraries we need to do this. I create a Tkinter window. I add an amplitude slider. I add a figure to contain our math visual. And then I have our generate plot function that calculates the sine wave given the amplitude inputted by the user and then plots it onto canvas. So all the same code, but this time I'm going to be adding a download file button. And here I import the CSV because I'm going to be saving the data into a CSV file format. And then I create this download CSV function here that gets the amplitude inputted by the amplitude slider by the user. And then I define the x values for the function. And then I create a download CSV file, open it in write mode, reference it as file, and then I use the dict writer tool within CSV in order to write the dictionary values into the file with field names of x containing the x values that are going to be inputted into the function and the y output values outputted by the function. I create a header in the file. So you can see this time around we have the amplitude slider here, but now we have the download CSV. So we can set the amplitude to like 8 and then we can click download CSV. And what this will do is it will generate a CSV file So you can see data.csv. So you can see download.csv. This brings us into the first exercise of this lesson, where you're tasked with creating an interactive line plot. So here I import all the libraries we need. And firstly, let's begin by creating a tkinter window that has the Sun Valley theme. So let's call this root, and we can do tkinter.tk. And then we can set the Sun Valley theme, so here, and then set theme, and let's set it to dark mode. And then let's give this window a title, and I'm going to title it custom line plot, and then set the dimensions of it to be 500 by 800. So now that we have our window initialized, let's create the slope slider that's going to adjust the slope of the function they want, which is a line graph. So slope slider is equal to tkinter.scale, and we can put this in our window. Let's start from 1 and then set it to 10. The tick interval is going to be 1, and we can set the orientation to be the tkinter.horizontal, and then have it be 400 pixels in length. Then we can set this value, the default value, and I'm going to set it to 1. And then we could finally add this to the window. Now let's create a figure to hold the mathematical function. So I'm going to invoke figure, and we can set the fig size to be 8 by 6, and then we can set the DPI to be 100. And then let's create a canvas using figure canvas tk, and then let's pass in the figure, and let's give it a master window of root. And then let's create a function that's going to allow us to generate our plot. So generate plot, it's going to take in the canvas and the figure, and then it checks if there's a figure present. If there is a figure present, let's make sure it's clear in order to update it fresh every single time. And then we can get the m value from the user by getting slope slider.get, and then we can define the x value range. So it's going to be linspace 0 to 10 with 100 evenly spaced values, and then y is going to be the m inputted by the user times the time range x. And then we could create a subplot, and then plot our x and y values. So we're going to do plot.plot, and then finally draw everything to the canvas. And now that we have that, let's create a plot button that's going to trigger this generate plot function. This is going to be ttk.button, taking in the root window alongside some text. and then the command, and I'm going to make this a lambda function that invokes generate plot each time, passing in the canvas and the figure. And then let's pack this onto the window. And then let's create a download CSV function that's going to download the CSV output contents whenever the button is pressed. So amplitude slider dot get, and then let's define the time range, the X range here, and then let's open the CSV file. It's got to be called slope.csv, and we're going to put this in write mode, and then let's set new line to be empty, and let's reference it as file. And inside here I'm going to initiate a writer, so I'm going to call csv.dict writer, and then I'm going to pass in the file alongside the field names, and I want each of the columns to be called X and Y. And then let's write the header first, and for each value inside of the X range, we're going to save its corresponding Y output. So that's going to be Y is equal to M times X of I. And then we can write a row for it. And this is going to be a dictionary because it's dict writer. It writes from dictionary to CSV. And we're going to save X, which is going to be X of I, and then Y, which is going to be Y of I. Oh, apologies, just Y. And then let's create an instance of a download button, which is going to be set to tk.button, which is going to be on the root window and has the text of download data. And this, when pressed, is going to trigger download CSV. And then let's pack this button onto the window. And now let's pack the entire widget onto the window. So we're going to do get tk widget dot pack canvas, and then generate plot. You can pass in canvas and the figure. So you can see here we have an output of a numerical slider that determines the slope of the line, and whenever I change the value, so we have 1 right now, but let's say I change it to like 3, it updates the graph accordingly to have the slope changed. It's a bit subtle, but you can see it's 30 over 10, so it has a slope m of 3, and let's say like 8. So you can see if we check out the file display here and open up the slope.csv output file, it will print out 100 equally spaced values of x from 0 to 10, and its core. Welcome to the final project of the Python for Aerospace course. In this project, we'll be working on a comprehensive program that's going to model a satellite trajectory and analyze it using mathematical functions. So firstly, before we dive in, let's cover some conceptual background knowledge. So firstly, satellite trajectories consist of a lot of core topics that make up the entire subject. Things such as orbital mechanics, orbital elements, two-body and the n-body problem, perturbations, things that deviate the orbit alongside external forces, orbital maneuvers, and propagation methods are all things that are encompassed within this category. So a few of the things we're going to be focusing on specifically as we work on this project is orbital dynamics, and orbital dynamics refers to the motion of celestial bodies under the influence of gravity, and we use it in order to predict the motion of these objects using Kepler's laws of planetary motion alongside Newton's laws of motion gravitation in order to understand how these celestial bodies will be influenced by gravitational forces. So, like we mentioned, the Kepler's 3 laws is that every orbit is an ellipse. The distance between positions of an orbit alongside orientation of an orbit. And we have orbital elements. These things describe the characteristics of a satellite's orbit, and it includes its shape, orientation, and positioning, and these are also referred to as the Keplerian elements. We can also describe the motion of a satellite using simplified models that mimic the behavior, and the most simplified model is a two-body problem, where we have a central body and a satellite body that's orbiting it. And there's more complex versions of this, which is beyond the scope of this lesson, but they are referred to as n-body problems, where you have more than two objects orbiting one another. But in the case of satellite orbital characteristics, you're dealing with a two-body problem. In terms of perturbations are used when modeling realistic satellite trajectories because they take into account external forces. External forces that modify an orbit are called perturbations that can cause the satellite to deviate from its ideal orbit. And things that are considered as perturbations include gravitational influences from outside celestial bodies, such as other planets, large asteroids, and other things that could deviate a satellite's orbit. There's also atmospheric drag. The Earth's atmosphere can introduce drag to a satellite due to its interaction with air molecules, which will eventually cause the satellite's orbit to decay and decrease in altitude. There's also solar radiation pressure. This is caused by photons that are exuded by the surface of the sun that add extra pressure on the surface of the satellite. There's also geopotential forces, which are caused by the irregularities of the Earth's curvature. Earth is not a perfect sphere, so deviations within the Earth's surface can cause different gravitational forces to act upon the satellite. There's also thrust generated by the propulsion systems on the satellite itself, which are used for maneuvers, which could introduce more perturbations. And then lastly, there's magnetic fields generated by the Earth's magnetosphere and also by the onboard magnetic components housed by the satellite that could also influence orbital parameters. So we can break down satellite trajectory into a few categorical steps because it is pretty complicated, and this is just the sake for our trajectory analyzer. Real-life simulative trajectory analyzers are a lot more complicated, but for the sake of simplicity and educational purposes, we'll be following this kind of generalized step outline. First is orbit determination. This consists of predicting the satellite's positioning and velocity based on observed data. Then there's numerical propagation. Propagation is when we use mathematical models in order to predict the satellite's future trajectory over time. There's perturbation modeling. This models or takes into account the external forces that are imparted on the satellite, such as external gravitational forces, atmospheric drag, and other things we mentioned here under the perturbations list. And then finally, there's calibration, where we adjust different parameters within our model in order to improve the accuracy of the simulation as we continue to experiment with the observed data at hand. This leads us into propagation methods, and propagation methods are numerical models that are used to calculate future predictions about the satellite's orbital parameters, and a few popular mathematical propagation models include SGP4, which is a simple and efficient numerical model for predicting the positioning and velocity of Earth-orbiting satellites. There's Kepler on perturbed orbits mathematical models, which relies on Kepler's laws of planetary motion to analytically compute the positioning and velocity of a satellite in an ideal orbital scenario with no external perturbations. And then there's the J4, which expands upon the previous Keplerian elements and also adds in other additional terms in order to take into account Earth's oblateness and higher order gravitational harmonics. And more updated versions of these, it started off with a baseline model of G2, and then there's higher level terms that take into account more nuances such as J3 and eventually J4. A side note for perturbation models also allow us to make more robust and accurate numerical satellite trajectory models, and they take into account gravitational perturbations, which are influences of gravitational forces from other planets, atmospheric drag, which is caused on the surface of the spacecraft by its ballistic coefficient, atmospheric density variations, and drag coefficient, and its solar radiation pressure modeling, which models the pressure exerted by solar radiation on the satellite surface. In regards to orbital maneuvers are changes to the satellite's orbit, which are achieved by applying external forces onto the satellite itself. And some popular types of orbital maneuvers include orbit transfer. This is when a satellite moves from one orbit to another. So for example, we can have a satellite within low Earth orbit move to like a medium Earth orbit. And one very popular orbit transfer maneuver is called the Hohmann transfer. And this maneuver is used to transfer a satellite between two coplanar circular orbits of different radii. So for example, if we have one orbit here and we want to move to the secondary outer orbit here, we'll use a Hohmann transfer in order to move this orbit to this orbit. There's also attitude transfer. This is when you change the orientation, such as like the rotational angles of the satellite, so the way it's oriented or the way it's facing different directions, and this can account for perturbations that are influencing the satellite's directionality. There's also rendezvous and docking orbits, and a rendezvous orbit is when two approaching spacecraft want to meet up at some point in space, and this is usually concluded with a docking phase where the approaching spacecraft physically attaches to the target spacecraft. And then lastly, we have a niche type of orbit maneuver called station keeping, which is used to maintain a satellite's position and orientation within its designated orbital spot. So in order to begin making our satellite trajectory analyzer, we'll need this behemoth list of libraries to be imported. So let's import that. And your turn here, you need to create a Tkinter window titled Satellite Trajectory Analysis with the dimensions of 1200 by 800. So in order to do this, let's begin by creating our window. So I'm going to do tkinter.tk, and then let's give this a title. So I'm going to call this Satellite Trajectory Analysis, and then we can set the dimensions of this to be 1200 by 800. And moving on to styling, we first need to set the Kinter theme to use Sun Valley. So in order to do that, we do sv_tdk.set theme, and we are going to configure this to use dark mode. And then let's also set the Matplotlib theme to use dark mode as well. So I'm going to do plt.style.use and then plug in dark. And then let's create a style instance in order to create one custom Kinter class. So this creates our styling instance, and then let's configure it to create our first class, which is going to be called margin T label. And this is going to include a padding of 0, 20, 0, and 5. And then let's create one more titled T button. And this is going to include two styles, a padding of 10, 10, alongside a background set to this color. So now that we have our styling configured, this is going to allow us to create side-by-side frames. So in this case, we're going to have a frame. Oops. Oh, instead of dark, it's going to be dark_background. So in this example, we want to create two horizontally adjacent frames. So we're going to have one big frame on the left side and another big frame on the right side. And we're going to designate them as left frame and right frame. So this creates our two frames. So our left frame is going to be in our root window, and it's going to be 500 in width and 600 in height. Our right frame is going to be slightly smaller. It's going to be 300 in width and the same height. And then this packs their frames side by side. So I set left frame pack, put the same side as left, fill both and expand true, and then I put in right as well, and this packs it exactly right next to the left frame. And then now we're going to be adding interactivity to our user interface, and I'm going to embed 6 sliders for each of our Keplerian elements. If you remember that there's 6 orbital characteristics that define the positionality and the different characteristics of an orbit, and they are the semi-major axis, the eccentricity, the inclination, the right ascension of ascending node, the argument of perigee, and the mean anomaly. You can see here I have 3 example labels and sliders configured for the first 3 Keplerian elements. Your task is to create 3 more sliders for the right ascension of the ascending node, the argument of perigee, and the mean anomaly. Give it a shot. So here, we're going to first create a slider code alongside of a label for the right ascension of the ascending node. So in order to do so, let's begin by creating our label. And this is going to be equal to label. And this is going to be within the right frame. So I'm going to do right frame. And I'm going to set the text to be right ascension of ascending node. And put a comma there, a space. And then let's give this a style and have that style be labeled margin.t label. And then let's pack this into our window. And then now let's create a slider. So I'm going to copy this reference code, and I'm going to name it R and slider, and we're going to embed it in the right frame. It's going to be 0 to 360, like specified here, with a tick interval of 40. It's going to be horizontal, and I'm going to be 400 pixels in length. And then finally, let's pack this onto our display as well. And then let's do the same thing for argument of perigee. So we're going to do I'm going to name this argument periapsis label. And then in here, we're going to designate it as argument of perigee and styling standard. Let's pack this into our display. And then let's name this argument periapsis slider and pack that. And then it's going to be 1 to 360 with a tick interval of 40. And we can save the other configurations. And then now let's create one more for mean anomaly. So let's name this mean underscore anomaly label. And then let's pack it into our display. Let's call this slider. And then let's set the text to this to be mean anomaly. And it's going to be 1 to 360 with a tick interval of 40. And that's all the code we need in order to make 6 sliders with 6 designated labels describing each of the 6 Keplerian elements in our form. And I made this helper method here that takes in the output values inputted by the user in the form for each of these sliders and takes it in as parameter variables for this function here, and it sets each of the sliders to be that variable designated in this parameter list. So here I have a default slider setting because this sets all the slider values, and it's going to be 10,000 of the semi-major axis, a 0.1 eccentricity, a 90 inclination, right ascension of ascending node of 40, argument of periapsis of 1, and a mean anomaly of 1. And it looks like I named one of these values wrong. Mean anomaly slider, and then this calls the function. Actually, let me rename this. I think this is the correct naming. And then we can run this one more time. And then now let's create the graphical outputs. So in this case, we're going to be making an altitude versus time graph, which describes the altitude, how high up the satellite is in orbit over time. And this uses a propagation method. Remember, a propagator is a mathematical model that allows us to keep track of the positioning of the satellite over time. And it can be used to predict the altitude of satellite in respect to the surface of the Earth. And we're going to be using a propagation method called SGP4. And this is provided by the SGP4 library under the SatRec class. So here I define a function called traceAltitudeGraph that takes in a TLE value, and it saves a satellite instance using SatRec using the TLE configuration. So I pass in TLE1 and TLE2. This defines a time range that we're going to be running our propagation method over. So I set the start time to be 0. I want this to last for an entire day, so it multiplies 24 hours in a single day, and for each hour we have 3,600 seconds. So this is in seconds, and then 60 seconds is in 1 minute, so we set the step interval to be 1 minute. And then I create this A range and linspace to create our entire points for each of the X values. And then now I create an altitudes list in order to store our Y values, which will be the altitude. And I loop over each of the timestamps, and I save each of the timestamps within Julian date, which is a time reference system that's used by the SPG4 propagation method. And then I run the SGP4 algorithm on the specific timestamps themselves, and that gives me a state vector of the following values. And R is the value we want out of this output, and R is a a position vector of the satellite representing its three-dimensional coordinates in space. So it has the X, Y, and the Z. And then now with this positioning information, we can calculate the altitude of the satellite above the Earth's surface. So we get the altitude by calculating it here, and then getting the square root of it and subtracting from the Earth's main radius in kilometers. And then we finally append this altitude value to our entire altitudes list. And now we want to display this as a mathematical figure, so I create an instance of a figure here with these dimensions, and then I embed it into the Tkinter window using this line of code. I pack it into the window with a padding Y of 15 pixels, create a subplot for it, and then I finally plot the X and Y axis values of times and altitudes respectively. I give the plot a gridded background, and I finally draw everything on the plot. And in order to run this trace altitude graph, we need to pass in the TLE configurations of the satellite. So I pass in one for the ISS that I retrieved in the past, plugging in the first line here and then the second line. And then now we can visualize a 3D orbit in a figure using the PyASL library that extracts the positional trajectory data using the Kepler ellipse XYZ pos features of PyASL. So here I create a second figure in order to create the three-dimensional plot. And I embed it within the left frame using the figure canvas TK_ADG class. And then I create a method that takes in the 6 Keplerian elements and then plots them in the 3D graph. So here I take in the 6 Keplerian elements and then the figure to visualize it on. And then I create a Kepler ellipse orbit instance, plug in the different parameter values that are calculated beforehand. I define a time range here. And then this gets the positioning, this calculates the positioning of the orbit and returns the X, Y, and Z as a positional state vector at that timestamp. And then I clear the figure if it already exists in order to refresh the entire canvas and make it all clean. And then I pack the canvas onto a Tkinter widget. I create a subplot for it, making sure it is going to be a 3D visualization. And then I create 3 plots. I create a plot for Earth. This is going to be a single point centered at the center of the plot, giving it a marker size of 9 and labeling it as Earth. And then I plot the satellite trajectory, which is all the positioning output calculated up here. And then I plug in the X and Y values respectively. And then finally I plot the periapsis, which is the point, a single point of the orbit that's closest to the central body, in this case Earth. And this is the X value index of the periapsis and the Y value index of the periapsis. And then finally I plot everything onto the canvas. And now I invoke this method here that takes in the Keplerian elements alongside the figure and visualizes it. I plug in default values. And then finally we're going to be adding additional buttons to our display. And you can see now that we have our generated output in our Tkinter application. Here we have our altitude over time graph that we generated for our left frame, and then we have a right frame here which contains all of our different slider values for 6 Keplerian elements, and you can see we can adjust them. And this should update both of the visualizations once we click the update button down below, alongside downloading a respective CSV data file with clicking the CSV download data file. And we also have our 3D visualization of. Congratulations for completing the Python for Aerospace comprehensive course. In this course, we covered 5 interactive projects after establishing conceptual aerospace knowledge alongside the foundations of Python programming. You began with creating an aircraft performance calculator after learning the foundations and basics of Python syntax and functionality. And then we went about creating a satellite tracker after going through a few Python libraries and visualization tools. Thirdly, we created our own solar system orbital visualization by learning how to make our own 3D visualizations using Matplotlib and using numerical solvers. And we went further into numerical solvers and calculus by creating our own rocket equation numerical solver that mapped out an ordinary differential equation in order to solve the rocket equation. And then lastly, we developed a comprehensive satellite trajectory analyzer that brought together all our previous aerospace and Python knowledge that mapped out not only a 3D visualization, but also an altitude versus position mathematically calculated plot that took into account the user's input using a Tkinter application and a form including 6 numerical sliders within it. I hope you enjoy this course. If you'd like to keep up to date with some other projects I work on, I also have a YouTube and Twitter. I've linked the handles below, and I also keep a log of all the projects I am currently working on my website, angelinasavoy.com. Thank you so much for attending this course, and I hope you have a great rest of your day.